We, the people of India, sovereign socialist secular democratic republic, justice, liberty, equality, fraternity in our constituent assembly hereby adopt, enact and give to ourselves this constitution. Having solemnly resolved to constitute India into a and to secure to all its citizens, social, economic and political, of thought, expression, belief, faith and worship, of status and of opportunity, and to promote among them all assuring the dignity of the individual and the unity and integrity of the nation. This 26th day of November, 1949 to 1-2-1. Subs. By the Constitution 42nd Amendment Act, 1976, Seconds. 2, for Sovereign Democratic Republic WEF. March 1, 1977, 2. Subs. By the Constitution 42nd Amendment Act, 1976, Seconds. 2, for Unity of the Nation WEF. March 1, 1977, the Constitution of India Preamble. As we look at our surroundings, we see a large variety of things with different shapes, sizes and textures. Everything in this universe is made up of material which scientists have named matter. The air we breathe, the food we eat, stones, clouds, stars, plants and animals, even a small drop of water or a particle of sand, everything is matter. We can also see as we look around that all the things mentioned above occupy space and have mass. In other words, they have both mass and volume. Since early times, human beings have been trying to understand their surroundings. Early Indian philosophers classified matter in the form of 5 basic elements: the Panch Tattva: air, earth, fire, sky and water. According to them, everything, living or non-living, was made up of these 5 basic elements. Ancient Greek philosophers had arrived at a similar classification of matter. Modern-day scientists have evolved 2 types of classification of matter based on their physical properties and chemical nature. In this chapter we shall learn about matter based on its physical properties. Chemical aspects of matter will be taken up in subsequent chapters. 1.1 Physical nature of matter. 1.1.1 Matter is made up of particles. For a long time, 2 schools of thought prevailed regarding the nature of matter. One school believed matter to be continuous like a block of wood, whereas the other thought that matter was made up of particles like sand. Let us perform an activity to decide about the nature of matter. Is it continuous or particulate? Activity 1.1 Middle. Take a 100 ml beaker. Middle. Fill half the beaker with water and mark the level of water. Middle. Dissolve some salt sugar with the help of a glass rod. Middle. Observe any change in water level. Middle. What do you think has happened to the salt? Middle. Where does it disappear? Middle. Does the level of water change? In order to answer these questions we need to use the idea that matter is made up of particles. What was there in the spoon, salt or sugar, has now spread throughout water. This is illustrated in figure 1.1. 1.1.2 How small are these particles of matter? Activity 1.2 Middle. Take 2-3 crystals of potassium permanganate and dissolve them in 100 ml of water. Figure 1.1 When we dissolve salt in water, the particles of salt get into the spaces between particles of water. The C unit of mass is kilograms. The C unit of volume is cubic meter and 3. The common unit of measuring volume is liter L, such that 1 liter 1 dm 3, 1 liter 1000 ml, 1 milliliter 1 centimeters 3. 1 meter mm matter surroundings chapter. SCIENCE2 Middle. Take out approximately 10 ml of this solution and put it into 90 ml of clear water. Middle. Take out 10 ml of this solution and put it into another 90 ml of clear water. Middle. Keep diluting the solution like this 5 to 8 times. Middle dot is the water still colored 1.2.2 particles of matter are continuously moving. Activity 1.3 Middle dot put an unlit incense stick in a corner of your class. How close do you have to go near it so as to get its smell? Middle dot now light the incense stick. What happens? Do you get the smell sitting at a distance? Middle dot record your observations. Activity 1.4 Middle dot take 2 glasses beakers filled with water. Middle dot put a drop of blue or red ink slowly and carefully along the sides of the first beaker and honey in the same way in the second beaker. Middle dot leave them undisturbed in your house or in a corner of the class. Middle dot record your observations. Middle dot what do you observe immediately after adding the ink drop? Middle dot what do you observe immediately after adding a drop of honey? Middle dot how many hours or days does it take for the color of ink to spread evenly throughout the water? Activity 1.5 Middle dot drop a crystal of copper sulfate or potassium permanganate into a glass of hot water and another containing cold water. Do not stir the solution. Allow the crystals to settle at the bottom. Middle dot what do you observe just above the solid crystal in the glass? Middle dot what happens as time passes? Middle dot what does this suggest about the particles of solid and liquid? Middle dot does the rate of mixing change with temperature? Why and how? From the above 3 activities 1.3, 1.4 and 1.5, we can conclude the following. Figure 1.2, estimating how small are the particles of matter. With every dilution, though the color becomes light, it is still visible. This experiment shows that just a few crystals of potassium permanganate can color a large volume of water about 1000 L. So we conclude that there must be millions of tiny particles in just one crystal of potassium permanganate, which keep on dividing themselves into smaller and smaller particles. The same activity can be done using 2 ml of Dettol instead of potassium permanganate. The smell can be detected even on repeated dilution. The particles of matter are very small. They are small beyond our imagination. 1.2 Characteristics of particles of matter 1.2.1 Particles of matter have space between them. In activities 1.1 and 1.2 we saw that particles of sugar, salt, Dettol, or potassium permanganate got evenly distributed in water. Similarly, when we make tea, coffee or lemonade nimbupaini, particles of one type of matter get into the spaces between particles of the other. This shows that there is enough space between particles of matter. Matter in our surroundings 3 Middle dot if we consider each student as a particle of matter, then in which group the particles held each other with the maximum force? Activity 1.7 Middle dot take an iron nail, a piece of chalk and a rubber band. Middle dot try breaking them by hammering, cutting or stretching. Middle dot in which of the above 3 substances do you think the particles are held together with greater force? Activity 1.8 Middle dot take some water in a container. Try cutting the surface of water with your fingers. Middle dot were you able to cut the surface of water? Middle dot what could be the reason behind the surface of water remaining together? The above 3 activities 1.6, 1.7 and 1.8 suggest that particles of matter have force acting between them. This force keeps the particles together. The strength of this force of attraction varies from one kind of matter to another. Questions 1. Which of the following are matter? Chair, air, love, smell, hate, almonds, thought, cold, lemon water, smell of perfume. 2. Give reasons for the following observation. The smell of hot sizzling food reaches you several meters away, but to get the smell from cold food you have to go close. 3. A diver is able to cut through water in a swimming pool. Which property of matter does this observation show? 4. What are the characteristics of the particles of matter? Particles of matter are continuously moving, that is, they possess what we call the kinetic energy. As the temperature rises, particles move faster. So, we can say that with increase in temperature the kinetic energy of the particles also increases. In the above three activities we observe that particles of matter intermix on their own with each other. They do so by getting into the spaces between the particles. This intermixing of particles of two different types of matter on their own is called diffusion. We also observe that on heating, diffusion becomes faster. Why does this happen? 1.2.3 Particles of matter attract each other. Activity 1.6 Middle. Play this game in the field. Make 4 groups and form human chains as suggested. Middle. The first group should hold each other from the back and lock arms like I do Mishmi dancer's figure. 1.3 Figure 1.3 Middle. The second group should hold hands to form a human chain. Middle. The third group should form a chain by touching each other with only their fingertips. Middle. Now, the fourth group of students should run around and try to break the 3 human chains one by one into as many small groups as possible. Middle. Which group was the easiest to break? YQ. SCIENCE 1.3 States of matter. Observe different types of matter around you. What are its different states? We can see that matter around us exists in 3 different states: solid, liquid and gas. These states of matter arise due to the variation in the characteristics of the particles of matter. Now, let us study about the properties of these 3 states of matter in detail. 1.3.1 The solid state. Activity 1.9 Middle. Collect the following articles: a pen, a book, a needle and a piece of wooden stick. Middle. Sketch the shape of the above articles in your notebook by moving a pencil around them. Middle. Do all these have a definite shape? Distinct boundaries and a fixed volume. Middle. What happens if they are hammered, pulled or dropped? Middle. Are these capable of diffusing into each other? Middle. Try compressing them by applying force. Are you able to compress them? All the above are examples of solids. We can observe that all these have a definite shape, distinct boundaries and fixed volumes, that is, have negligible compressibility. Solids have a tendency to maintain their shape when subjected to outside force. Solids may break under force, but it is difficult to change their shape, so they are rigid. Consider the following. A. What about a rubber band? Can it change its shape on stretching? Is it a solid? B. What about sugar and salt? When kept in different jars, these take the shape of the jar. Are they solid? C. What about a sponge? It is a solid, yet we are able to compress it. Why all the above are solids? As Middle. A rubber band changes shape under force and regains the same shape when the force is removed. If excessive force is applied, it breaks. Middle. The shape of each individual sugar or salt crystal remains fixed, whether we take it in our hand, put it in a plate or in a jar. Middle. A sponge has minute holes, in which air is trapped. When we press it, the air is expelled out and we are able to compress it. 1.3.2 The liquid state. Activity 1.10 Middle. Collect the following: a water, cooking oil, milk, juice, a cold drink. B. Containers of different shapes. Put a 50 ml mark on these containers using a measuring cylinder from the laboratory. Middle. What will happen if these liquids are spilled on the floor? Middle. Measure 50 ml of any one liquid and transfer it into different containers one by one. Does the volume remain the same? Middle. Does the shape of the liquid remain the same? Middle. When you pour the liquid from one container into another, does it flow easily? We observe that liquids have no fixed shape but have a fixed volume. They take up the shape of the container in which they are kept. Liquids flow and change shape, so they are not rigid but can be called fluid. Refer to activities 1.4 and 1.5 where we saw that solids and liquids can diffuse into liquids. The gases from the atmosphere diffuse and dissolve in water. These gases, especially oxygen and carbon dioxide, are essential for the survival of aquatic animals and plants. All living creatures need to breathe for survival. The aquatic animals can breathe underwater due to the presence of dissolved oxygen in water. Thus, we may conclude that solids, liquids and gases can diffuse into liquids. The rate of diffusion of liquids is matter in our surroundings 5 higher than that of solids. This is due to the fact that in the liquid state, particles move freely and have greater space between each other as compared to particles in the solid state. 1.3.3 The gaseous state. Have you ever observed a balloon seller filling a large number of balloons from a single cylinder of gas? Inquire from him how many balloons is he able to fill from one cylinder. Ask him which gas does he have in the cylinder. Activity 1.11 Middle. Take 3 100 ml syringes and close their nozzles by rubber corks, as shown in Fig. 1.4. Middle. Remove the pistons from all the syringes. Middle. Leaving one syringe untouched, fill water in the second and pieces of chalk in the third. Middle. Insert the pistons back into the syringes. You may apply some Vaseline on the pistons before inserting them into the syringes for their smooth movement. Middle. Now, try to compress the content by pushing the piston in each syringe. We have observed that gases are highly compressible as compared to solids and liquids. The liquefied petroleum gas LPG cylinder that we get in our home for cooking or the oxygen supplied to hospitals in cylinders is compressed gas. Compressed natural gas CNG is used as fuel these days in vehicles. Due to its high compressibility, large volumes of a gas can be compressed into a small cylinder and transported easily. We come to know of what is being cooked in the kitchen without even entering there, by the smell that reaches our nostrils. How does this smell reach us? The particles of the aroma of food mix with the particles of air spread from the kitchen, reach us and even farther away. The smell of hot-cooked food reaches us in seconds. Compare this with the rate of diffusion of solids and liquids. Due to high speed of particles and large space between them, gases show the property of diffusing very fast into other gases. In the gaseous state, the particles move about randomly at high speed. Due to this random movement, the particles hit each other and also the walls of the container. The pressure exerted by the gas is because of this force exerted by gas particles per unit area on the walls of the container. Figure 1.4 Middle. What do you observe? In which case was the piston easily pushed in middle? What do you infer from your observations? SCIENCE 61.4.1 Effective change of temperature. Activity 1.12 Middle. Take about 150 grams of ice in a beaker and suspend a laboratory thermometer so that its bulb is in contact with the ice. As in Figure 1.6. Questions 1. The mass per unit volume of a substance is called density. Density, mass, volume. Arrange the following in order of increasing density: air, exhaust from chimneys, honey, water, chalk, cotton and iron. 2. Tabulate the differences in the characteristics of states of matter. B. Comment upon the following: rigidity, compressibility, fluidity, filling a gas container, shape, kinetic energy and density. 3. Give reasons a gas fills completely the vessel in which it is kept. B. A gas exerts pressure on the walls of the container. C. A wooden table should be called a solid. D. We can easily move our hand in air, but to do the same through a solid block of wood we need a karate expert. 4. Liquids generally have lower density as compared to solids. But you must have observed that ice floats on water. Find out why. 1.4 Can matter change its state? We all know from our observation that water can exist in 3 states of matter: middle. Solid, as ice, middle. Liquid, as the familiar water, and middle. Gas, as water vapor. What happens inside the matter during this change of state? What happens to the particles of matter during the change of states? How does this change of state take place? We need answers to these questions. Isn't it Q a B figure? 1.6 A conversion of ice to water, B. Conversion of water to water vapor. Matter in our surroundings. 7 Middle. Start heating the beaker on a low flame. Middle. Note the temperature when the ice starts melting. Middle. Note the temperature when all the ice has converted into water. Middle dot record your observations for this conversion of solid to liquid state. Middle dot now, put a glass rod in the beaker and heat while stirring till the water starts boiling. Middle dot keep a careful eye on the thermometer reading till most of the water has vaporized. Middle dot record your observations for the conversion of water in the liquid state to the gaseous state. On increasing the temperature of solids, the kinetic energy of the particles increases. Due to the increase in kinetic energy, the particles start vibrating with greater speed. The energy supplied by heat overcomes the forces of attraction between the particles. The particles leave their fixed positions and start moving more freely. A stage is reached when a solid melts and is converted to a liquid. The minimum temperature at which a solid melts to become a liquid at the atmospheric pressure is called its melting point. The melting point of a solid is an indication of the strength of the force of attraction between its particles. The melting point of ice is 273.15 K. The process of melting, that is, change of solid state into liquid state, is also known as fusion. When a solid melts, its temperature remains the same, so where does the heat energy go? You must have observed during the experiment of melting, that the temperature of the system does not change after the melting point is reached, till all the ice melts. This happens even though we continue to heat the beaker, that is, we continue to supply heat. This heat gets used up in changing the state by overcoming the forces of attraction between the particles. As this heat energy is absorbed by ice without showing any rise in temperature, it is considered that it gets hidden into the contents of the beaker and is known as the latent heat. The word latent means hidden. The amount of heat energy that is required to change 1 kilogram of a solid into liquid at atmospheric pressure at its melting point is known as the latent heat of fusion. So, particles in water at 00 C 273 K have more energy as compared to particles in ice at the same temperature. When we supply heat energy to water, particles start moving even faster. At a certain temperature, a point is reached when the particles have enough energy to break free from the forces of attraction of each other. At this temperature, the liquid starts changing into gas. The temperature at which a liquid starts boiling at the atmospheric pressure is known as its boiling point. Boiling is a bulk phenomenon. Particles from the bulk of the liquid gain enough energy to change into the vapor state. For water, this temperature is 373 K 100 0 C 273 100 373 K. Can you define the latent heat of vaporization? Do it in the same way as we have defined the latent heat of fusion. Particles in steam, that is, water vapor at 373 K 1000 C have more energy than water at the same temperature. This is because particles in steam have absorbed extra energy in the form of latent heat of vaporization. Note: Kelvin is the C unit of temperature, 00 C 273.15 K. For convenience, we take 00 C 273 K after rounding off the decimal. To change a temperature on the Kelvin scale to the Celsius scale, you have to subtract 273 from the given temperature. And to convert a temperature on the Celsius scale to the Kelvin scale, you have to add 273 to the given temperature. So, we infer that the state of matter can be changed into another state by changing the temperature. We have learned that substances around us change state from solid to liquid and from liquid to gas on application of heat. But there NCERT enclosed in a cylinder, will the particles come closer? Do you think that increasing or decreasing the pressure can change the state of matter? Are some that change directly from solid state to gaseous state and vice versa without changing into the liquid state? Activity 1.13 Middle dot take some camphor or ammonium chloride. Crush it and put it in a china dish. Middle dot put an inverted funnel over the china dish. Middle dot put a cotton plug on the stem of the funnel, as shown in figure 1.7. Atmosphere ATM is a unit of measuring pressure exerted by a gas. The unit of pressure is Pascal Pa, 1 atmosphere 1.01 times 105 Pennsylvania. The pressure of air in atmosphere is called atmospheric pressure. The atmospheric pressure at sea level is 1 atmosphere, and is taken as the normal atmospheric pressure. Figure 1.7, Sublimation of ammonium chloride. Figure 1.8, by applying pressure, particles of matter can be brought close together. Applying pressure and reducing temperature can liquefy gases. Have you heard of solid carbon dioxide CO2? It is stored under high pressure. Solid CO2 gets converted directly to gaseous state on decrease of pressure to 1 atmosphere without coming into liquid state. This is the reason that solid carbon dioxide is also known as dry ice. Thus, we can say that pressure and temperature determine the state of a substance, whether it will be solid, liquid or gas. Now, heat slowly and observe. What do you infer from the above activity? A change of state directly from solid to gas without changing into liquid state is called sublimation, and the direct change of gas to solid without changing into liquid is called deposition. 1.4.2 Effect of change of pressure. We have already learned that the difference in various states of matter is due to the difference in the distances between the constituent particles. What will happen when we start putting pressure and compress a gas? Figure 1.9, Interconversion of the 3 states of matter. Deposition. Matter in our surroundings. 9 dish and keep it inside a cupboard or on a shelf in your class. Record the room temperature. Record the time or days taken for the evaporation process in the above cases. Repeat the above 3 steps of activity on a rainy day and record your observations. What do you infer about the effect of temperature, surface area and wind velocity speed on evaporation? You must have observed that the rate of evaporation increases with an increase of surface area. We know that evaporation is a surface phenomenon. If the surface area is increased, the rate of evaporation increases. For example, while putting clothes for drying up, we spread them out. An increase of temperature. With the increase of temperature, more number of particles get enough kinetic energy to go into the vapor state. A decrease in humidity. Humidity is the amount of water vapor present in air. The air around us cannot hold more than a definite amount of water vapor at a given temperature. If the amount of water in air is already high, the rate of evaporation decreases. An increase in wind speed. It is a common observation that clothes dry faster on a windy day. With the increase in wind speed, the particles of water vapor move away with the wind, decreasing the amount of water vapor in the surrounding. 1.5.2 How does evaporation cause cooling in an open vessel? The liquid keeps on evaporating. The particles of liquid absorb energy from the surrounding to regain the energy lost during evaporation. This absorption of energy from the surroundings make the surroundings cold. Questions 1. Convert the following temperature to Celsius scale. 300 kb. 573 K2. What is the physical state of water at 250 superscript OCB? 100 superscript OC3. For any substance. Why does the temperature remain constant during the change of state? 4. Suggest a method to liquefy atmospheric gases. 1.5 Evaporation. Do we always need to heat or change pressure for changing the state of matter? Can you quote some examples from everyday life where change of state from liquid to vapor takes place without the liquid reaching the boiling point? Water, when left uncovered, slowly changes into vapor. Wet clothes dry up. What happens to water? In the above 2 examples we know that particles of matter are always moving and are never at rest. At a given temperature in any gas, liquid or solid, there are particles with different amounts of kinetic energy. In the case of liquids, a small fraction of particles at the surface, having higher kinetic energy, is able to break away from the forces of attraction of other particles and gets converted into vapor. This phenomenon of change of a liquid into vapors at any temperature below its boiling point is called evaporation. 1.5.1 Factors affecting evaporation. Let us understand this with an activity. Activity 1.14 Middle. Take 5 ml of water in a test tube and keep it near a window or under a fan. Middle. Take 5 ml of water in an open china dish and keep it near a window or under a fan. Middle. Take 5 ml of water in an open china Q. SCIENCE10 What happens when you pour some acetone nail polish remover on your palm? The particles gain energy from your palm or surroundings and evaporate, causing the palm to feel cool. After a hot sunny day, people sprinkle water on the roof or open ground because the large latent heat of vaporization of water helps to cool the hot surface. Can you cite some more examples from daily life where we can feel the effect of cooling due to evaporation? Why should we wear cotton clothes in summer? During summer, we perspire more because of the mechanism of our body which keeps us cool. We know that during evaporation, the particles at the surface of the liquid gain energy from the surroundings or body surface and change into vapor. The heat energy equal to the latent heat of vaporization is absorbed from the body, leaving the body cool. Cotton, being a good absorber of water, helps in absorbing the sweat and exposing it to the atmosphere for easy evaporation. Why do we see water droplets on the outer surface of a glass containing ice-cold water? Let us take some ice-cold water in a tumbler. Soon we will see water droplets on the outer surface of the tumbler. The water vapor present in air, on coming in contact with the cold glass of water, loses energy and gets converted to liquid state, which we see as water droplets. Questions 1. Why does a desert cooler cool better on a hot dry day? 2. How does the water kept in an earthen pot matka become cool during summer? 3. Why does our palm feel cold when we put some acetone or petrol or perfume on it? 4. Why are we able to sip hot tea or milk faster from a saucer rather than a cup? 5. What type of clothes should we wear in summer? More to know. Now scientists are talking of 5 states of matter: solid, liquid, gas, plasma and Bose-Einstein condensate. Plasma, the state consists of superenergetic and superexcited particles. These particles are in the form of ionized gases. The fluorescent tube and neon sign bulbs consist of plasma. Inside a neon sign bulb there is neon gas, and inside a fluorescent tube there is helium gas or some other gas. The gas gets ionized, that is, gets charged when electrical energy flows through it. This charging up creates a plasma glowing inside the tube or bulb. The plasma glows with a special color depending on the nature of gas. The sun and the stars glow because of the presence of plasma in them. The plasma is created in stars because of very high temperature. Bose-Einstein condensate. In 1920, Indian physicist Satyendranath Bose had done some calculations for a 5th state of matter. Building on his calculations, Albert Einstein predicted a new state of matter, the Bose-Einstein condensate Beck. In 2001, Eric A. Cornell, Wolfgang Ketterl and Carly Wieman of USA received the Nobel Prize in Physics for achieving Bose-Einstein condensation. The Beck is formed by cooling a gas of extremely low density, about 100,000th the density of normal air, to super low temperatures. You can log on to www.chem4kids.com to get more information on these 4th and 5th states of matter. QSN Bose 1894-1974, Albert Einstein 1879-1955. Matter in our surroundings. 11. What you have learned. Middle. Matter is made up of small particles. Middle. The matter around us exists in 3 states: solid, liquid and gas. Middle. The forces of attraction between the particles are maximum in solids, intermediate in liquids and minimum in gases. Middle. The spaces in between the constituent particles and kinetic energy of the particles are minimum in the case of solids, intermediate in liquids and maximum in gases. The arrangement of particles is most ordered in the case of solids. In the case of liquids, layers of particles can slip and slide over each other, while for gases, there is no order, particles just move about randomly. The states of matter are interconvertible. The state of matter can be changed by changing temperature or pressure. Sublimation is a change of solid state directly to gaseous state without going through liquid state. Deposition is a change of gaseous state directly to solid state without going through liquid state. Boiling is a bulk phenomenon. Particles from the bulk hole of the liquid change into vapor state. Evaporation is a surface phenomenon. Particles from the surface gain enough energy to overcome the forces of attraction present in the liquid and change into the vapor state. The rate of evaporation depends upon the surface area exposed to the atmosphere, the temperature, the humidity and the wind speed. Evaporation causes cooling. Latent heat of vaporization is the heat energy required to change 1 kilogram of a liquid to gas at atmospheric pressure at its boiling point. Latent heat of fusion is the amount of heat energy required to change 1 kilogram of solid into liquid at its melting point. SCIE 12 Exercises 1. Convert the following temperatures to the Celsius scale. A 293 kb 470 K. 2. Convert the following temperatures to the Kelvin scale. A 25 degrees Celsius B 373 degrees Celsius. 3. Give reason for the following observations. A. Naphthalene balls disappear with time without leaving any solid. B. We can get the smell of perfume sitting several meters away. 4. Arrange the following substances in increasing order of forces of attraction between the particles: water, sugar, oxygen. 5. What is the physical state of water at a 25 degrees Celsius B 0 degrees Celsius C 100 degrees Celsius? 6. Give 2 reasons to justify a water at room temperature is a liquid. B. An iron almirah is a solid at room temperature. 7. Why is ice at 273 K more effective in cooling than water at the same temperature? 8. What produces more severe burns, boiling water or steam? 9. Name A, B, C, D, E and F in the following diagram showing change in its state: quantity unit symbol temperature Kelvin, K length meter, M mass kilogram, kilograms weight Newton, N volume cubic meter, M3 density kilogram per cubic meter, kilograms, M3 pressure Pascal per middle. Some measurable quantities and their units to remember. Matter in our surroundings. 13. Group activity. Prepare a model to demonstrate movement of particles in solids, liquids and gases. For making this model you will need a transparent jar, a big rubber balloon or piece of stretchable rubber sheet, a string, few chickpeas or black gram or dry green peas. How to make put the seeds in the jar. Sew the string to the center of the rubber sheet and put some tape to keep it tied securely. Stretch and tie the rubber sheet on the mouth of the jar. Your model is ready. Now run your fingers up and down the string by first tugging at it slowly and then rapidly. Figure 1.10, a model for converting of solid to liquid and liquid to gas. Figure 2.1, some consumable items. Have you ever noticed the word pure written on the packs of these consumables? For a common person, pure means having no adulteration. But, for a scientist, all these things are actually mixtures of different substances and hence not pure. For example, milk is actually a mixture of water, fat, proteins, etc. When a scientist says that something is pure, it means that all the constituent particles of that substance are the same in their chemical nature. A pure substance consists of a single type of particles. In other words, a substance is a pure single form of matter. As we look around, we can see that most of the matter around us exists as mixtures of two or more pure components, for example, seawater, minerals, soil, etc. Are all mixtures. 2.1 What is a mixture? Mixtures are constituted by more than one kind of pure form of matter. We know that dissolved sodium chloride can be separated from water by the physical process of evaporation. However, sodium chloride is itself a pure substance and cannot be separated by physical process into its chemical constituents. Similarly, sugar is a substance which contains only one kind of pure matter and its composition is the same throughout. Soft drink and soil are not single pure substances. Whatever the source of a pure substance may be, it will always have the same characteristic properties. Therefore, we can say that a mixture contains more than one pure substance. 2.1.1 Types of mixtures. Depending upon the nature of the components that form a mixture, we can have different types of mixtures. Activity 2.1 Middle. Let us divide the class into groups A, B, C and D. Middle. Group A takes a beaker containing 50 ml of water and one spatula full of copper sulfate powder. Group B takes 50 ml of water and 2 spatula full of copper sulfate powder in a beaker. Middle. Groups C and D can take different amounts of copper sulfate and potassium permanganate or common salt sodium chloride and mix the given components to form a mixture. Middle. Report the observations on the uniformity in color and texture. Middle. Groups A and B have obtained a mixture which has a uniform composition throughout. Such mixtures are called homogeneous mixtures or solutions. Some other examples of such mixtures are, I salt dissolved in water and 2 sugar. How do we judge whether milk, ghee, butter, salt, spices, mineral water or juice that we buy from the market are pure? 2 2 ice matter round pure. Chapter. More to know. Dissolved in water. Compare the color of the solutions of the two groups. Though both the groups have obtained copper sulfate solution, but the intensity of color of the solutions is different. This shows that a homogeneous mixture can have a variable composition. Middle. Groups C and D have obtained mixtures, which contain physically distinct parts and have non-uniform compositions. Such mixtures are called heterogeneous mixtures. Mixtures of sodium chloride and iron filings, salt and sulfur, and oil and water are examples of heterogeneous mixtures. Activity 2.2 Middle. Let us again divide the class into 4 groups A, B, C and D. Middle. Distribute the following samples to each group. Few crystals of copper sulfate to Group A. 1 spatula full of copper sulfate to Group B. Chalk powder or wheat flour to Group C. Few drops of milk or ink to Group D. Middle. Each group should add the given sample in water and stir properly using a glass rod. Are the particles in the mixture visible? Middle. Direct a beam of light from a torch through the beaker containing the mixture and observe from the front. Was the path of the beam of light visible? Middle. Leave the mixtures undisturbed for a few minutes and set up the filtration apparatus in the meantime. Is the mixture stable or do the particles begin to settle after some time? Middle. Filter the mixture. Is there any residue on the filter paper? Discuss the results and form an opinion. Middle. Groups A and B have got a solution. Middle. Group C has got a suspension. Middle. Group D has got a colloidal solution. Now, we shall learn about solutions, suspensions and colloidal solutions in the following sections. Questions 1. What is meant by a substance? 2. List the points of differences between homogeneous and heterogeneous mixtures. 2.2 What is a solution? A solution is a homogeneous mixture of 2 or more substances. You come across various types of solutions in your daily life. Lemonade, soda water etc. are all examples of solutions. Usually we think of a solution as a liquid that contains either a solid, liquid or a gas dissolved in it. But, we can also have solid solutions, alloys and gaseous solutions air. In a solution there is homogeneity at the particle level. For example, lemonade tastes the same throughout. This shows that particles of sugar or salt are evenly distributed in the solution. Q Figure 2.2, Filtration alloys. Alloys are mixtures of two or more metals or a metal and a non-metal and cannot be separated into their components by physical methods. But still, an alloy is considered as a mixture because it shows the properties of its constituents and can have variable composition. For example, brass is a mixture of approximately 30 zinc and 70 copper. Is matter around us pure? 15. NCERT. A solution has a solvent and a solute as its components. The component of the solution that dissolves the other component in it, usually the component present in larger amount, is called the solvent. The component of the solution that is dissolved in the solvent, usually present in lesser quantity, is called the solute. Examples: a solution of sugar in water is a solid and liquid solution. In this solution, sugar is the solute and water is the solvent. 2. A solution of iodine in alcohol, known as tincture of iodine, has iodine solid as the solute and alcohol liquid as the solvent. 3. Aerated drinks like soda water etc. are gas and liquid solutions. These contain carbon dioxide gas as solute and water liquid as solvent. Air is a mixture of gas and gas. Air is a homogeneous mixture of a number of gases. Its two main constituents are oxygen 21 and nitrogen 78. The other gases are present in very small quantities. Properties of a solution. A solution is a homogeneous mixture. The particles of a solution are smaller than 1 nm 9 meter in diameter. So, they cannot be seen by naked eyes. Because of very small particle size, they do not scatter a beam of light passing through the solution. So, the path of light is not visible in a solution. The solute particles cannot be separated from the mixture by the process of filtration. The solute particles do not settle down when left undisturbed, that is, a solution is stable. 2.2.1 Concentration of a solution. In Activity 2.2, we observed that groups A and B obtained different shades of solutions. So, we understand that in a solution the relative proportion of the solute and solvent can be varied. Depending upon the amount of solute present in a solution, it can be called a dilute, concentrated or a saturated solution. Dilute and concentrated are comparative terms. In Activity 2.2, the solution obtained by Group A is dilute as compared to that obtained by Group B. Activity 2.3 Take approximately 50 ml of water each in two separate beakers. Add salt in one beaker and sugar or barium chloride in the second beaker with continuous stirring. When no more solute can be dissolved, heat the contents of the beaker to raise the temperature by about 5 degrees Celsius. Start adding the solute again. Is the amount of salt and sugar or barium chloride that can be dissolved in water at a given temperature, the same at any particular temperature. A solution that has dissolved as much solute as it is capable of dissolving is said to be a saturated solution. In other words, when no more solute can be dissolved in a solution at a given temperature, it is called a saturated solution. The amount of the solute present in the saturated solution at this temperature is called its solubility. If the amount of solute contained in a solution is less than the saturation level, it is called an unsaturated solution. What would happen if you were to take a saturated solution at a certain temperature and cool it slowly? We can infer from the above activity that different substances in a given solvent have different solubilities at the same temperature. The concentration of a solution is the amount mass or volume of solute present in a given amount mass or volume of solution. There are various ways of expressing the concentration of a solution, but here we will learn only 3 methods. I mass by mass percentage of a solution, mass of solute times 100 mass of solution. 2 mass by volume percentage of a solution, mass of solute times 100 volume of solution. 3 volume by volume percentage of a solution, volume of solute times 100 volume of solution. Example 2.1 A solution contains 40 grams of common salt and 320 grams of water. Calculate the concentration in terms of mass by mass percentage of the solution. Solution, mass of solute salt 40 grams, mass of solvent water 320 grams. We know mass of solution, mass of solute, mass of solvent 40 grams, 320 grams, 360 grams. Mass percentage of solution, mass of solute times 100, mass of solution 40 times 100. 11.1 362.2.2 What is a suspension? Non-homogeneous systems, like those obtained by Group C in Activity 2.2, in which solids are dispersed in liquids, are called suspensions. A suspension is a heterogeneous mixture in which the solute particles do not dissolve but remain suspended throughout the bulk of the medium. Particles of a suspension are visible to the naked eye. Properties of a suspension. Suspension is a heterogeneous mixture. The particles of a suspension can be seen by the naked eye. The particles of a suspension scatter a beam of light passing through it and make its path visible. The solute particles settle down when a suspension is left undisturbed, that is, a suspension is unstable. They can be separated from the mixture by the process of filtration. When the particles settle down, the suspension breaks and it does not scatter light anymore. 2.2.3 What is a colloidal solution? The mixture obtained by Group D in Activity 2.2 is called a colloid or a colloidal solution. The particles of a colloid are uniformly spread throughout the solution. Due to the relatively smaller size of particles, as compared to that of a suspension, the mixture appears to be homogeneous. But actually, a colloidal solution is a heterogeneous mixture, for example, milk. Because of the small size of colloidal particles, we cannot see them with naked eyes. But, these particles can easily scatter a beam of visible light as observed in Activity 2.2. This scattering of a beam of light is called the Tyndall effect after the name of the scientist who discovered this effect. Tyndall effect can also be observed when a fine beam of light enters a room through a small hole. This happens due to the scattering of light by the particles of dust and smoke in the air. Figure 2.3, a solution of copper sulfate does not show Tyndall effect. B mixture of water and milk shows Tyndall effect. A B. Q They cannot be separated from the mixture by the process of filtration. But, a special technique of separation known as centrifugation perform Activity 2.5, can be used to separate the colloidal particles. The components of a colloidal solution are the dispersed phase and the dispersion medium. The solute-like component or the dispersed particles in a colloid form the dispersed phase, and the component in which the dispersed phase is suspended is known as the dispersing medium. Colloids are classified according to the state solid, liquid or gas of the dispersing medium and the dispersed phase. A few common examples are given in Table 2.1. From this table you can see that they are very common everyday life. Questions 1. Differentiate between homogeneous and heterogeneous mixtures with examples. 2. How are solution and suspension different from each other? 3. To make a saturated solution, 36 grams of sodium chloride is dissolved in 100 grams of water at 293 K. Find its concentration at this temperature. Tyndall effect can be observed when sunlight passes through the canopy of a dense forest. In the forest, mist contains tiny droplets of water, which act as particles of colloid dispersed in air. Figure 2.4, the Tyndall effect properties of a colloid. A colloid is a heterogeneous mixture. Middle dot. The size of particles of a colloid is too small to be individually seen by naked eyes. Middle dot. Colloids are big enough to scatter a beam of light passing through it and make its path visible. Middle dot. They do not settle down when left undisturbed, that is, a colloid is quite stable. Table 2.1. Common examples of colloids: dispersed, dispersing type. Example: phase, medium, liquid, gas, aerosol, fog. Clouds, mist, solid gas, aerosol, smoke, automobile exhaust gas, liquid, foam, shaving cream, liquid, liquid, emulsion, milk. Face, cream, solid, liquid, sole, milk of magnesia, mud, gas, solid, foam, foam, rubber, sponge, pumice, liquid, solid, gel, jelly. Cheese, butter, solid, 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 soul-colored gemstone, milky glass. Is matter around us pure? 19. 2.3 Separating the components of a mixture. We have learned that most of the natural substances are not chemically pure. Different methods of separation are used to get individual components from a mixture. Separation makes it possible to study and use the individual components of a mixture. Heterogeneous mixtures can be separated into their respective constituents by simple physical methods like handpicking, sieving, filtration that we use in our day-to-day life. Sometimes special techniques have to be used for the separation of the components of a mixture. 2.3.1 How can we obtain colored component dye from blue-black ink? Activity 2.4 Middle dot. Fill half a beaker with water. Middle dot. Put a watch glass on the mouth of the beaker. Figure 2.5. Middle dot. Put few drops of ink on the watch glass. Middle dot. Now start heating the beaker. We do not want to heat the ink directly. You will see that evaporation is taking place from the watch glass. Middle dot. Continue heating as the evaporation goes on and stop heating when you do not see any further change on the watch glass. Middle dot. Observe carefully and record your observations. Now answer. Middle dot. What do you think has got evaporated from the watch glass? Middle dot. Is there a residue on the watch glass? Middle dot. What is your interpretation? Is ink a single substance pure, or is it a mixture? We find that ink is a mixture of a dye and water. Thus, we can separate the volatile component solvent from its non-volatile solute by the method of evaporation. 2.3.2 How can we separate cream from milk? Nowadays, we get full cream, toned and double-toned varieties of milk packed in poly packs or Tetra packs in the market. These varieties of milk contain different amounts of fat. Activity 2.5 Middle dot. Take some full cream milk in a test tube. Middle dot. Centrifuge it by using a centrifuging machine for 2 minutes. If a centrifuging machine is not available in the school, you can do this activity at home by using a milk churner, used in the kitchen. Middle dot. If you have a milk dairy nearby, visit it and ask how they separate cream from milk and how they make cheese paneer from milk. Now answer. Middle dot. What do you observe on churning the milk? Middle dot. Explain how the separation of cream from milk takes place. Sometimes the solid particles in a liquid are very small and pass through a filter paper. For such particles, the filtration technique cannot be used for separation. Such mixture SCIE and CE20 are separated by centrifugation. The principle is that the denser particles are forced to the bottom and the lighter particles stay at the top when spun rapidly. Applications. Middle dot. Used in diagnostic laboratories for blood and urine tests. Middle dot. Used in dairies and home to separate butter from cream. Middle dot. Used in washing machines to squeeze out water from wet clothes. 2.3.3 How can we separate a mixture of two immiscible liquids? Activity 2.6 Middle dot. Let us try to separate kerosene oil from water using a separating funnel. Middle dot. Pour the mixture of kerosene oil and water in a separating funnel. Figure 2.6. Middle dot. Let it stand undisturbed for some time so that separate layers of oil and water are formed. Middle dot. Open the stopcock of the separating funnel and pour out the lower layer of water carefully. Middle dot. Close the stopcock of the separating funnel as the oil reaches the stopcock. Applications. Middle dot. To separate mixture of oil and water. Middle dot. In the extraction of iron from its ore, the lighter slag is removed from the top by this method to leave the molten iron at the bottom in the furnace. The principle is that immiscible liquids separate out in layers depending on their densities. 2.3.4 How can we separate a mixture of salt and camphor? We have learned in Chapter 1 that camphor changes directly from solid to gaseous state on heating. So, to separate such mixtures that contain a sublimable volatile component from a non-sublimable impurity, the sublimation process is used in Figure 2.7. Some examples of solids which sublime are ammonium chloride, naphthalene and anthracene. Figure 2.7, Separation of camphor and salt by sublimation. Fig. 2.6, Separation of immiscible liquids. Is matter around US pure? 21. 2.3.5 Is a dye in black ink a single color activity? 2.7 Middle dot. Take a thin strip of filter paper. Middle dot. Draw a line on it using a pencil, approximately 3 centimeters above the lower edge. Figure 2.8a. Middle dot. Put a small drop of ink, water soluble, that is, from a sketch pen or fountain pen, at the center of the line. Let it dry. Middle dot. Lower the filter paper into a jar glass beaker test tube containing water so that the drop of ink on the paper is just above the water level, as shown in Figure 2.8b, and leave it undisturbed. Middle dot. Watch carefully as the water rises up on the filter paper. Record your observations. This process of separation of components of a mixture is known as chromatography. Chroma in Greek means color. This technique was first used for separation of colors, so this name was given. Chromatography is the technique used for separation of those solutes that dissolve in the same solvent. With the advancement in technology, newer techniques of chromatography have been developed. You will study about chromatography in higher classes. Applications to separate middle dot colors in a dye. Middle dot. Pigments from natural colors. Middle dot. Drugs from blood. 2.3.6 How can we separate a mixture of two miscible liquids? Activity 2.8 Middle dot. Let us try to separate acetone and water from their mixture. Middle dot. Take the mixture in a distillation flask. Fit it with a thermometer. Middle dot. Arrange the apparatus as shown in Figure 2.9. Middle dot. Heat the mixture slowly, keeping a close watch at the thermometer. Middle dot. The acetone vaporizes, condenses in the condenser, and can be collected from the condenser outlet. Middle dot. Water is left behind in the distillation flask. Figure 2.8, Separation of dyes in black ink using chromatography. Now answer. Middle dot. What do you observe on the filter paper as the water rises on it? Middle dot. Do you obtain different colors on the filter paper strip? Middle dot. What, according to you, can be the reason for the rise of the colored spot on the paper strip? The ink that we use has water as the solvent and the dye is soluble in it. As the water rises on the filter paper, it takes along with it the dye particles. Usually, a dye is a mixture of two or more colors. The colored component that is more soluble in water rises faster, and in this way the colors get separated. Fig. 2.9, Separation of two miscible liquids by distillation. SCIENCE 22 Now answer. Middle dot. What do you observe as you start heating the mixture? Middle dot. At what temperature does a thermometer reading become constant for some time? Middle dot. What is the boiling point of acetone? Middle dot. Why do the two components separate? This method is called distillation. It is used for the separation of components of a mixture containing two miscible liquids that boil without decomposition and have sufficient difference in their boiling points. To separate a mixture of two or more miscible liquids for which the difference in boiling points is less than 25 K, fractional distillation process is used. For example, for the separation of different gases from air, different fractions from petroleum products, etc. The apparatus is similar to that for simple distillation, except that a fractionating column is fitted in between the distillation flask and the condenser. A simple fractionating column is a tube packed with glass beads. The beads provide surface for the vapors to cool and condense repeatedly, as shown in figure 2.10. 2.3.7 How can we obtain different gases from air? Air is a homogeneous mixture and can be separated into its components by fractional distillation. The flow diagram figure 2.11 shows the steps of the process. Figure 2.10, fractional distillation figure 2.11, flow diagram shows the process of obtaining gases from air. If we want oxygen gas from air, figure 2.12, we have to separate out all the other gases present in the air. The air is compressed by increasing the pressure and is then cooled by decreasing the temperature to get liquid air. This liquid air is allowed to warm up slowly in a fractional distillation column, where gases get separated at different heights depending upon their boiling points. Answer the following. Middle dot. Arrange the gases present in air in increasing order of their boiling points. Middle dot. Which gas forms the liquid first as the air is cooled? Is matter around US pure 23 it? To remove these impurities, the process of crystallization is used. Crystallization is a process that separates a pure solid in the form of its crystals from a solution. Crystallization technique is better than simple evaporation technique as middle dot. Some solids decompose or some, like sugar, may get charred on heating to dryness. Middle dot. Some impurities may remain dissolved in the solution even after filtration. On evaporation these contaminate the solid. Applications. Middle dot. Purification of salt that we get from seawater. Middle dot. Separation of crystals of alum thick airy from impure samples. Thus, by choosing one of the above methods according to the nature of the components of a mixture, we get a pure substance. With advancements in technology, many more methods of separation techniques have been devised. In cities, drinking water is supplied from waterworks. A flow diagram of a typical waterworks is shown in figure 2.13. From this figure write down the processes involved to get the supply of drinking water to your home from the waterworks and discuss it in your class. Figure 2.12, separation of components of air 2.3.8 How can we obtain pure copper sulfate from an impure sample? Activity 2.9 Middle dot. Take some approximately 5 grams impure sample of copper sulfate in a china dish. Middle dot. Dissolve it in minimum amount of water. Middle dot. Filter the impurities out. Middle dot. Evaporate water from the copper sulfate solution so as to get a saturated solution. Middle dot. Cover the solution with a filter paper and leave it undisturbed at room temperature to cool slowly for a day. Middle dot. You will obtain the crystals of copper sulfate in the china dish. Middle dot. This process is called crystallization. Now answer middle dot. What do you observe in the china dish? Middle dot. Do the crystals look alike? Middle dot. How will you separate the crystals from the liquid in the china dish? The crystallization method is used to purify solids. For example, the salt we get from seawater can have many impurities in. Questions 1. How will you separate a mixture containing kerosene and petrol? Difference in their boiling points is more than 25 superscript OC, which are miscible with each other. 2. Name the technique to separate butter from curd, 2 salt from seawater, 3 camphor from salt. 3. What type of mixtures are separated by the technique of crystallization? 2.4 Physical and chemical changes. In the previous chapter, we have learned about a few physical properties of matter. The properties that can be observed and specified like color, hardness, rigidity, fluidity, density, melting point, boiling point, etc. are the physical properties. The interconversion of states is a physical change because these changes occur without a change in composition and no change in the chemical nature of the substance. Although ice, water and water vapor all look different and display different physical properties, they are chemically the same. Both water and cooking oil are liquid, but their chemical characteristics are different. Q figure 2.13. Water purification system in waterworks. They differ in odor and inflammability. We know that oil burns in air, whereas water extinguishes fire. It is this chemical property of oil that makes it different from water. Burning is a chemical change. During this process, one substance reacts with another to undergo a change in chemical composition. Chemical change brings change in the chemical properties of matter, and we get new substances. A chemical change is also called a chemical reaction. During burning of a candle, both physical and chemical changes take place. Can you distinguish these questions? 1. Classify the following as chemical or physical changes: cutting of trees, melting of butter in a pan, rusting of almirah, boiling of water to form steam, passing of electric current through water and the water breaking down into hydrogen and oxygen gases, dissolving common salt in water, making a fruit salad with raw fruits, and burning of paper and wood. 2. Try segregating the things around you as pure substances or mixtures. Q. Is matter around you as pure? 25. 2.5. What are the types of pure substances on the basis of their chemical composition? Substances can be classified either as elements or compounds. 2.5.1 Elements. Robert Boyle was the first scientist to use the term element in 1661. Antoine Laurent Lavoisier 1743–94, a French chemist, was the first to establish an experimentally useful definition of an element. He defined an element as a basic form of matter that cannot be broken down into simpler substances by chemical reactions. Elements can be normally divided into metals, nonmetals and metalloids. Metals usually show some or all of the following properties. They have a luster shine. They have silvery gray or golden yellow color. They conduct heat and electricity. They are ductile, can be drawn into wires. They are malleable, can be hammered into thin sheets. They are sonorous, make a ringing sound when hit. Examples of metals are gold, silver, copper, iron, sodium, potassium, etc. Mercury is the only metal that is liquid at room temperature. Nonmetals usually show some or all of the following properties. They display a variety of colors. They are poor conductors of heat and electricity. They are not lustrous, sonorous or malleable. Examples of nonmetals are hydrogen, oxygen, iodine, carbon, coal, coke, bromine, chlorine, etc. Some elements have intermediate properties between those of metals and nonmetals. They are called metalloids. Examples are boron, silicon, germanium, etc. More to know. The number of elements known at present are more than 100. 92 elements are naturally occurring and the rest are man-made. Majority of the elements are solid. 11 elements are in gaseous state at room temperature. 2 elements are liquid at room temperature, mercury and bromine. Elements, gallium and caesium, become liquid at a temperature slightly above room temperature 303 K. 2.5.2 Compounds. A compound is a substance composed of two or more elements, chemically combined with one another in a fixed proportion. What do we get when two or more elements are combined? Activity 2.10 Divide the class into two groups. Give 5 grams of iron filings and 3 grams of sulfur powder in a china dish to both the groups. Group I. Mix and crush iron filings and sulfur powder. Group 2. Mix and crush iron filings and sulfur powder. Heat this mixture strongly till red hot. Remove from flame and let the mixture cool. Groups I and 2. Check for magnetism in the material obtained. Bring a magnet near the material and check if the material is attracted towards the magnet. Middle dot. Compare the texture and color of the material obtained by the groups. Middle dot. Add carbon disulfide to one part of the material obtained. Stir well and filter. Middle dot. Add dilute sulfuric acid or dilute hydrochloric acid to the other part of SCIENCE 26 the material obtained. Note: teacher's supervision is necessary for this activity. Middle dot. Perform all the above steps with both the elements iron and sulfur separately. Now answer. Middle dot. Did the material obtained by the two groups look the same? Middle dot. Which group has obtained a material with magnetic properties? Middle dot. Can we separate the components of the material obtained? Middle dot. On adding dilute sulfuric acid or dilute hydrochloric acid. Did both the groups obtain a gas? Did the gas in both the cases smell the same or different? The gas obtained by group I is hydrogen. It is colorless, odorless and combustible. It is not advised to do the combustion test for hydrogen in the class. The gas obtained by group 2 is hydrogen sulfide. It is a colorless gas with a smell of rotten eggs. You must have observed that the products obtained by both the groups show different properties, though the starting materials were the same. Group I has carried out the activity involving a physical change, whereas in case of Group 2, a chemical change, a chemical reaction has taken place. Middle dot. The material obtained by Group I is a mixture of the two substances. The substances given are the elements iron and sulfur. Middle dot. The properties of the mixture are the same as that of its constituents. Middle dot. The material obtained by Group 2 is a compound. Middle dot. On heating the two elements strongly we get a compound, which has totally different properties compared to the combining elements. Middle dot. The composition of a compound is the same throughout. We can also observe that the texture and the color of the compound are the same throughout. Thus, we can summarize the physical and chemical nature of matter in the following graphical organizer, Table 2.2, Mixtures and Compounds. Mixtures. Compounds. 1. Elements or compounds just mix. 1. Elements react to form new compounds together to form a mixture and no new compound is formed. 2. A mixture has a variable composition. 2. The composition of each new substance is always fixed. 3. A mixture shows the properties of the 3. The new substance has totally different constituent substances. Properties. 4. The constituents can be separated. 4. The constituents can be separated only fairly easily by physical methods, by chemical or electrochemical reactions. Is matter around us pure? 27. What you have learned. Middle dot. A mixture contains more than one substance, element, and or compound mixed in any proportion. Middle dot. Mixtures can be separated into pure substances using appropriate separation techniques. Middle dot. A solution is a homogeneous mixture of two or more substances. The major component of a solution is called the solvent, and the minor, the solute. Middle dot. The concentration of a solution is the amount of solute present per unit volume or per unit mass of the solution. Middle dot. Materials that are insoluble in a solvent and have particles that are visible to naked eyes form a suspension. A suspension is a heterogeneous mixture. Middle dot. Colloids are heterogeneous mixtures in which the particle size is too small to be seen with the naked eye, but is big enough to scatter light. Colloids are useful in industry and daily life. The particles are called the dispersed phase and the medium in which they are distributed is called the dispersion medium. Middle dot. Pure substances can be elements or compounds. An element is a form of matter that cannot be broken down by chemical reactions into simpler substances. A compound is a substance composed of two or more different types of elements, chemically combined in a fixed proportion. Middle dot. Properties of a compound are different from its constituent elements, whereas a mixture shows the properties of its constituting elements or compounds. SCIENCE 28 Exercises 1. Which separation techniques will you apply for the separation of the following: a sodium chloride from its solution in water? B. Ammonium chloride from a mixture containing sodium chloride and ammonium chloride. C. Small pieces of metal in the engine oil of a car. D. Different pigments from an extract of flower petals. E. Butter from curd. F. Oil from water. G. Tea leaves from tea. H. Iron pins from sand. I. Wheat grains from husk. J. Fine mud particles suspended in water. 2. Write the steps you would use for making tea. Use the words solution, solvent, solute, dissolve, soluble, insoluble, filtrate and residue. 3. Prague tested the solubility of 3 different substances at different temperatures and collected the data as given below. Results are given in the following table. As grams of substance dissolved in 100 grams of water to form a saturated solution. What mass of potassium nitrate would be needed to produce a saturated solution of potassium nitrate in 50 grams of water at 313 K? B. Prague makes a saturated solution of potassium chloride in water at 353 K and leaves the solution to cool at room temperature. What would she observe as the solution cools? Explain. C. Find the solubility of each salt at 293 K. Which salt has the highest solubility at this temperature? D. What is the effect of change of temperature on the solubility of a salt? Temperature in K. 283,293,313,333 353 Solubility potassium nitrate 21, 32, 62, 106, 167 Sodium chloride 36, 36, 36, 37 37 Potassium chloride 35, 35, 40, 46 54 Ammonium chloride 24, 37, 41, 55, 66 Substance dissolved. Is matter around you as pure? 29, 4. Explain the following giving examples. A saturated solution. B. Pure substance. C. Colloid. D. Suspension. 5. Classify each of the following as a homogeneous or heterogeneous mixture. Soda, water, wood, air, soil, vinegar, filtered tea. 6. How would you confirm that a colorless liquid given to you is pure water? 7. Which of the following materials fall in the category of a pure substance? Ice. B. Milk. C. Iron. D. Hydrochloric acid. E. Calcium oxide. F. Mercury. G. Brick. H. Wood. I. Air. 8. Identify the solutions among the following mixtures. A. Soil. B. Sea water. C. Air. D. Coal. E. Soda. Water. 9. Which of the following will show Tyndall effect? A. Salt solution. B. Milk. C. Copper sulfate solution. D. Starch solution. 10. Classify the following into elements, compounds and mixtures. A. Sodium. B. Soil. C. Sugar solution. D. Silver. E. Calcium carbonate. F. Tin. G. Silicon. SCIENCE30H. Coal. I. Air. J. Soap. K. Methane. L. Carbon dioxide. M. Blood. 11. Which of the following are chemical changes? A. Growth of a plant. B. Rusting of iron. C. Mixing of iron filings and sand. D. Cooking of food. D. Digestion of food. F. Freezing of water. G. Burning of a candle. Group activity. Take an earthen pot, mica, some pebbles and sand. Design a small-scale filtration plant that you could use to clean muddy water. Ancient Indian and Greek philosophers have always wondered about the unknown and unseen form of matter. The idea of divisibility of matter was considered long back in India, around 500 BC. An Indian philosopher, Maharishi Kanad, postulated that if we go on dividing matter padarth, we shall get smaller and smaller particles. Ultimately, a stage will come when we shall come across the smallest particles beyond which further division will not be possible. He named these particles Parmanu. Another Indian philosopher, Pakudakatyayama, elaborated this doctrine and said that these particles normally exist in a combined form which gives us various forms of matter. Around the same era, Ancient Greek philosophers Democritus and Leucippus suggested that if we go on dividing matter, a stage will come when particles obtained cannot be divided further. Democritus called these indivisible particles atoms, meaning indivisible. All this was based on philosophical considerations, and not much experimental work to validate these ideas could be done till the 18th century. By the end of the 18th century, scientists recognized the difference between elements and compounds, and naturally became interested in finding out how and why elements combine and what happens when they combine. Antoine Lavoisier laid the foundation of chemical sciences by establishing two important laws of chemical combination. 3.1 Laws of chemical combination. The following two laws of chemical combination were established after much experimentations by Lavoisier and Joseph L. Proust. 3.1.1 Law of conservation of mass. Is there a change in mass when a chemical reaction takes place? Activity 3.1 Middle. Take one of the following sets. X and Y of chemicals. XYI copper sulfate sodium carbonate 1.25 grams 1.43 grams 2 barium chloride sodium sulfate 1.22 grams 1.53 grams 3 lead nitrate sodium chloride 2.07 grams 1.17 grams. Middle. Prepare separately a 5 solution of any one pair of substances listed under X and Y, each in 10 ml in water. Middle. Take a little amount of solution of Y in a conical flask and some solution of X in an ignition tube. Middle. Hang the ignition tube in the flask carefully. See that the solutions do not get mixed. Put a cork on the flask. See figure 3.1. Figure 3.1, ignition tube containing solution of X, dipped in a conical flask containing solution of Y. 3 atoms tombstones and molecules. Chapter SCIENCE 32. Middle. Weigh the flask with its contents carefully. Middle. Now tilt and swirl the flask, so that the solutions X and Y get mixed. Middle. Weigh again. Middle. What happens in the reaction flask? Middle. Do you think that a chemical reaction has taken place? Middle. Why should we put a cork on the mouth of the flask? Middle. Does the mass of the flask and its contents change? Law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. 3.1.2 Law of constant proportions. Lavoisier, along with other scientists, noted that many compounds were composed of two or more elements and each such compound had the same elements in the same proportions, irrespective of where the compound came from or who prepared it. In a compound such as water, the ratio of the mass of hydrogen to the mass of oxygen is always 1:8, whatever the source of water. Thus, if 9 grams of water is decomposed, 1 gram of hydrogen and 8 grams of oxygen are always obtained. Similarly, in ammonia, nitrogen and hydrogen are always present in the ratio 14:3 by mass, whatever the method or the source from which it is obtained. This led to the law of constant proportions, which is also known as the law of definite proportions. This law was stated by Proust as in a chemical substance the elements are always present in definite proportions by mass. The next problem faced by scientists was to give appropriate explanations of these laws. British chemist John Dalton provided the basic theory about the nature of matter. Dalton picked up the idea of divisibility of matter, which was till then just a philosophy. He took the name atoms as given by the Greeks and said that the smallest particles of matter are atoms. His theory was based on the laws of chemical combination. Dalton's atomic theory provided an explanation for the law of conservation of mass and the law of definite proportions. John Dalton was born in a poor weaver's family in 1766 in England. He began his career as a teacher at the age of 12. 7 years later he became a school principal. In 1793, Dalton left for Manchester to teach mathematics, physics and chemistry in a college. He spent most of his life there teaching and researching. In 1808, he presented his atomic theory, which was a turning point in the study of matter. According to Dalton's atomic theory, all matter, whether an element, a compound or a mixture, is composed of small particles called atoms. The postulates of this theory may be stated as follows. All matter is made of very tiny particles called atoms, which participate in chemical reactions. 2 atoms are indivisible particles, which cannot be created or destroyed in a chemical reaction. 3 atoms of a given element are identical in mass and chemical properties. 5 atoms of different elements have different masses and chemical properties. The atoms combine in the ratio of small whole numbers to form compounds. 6. The relative number and kinds of atoms are constant in a given compound. You will study in the next chapter that all atoms are made up of still smaller particles. Questions 1. In a reaction, 5.3 grams of sodium carbonate reacted with 6 grams of acetic acid. The products were 2.2 grams of carbon dioxide, 0.9 grams water, and 8.2 grams of sodium acetate. Show that these equal John Dalton. Atoms and molecules. 33. We might think that if atoms are so insignificant in size, why should we care about them? This is because our entire world is made up of atoms. We may not be able to see them, but they are there, and constantly affecting whatever we do. Through modern techniques, we can now produce magnified images of surfaces of elements showing atoms. Observations are in agreement with the law of conservation of mass. Sodium carbonate, acetic acid, sodium acetate, carbon dioxide, water. 2. Hydrogen and oxygen combine in the ratio of 1:8 by mass to form water. What mass of oxygen gas would be required to react completely with 3 grams of hydrogen gas? 3. Which postulate of Dalton's atomic theory is the result of the law of conservation of mass? 4. Which postulate of Dalton's atomic theory can explain the law of definite proportions? 3.2 What is an atom? Have you ever observed a mason building walls? From these walls a room and then a collection of rooms to form a building. What is the building block of the huge building? What about the building block of an anthill? It is a small grain of sand. Similarly, the building blocks of all matter are atoms. How big are atoms? Atoms are very small. They are smaller than anything that we can imagine or compare with. More than millions of atoms when stacked would make a layer barely as thick as this sheet of paper. Atomic radius is measured in nanometers. 110 9 meters, 1 nm, 1 meter, 109 nm. Relative sizes: radium m. Example: 1010 atom of hydrogen, 109 molecule of water, 108 molecule of hemoglobin, 104 grain of sand, 103 and 101 apple. Figure 3.2 An image of the surface of silicon. 3.2.1 What are the modern-day symbols of atoms of different elements? Dalton was the first scientist to use the symbols for elements in a very specific sense. When he used a symbol for an element, he also meant a definite quantity of that element, that is, 1 atom of that element. Berzelius suggested that the symbols of elements be made from 1 or 2 letters of the name of the element. Figure 3.3 Symbols for some elements as proposed by Dalton. SCIENCE 34 In the beginning, the names of elements were derived from the name of the place where they were found for the first time. For example, the name copper was taken from Cyprus. Some names were taken from specific colors. For example, gold was taken from the English word meaning yellow. Nowadays, IUPAC International Union of Pure and Applied Chemistry is an international scientific organization which approves names of elements, symbols and units. Many of the symbols are the first 1 or 2 letters of the element's name in English. The first letter of a symbol is always written as a capital letter uppercase and the second letter as a small letter lowercase. For example, I hydrogen, H2 aluminium, Al and not Alabama 3 cobalt, Co and not company. Symbols of some elements are formed from the first letter of the name and a letter appearing later in the name. Examples are I chlorine, Cl, to zinc, Zn, etc. Other symbols have been taken from the names of elements in Latin, German or Greek. For example, the symbol of iron is Fe from its Latin name ferrum, sodium is Na from natrium, potassium is K from kalium. Therefore, each element has a name and a unique chemical symbol. The above table is given for you to refer to whenever you study about elements. Do not bother to memorize all in one go. With the passage of time and repeated usage, you will automatically be able to reproduce the symbols. 3.2.2 Atomic mass. The most remarkable concept that Dalton's atomic theory proposed was that of the atomic mass. According to him, each element had a characteristic atomic mass. The theory could explain the law of constant proportions so well that scientists were prompted to measure the atomic mass of an atom. Since determining the mass of an individual atom was a relatively difficult task, relative atomic masses were determined using the laws of chemical combinations and the compounds formed. Let us take the example of a compound, carbon monoxide CO, formed by carbon and oxygen. It was observed experimentally that 3 grams of carbon combines with 4 grams of oxygen to form company. In other words, carbon combines with 3 times its mass of oxygen. Suppose we define the atomic mass unit earlier abbreviated as AMU. But according to the latest IUPAC recommendations, it is now written as U, unified mass, as equal to the mass of one carbon atom. Then we would assign carbon an atomic mass of 1.0 U and oxygen an atomic mass of 1.33 U. However, it is more convenient to have these numbers as Table 3.1, symbols for some elements: element symbol, aluminium, Al, copper, Cu, nitrogen, N, argon, Arkansas, fluorine, F, oxygen, O, barium, B, gold, O, potassium, K, boron, B, hydrogen, H, silicon, C, bromine, branch, iodine, I, silver, Ag, calcium, K, iron, Fe, sodium, N, carbon, C, lead, Pb, sulfur, S, chlorine, Cl, magnesium, milligrams, uranium, U, cobalt, Co, neon, zinc, Zn. Atoms and molecules. 35 whole numbers, or as near to a whole numbers as possible. While searching for various atomic mass units, scientists initially took 1/16 of the mass of an atom of naturally occurring oxygen as the unit. This was considered relevant due to 2 reasons. Oxygen reacted with a large number of elements and formed compounds. This atomic mass unit gave masses of most of the elements as whole numbers. However, in 1961, for a universally accepted atomic mass unit, carbon-12 isotope was chosen as the standard reference for measuring atomic masses. One atomic mass unit is a mass unit equal to exactly 1/12 the mass of one atom of carbon-12. The relative atomic masses of all elements have been found with respect to an atom of carbon-12. Imagine a fruit seller selling fruits without any standard weight with him. He takes a watermelon and says, "This has a mass equal to 12 units." 12 watermelon units or 12 fruit mass units. He makes 12 equal pieces of the watermelon and finds the mass of each fruit he is selling, relative to the mass of one piece of the watermelon. Now he sells his fruits by relative fruit mass unit FMU, as in Figure 3.4. Figure 3.4, a watermelon. B 12 pieces, C1 12 of watermelon, D how the fruit seller can weigh the fruits using pieces of watermelon. Similarly, the relative atomic mass of the atom of an element is defined as the average mass of the atom, as compared to 1/12 the mass of one carbon-12 atom. Table 3.2, atomic masses of a few elements. Element atomic mass: U, hydrogen 1, carbon 12, nitrogen 14, oxygen 16, sodium 23, magnesium 24, sulfur 32, chlorine 35.5, calcium 43.2.3. How do atoms exist? Atoms of most elements are not able to exist independently. Atoms form molecules and ions. These molecules or ions aggregate in large numbers to form the matter that we can see, feel or touch. Questions 1. Define the atomic mass unit. 2. Why is it not possible to see an atom with naked eyes? 3.3 What is a molecule? A molecule is in general a group of two or more atoms that are chemically bonded together. That is, tightly held together by attractive forces. A molecule can be defined as the smallest particle of an element or a compound that is capable of an independent existence and shows all the properties of that substance. Atoms of the same element or of different elements can join together to form molecules. Q. SCIENCE 36 3.3.1 Molecules of elements. The molecules of an element are constituted by the same type of atoms. Molecules of many elements, such as argon, Arkansas, helium, He, etc., are made up of only one atom of that element. But this is not the case with most of the nonmetals. For example, a molecule of oxygen consists of two atoms of oxygen, and hence it is known as a diatomic molecule, O2. If three atoms of oxygen unite into a molecule, instead of the usual two, we get ozone, O3. The number of atoms constituting a molecule is known as its atomicity. Metals and some other elements, such as carbon, do not have a simple structure but consist of a very large and indefinite number of atoms bonded together. Let us look at the atomicity of some nonmetals. Table 3.3, Atomicity of some elements. Type of name: atomicity. Element: non-metal, argon, monoatomic, helium, monoatomic, oxygen, diatomic, hydrogen, diatomic, nitrogen, diatomic, chlorine, diatomic, phosphorus, tetraatomic, sulfur, polyatomic. Table 3.4, Molecules of some compounds. Compound combining ratio: elements by mass: water, H2O, hydrogen, oxygen 1, 8 ammonia, NH3, nitrogen, hydrogen 14, 3 carbon dioxide, CO2, carbon, oxygen 3, 8 activity. 3.2 Middle dot. Refer to Table 3.4 for ratio by mass of atoms present in molecules and Table 3.2 for atomic masses of elements. Find the ratio by number of the atoms of elements in the molecules of compounds given in Table 3.4. Middle dot. The ratio by number of atoms for a water molecule can be found as follows: element ratio, atomic mass, simplest by mass ratio, ratio mass U, atomic mass H1 1 1 1 1 208 16 8 16 1 2 1. Middle dot. Thus, the ratio by number of atoms for water is H surprised 2 1. 3.3.3 What is an ion? Compounds composed of metals and nonmetals contain charged species. The charged species are known as ions. Ions may consist of a single charged atom or a group of atoms that have a net charge on them. An ion can be negatively or positively charged. A negatively charged ion is called an anion, and the positively charged ion, a cation. Take, for example, sodium chloride NaCl. Its constituent particles are positively charged sodium ions Na and negatively charged 3.3.2 molecules of compounds. Atoms of different elements join together in definite proportions to form molecules of compounds. Few examples are given in Table 3.4. Atoms and molecules. 37 Chloride ion Cl. A group of atoms carrying a charge is known as a polyatomic ion. Table 3.6. We shall learn more about the formation of ions in Chapter 4. Learn the symbols and combining capacity of the elements. The combining power or capacity of an element is known as its valency. Valency can be used to find out how the atoms of an element will combine with the atom S of another element to form a chemical compound. The valency of the atom of an element can be thought of as hands or arms of that atom. Human beings have 2 arms and an octopus has 8. If one octopus has to catch hold of a few people in such a manner that all the 8 arms of the octopus and both arms of all the humans are locked, how many humans do you think the octopus can hold? Represent the octopus with O and humans with H. Can you write a formula for this combination? Do you get RH4 as the formula? The subscript 4 indicates the number of humans held by the octopus. The valencies of some common ions are given in Table 3.6. We will learn more about valency in the next chapter. Some elements show more than one valency. A Roman numeral shows their valency in a bracket. Table 3.5. Some ionic compounds. Ionic constituting ratio compound elements by mass: calcium oxide, calcium and oxygen 5, 2 magnesium, magnesium sulfate and sulfur 3, 4 sodium, sodium chloride and chlorine 2335. 5. 3.4 Writing chemical formulae. The chemical formula of a compound is a symbolic representation of its composition. The chemical formulae of different compounds can be written easily. For this exercise, we need to Table 3.6, names and symbols of some ions. Veil: name of simple, non-simple, polyatomic, simple, C ion, metallic ions. Element 1. Sodium, hydrogen, H ammonium, NH4 potassium, K hydride, H hydroxide, Ohio silveride, chloride, Cl nitrate, NO3 copper, ICU bromide, branch hydrogen iodide, bicarbonate, HCO3 2. Magnesium milligrams, 2 oxide, O2 carbonate, CO3 2 calcium, K2 sulfate, S2 sulfite, SO3 2 zinc, Zn2 sulfate, SO4 2 iron, 2 Fe2 copper, 2 Cu2 3. Aluminium, Al3 nitride, N3 phosphate, PO4 3 iron, 3 Fe3. SCIE NCE38 3. Formula of carbon tetrachloride. For magnesium chloride, we write the symbol of cation milligrams 2 first, followed by the symbol of NaCl. Then their charges are crisscrossed to get the formula. 4. Formula of magnesium chloride. Formula, MgCl2. Thus, in magnesium chloride, there are 2 chloride ions Cl for each magnesium ion milligrams 2. The positive and negative charges must balance each other and the overall structure must be neutral. Note that in the formula, the charges on the ions are not indicated. Some more examples of formula for aluminium oxide. Formula, Al2O3b. Formula for calcium oxide. Here, the valencies of the two elements are the same. You may arrive at the formula K2O2. But we simplify the formula as Ca. The rules that you have to follow while writing a chemical formula are as follows. Middle dot: the valencies or charges on the ion must balance. Middle dot: when a compound consists of a metal and a non-metal, the name or symbol of the metal is written first. For example, calcium oxide Ca, sodium chloride NaCl, iron sulfate Fes, copper oxide Co, etc., where oxygen, chlorine, sulfur are nonmetals and are written on the right, whereas calcium, sodium, iron and copper are metals, and are written on the left. Middle dot: in compounds formed with polyatomic ions, the number of ions present in the compound is indicated by enclosing the formula of ion in the bracket and writing the number of ions outside the bracket. For example, milligrams O2. In case the number of polyatomic ion is 1, the bracket is not required. For example, NaO. 3.4.1 Formulae of simple compounds. The simplest compounds, which are made up of two different elements, are called binary compounds. Valencies of some ions are given in Table 3.6. You can use these to write formulae for compounds. While writing the chemical formulae for compounds, we write the constituent elements and their valencies as shown below. Then we must cross over the valencies of the combining atoms. Examples 1. Formula of hydrogen chloride. Formula of the compound would be HCl. 2. Formula of hydrogen sulfide. Atoms and molecules. 39 Following formulae: Al2SO432 Kcl2 3K2SO4 5KNO3 VCaco3. 3. What is meant by the term chemical formula for? How many atoms are present in IH2S molecule and 2PO4 ion? 3.5 Molecular mass and mole concept. 3.5.1 Molecular mass. In section 3.2.2 we discuss the concept of atomic mass. This concept can be extended to calculate molecular masses. The molecular mass of a substance is the sum of the atomic masses of all the atoms in a molecule of the substance. It is therefore the relative mass of a molecule expressed in atomic mass units U. Example 3.1 calculate the relative molecular mass of water H2O. B. Calculate the molecular mass of HNO3. Solution: atomic mass of hydrogen 1 U, oxygen 16 U. So the molecular mass of water, which contains 2 atoms of hydrogen and 1 atom of oxygen, is 2 times 1 times 16, 18 U. B. The molecular mass of HNO3, the atomic mass of H, the atomic mass of N 3 times the atomic mass of O1, 14, 48, 63 U. 3.5.2 Formula unit mass. The formula unit mass of a substance is a sum of the atomic masses of all atoms in a formula unit of a compound. Formula unit mass is calculated in the same manner as we calculate the molecular mass. The only difference is that C. Formula of sodium nitrate, formula, nano 3D. Formula of calcium hydroxide, formula, CO2. Note that the formula of calcium hydroxide is CO2 and not KO2. We use brackets when we have 2 or more of the same ions in the formula. Here, the bracket around O with a subscript 2 indicates that there are 2 hydroxyl groups joined to one calcium atom. In other words, there are 2 atoms each of oxygen and hydrogen in calcium hydroxide. E. Formula of sodium carbonate, formula, Na2CO3. In the above example, brackets are not needed if there is only one ion present. F. Formula of ammonium sulfate, formula, NH42SO4 Questions 1. Write down the formulae of isodium oxide 2 aluminium chloride 3 sodium sulfide magnesium hydroxide 2. Write down the names of compounds represented by Tech. We use the word formula unit for those substances whose constituent particles are ions. For example, sodium chloride, as discussed above, has a formula unit NaCl. Its formula unit mass can be calculated as 1 times 23, 1 times 35.5, 58.5 U. Example 3.2 Calculate the formula unit mass of Cl2. Solution: atomic mass of Ca2 times atomic mass of Cl40, 2 times 35.5, 4071, 111 U. Questions 1. Calculate the molecular masses of H2, O2, Cl2, CO2, CH4, C2H6, C2H4, NH3, CH3OH. 2. Calculate the formula unit masses of SNO. Na2O, K2CO3, given atomic masses of CN65U, Na23U, K39U, C12U, and O16U. 3.5.3 Mole concept. Take an example of the reaction of hydrogen and oxygen to form water, 2H2O2 2H2O. The above reaction indicates that I2 molecules of hydrogen combine with 1 molecule of oxygen to form 2 molecules of water. Or 24U of hydrogen molecules combine with 32U of oxygen molecules to form 36U of water molecules. We can infer from the above equation that the quantity of a substance can be characterized by its mass or the number of molecules. But, a chemical reaction equation indicates directly the number of atoms or molecules taking part in the reaction. Therefore, it is more convenient to refer to the quantity of a substance in terms of the number of its molecules or atoms, rather than their masses. So, a new unit mole was introduced. 1 mole of any species atoms, Q figure 3.5, relationship between mole, Avogadro number and mass. Molecules, ions or particles is that quantity in number having a mass equal to its atomic or molecular mass in grams. The number of particles, atoms, molecules or ions present in 1 mole of any substance is fixed, with a value of 6.022 times 1023. This is an experimentally obtained value. This number is called the Avogadro constant or Avogadro number, represented by N0, named in honor of the Italian scientist, Amedeo Avogadro. 1 mole of anything 6.022 times 1023 in number, as 1 dozen 12 knows. 1 gross 144 knows. Besides being related to a number, a mole has one more advantage over a dozen or a gross. This advantage is that mass of 1 mole of a particular substance is also fixed. The mass of 1 mole of a substance is equal to its relative atomic or molecular mass in grams. The atomic mass of an element gives us the mass of one atom of that element in atomic mass units U. To get the mass of 1 mole of atom of that element, that is, molar mass, we have to take the same numerical value but change the units from U to G. Molar mass of atoms is also known as gram atomic mass, for example, atomic mass of hydrogen 1 U. So, gram atomic mass of hydrogen 1 gram. 1 U hydrogen has only one atom of hydrogen. 1 gram hydrogen has 1 mole atoms, that is, 6.022 times 1023 atoms of hydrogen. Similarly, 16 U oxygen has only 1 atom of oxygen. 16 grams oxygen has 1 mole atoms, that is, 6.022 times 1023 atoms of oxygen. To find the gram molecular mass or molar mass of a molecule, we keep the numerical value the same as a molecular mass, but simply change units as above from U to G. For example, as we have already calculated, molecular mass of water H2O is 18 U. From here we understand that 18 U water has only 1 molecule of water, 18 grams water has 1 mole molecules of water, that is, 6.022 times 1023 molecules of water. Chemists need the number of atoms and molecules while carrying out reactions, and for this they need to relate the mass in grams to the number. It is done as follows: 1 mole 6.022 times 1023 number relative mass in grams. Thus, a mole is a chemist's counting unit. The word mole was introduced around 1896 by Wilhelm Ostwald, who derived the term from the Latin word moles, meaning a heap or pile. A substance may be considered as a heap of atoms or molecules. The unit mole was accepted in 1967 to provide a simple way of reporting a large number, the massive heap of atoms and molecules in a sample. Example 3.3.1. Calculate the number of moles for the following: I 52 grams of the finding mole from mass 212.044 times 1023 number of E atoms finding mole from number of particles. Solutions: no. Of moles N given mass M, molar mass M given number of particles N, Avogadro number of particles N, 0 I atomic mass of He 4 U, molar mass of He 4 grams. Thus, the number of moles given mass, molar mass N, MM 52, 4, 13, 2. We know, 1 mole 6.022 times 1023. The number of moles given number of particles, Avogadro number times NM, no 12, 044, 10, 6, 022, 10, 2, 23, 23. Example 3.4. Calculate the mass of the following: I 0.5 mole of N2 gas mass from mole of molecule 2, 0.5 mole of N atoms mass from mole of atom 3, 3.011 times 1023 number of N atoms mass from number I, 6.022 times 1023 number of N2 molecules mass from number. Solutions: I mass, molar mass times number of moles times mmNg 28, 0, 5, 14. 2 mass, molar mass times number of moles mm times N 14 times 0.5, 7 grams. 3 the number of moles N 0 given number of particles N, Avogadro number N 23, 23, 3.011, 10, 6.022, 10 times mmN 14, 3, 011, 10, 6, 022, 10, 23, 23. 14, 0.5, 7 grams times I 0 and NM times mmN N 0 23, 23, 28, 6, 022, 10, 6, 022, 10. 28 28 grams times example 3.5. Calculate the number of particles in each of the following: I 46 grams of atoms number from mass 2 8 grams O2 molecules number of molecules from mass 3 0.1 mole of carbon atoms number from given moles solutions. I the number of atoms given mass Avogadro number molar mass times NMN 0 times Mn 46 23 6 0 22 10 1 2 0 4 4 1 0 2 3 2 3 dot 2 the number of molecules times given mass molar mass of Avogadro number NMN atomic mass of oxy 0 ENU 16 molar mass of O2 molecules 16 times 2 32 grams times NN 8 32 6 0 22 10 1 5055 1 0 1 5 1 1 0 2 3 2 3 2 3 3 the number of particles atom number of moles of particles times Avogadro number Nn times N0 0.1 x 6.022 times 1023 6.022 times 1022 Questions 1. If 1 mole of carbon atoms weighs 12 grams, what is the mass in grams of 1 atom of carbon 2? Which has more number of atoms, 100 grams of sodium or 100 grams of iron given, atomic mass of Na23U? Fe56UQ. Atoms and molecules 43 What you have learned middle dot during a chemical reaction, the sum of the masses of the reactants and products remains unchanged. This is known as the law of conservation of mass middle dot in a pure chemical compound. Elements are always present in a definite proportion by mass. This is known as the law of definite proportions. Middle dot an atom is the smallest particle of the element that cannot usually exist independently and retain all its chemical properties. Middle dot a molecule is the smallest particle of an element or a compound capable of independent existence under ordinary conditions. It shows all the properties of the substance. Middle dot a chemical formula of a compound shows its constituent elements and the number of atoms of each combining element. Middle dot clusters of atoms that act as an ion are called polyatomic ions. They carry a fixed charge on them. Middle dot the chemical formula of a molecular compound is determined by the valency of each element. Middle dot in ionic compounds, the charge on each ion is used to determine the chemical formula of the compound. Middle dot scientists use the relative atomic mass scale to compare the masses of different atoms of elements. Atoms of carbon-12 isotopes are assigned a relative atomic mass of 12, and the relative masses of all other atoms are obtained by comparison with the mass of a carbon-12 atom. Middle dot the Avogadro constant 6.022 times 1023 is defined as the number of atoms in exactly 12 grams of carbon-12. Middle dot the mole is the amount of substance that contains the same number of particles atoms ions molecules formula units etc. as there are atoms in exactly 12 grams of carbon-12. Middle dot mass of 1 mole of a substance is called its molar mass. Exercises 1. A 0.24 gram sample of compound of oxygen and boron was found by analysis to contain 0.096 grams of boron and 0.144 grams of oxygen. Calculate the percentage composition of the compound by weight. 2. When 3.0 grams of carbon is burnt in 8.00 grams oxygen, 11.00 grams of carbon dioxide is produced. What mass of carbon dioxide will SCIENCE44 be formed when 3.00 grams of carbon is burnt in 50.00 grams of oxygen? Which law of chemical combination will govern your answer? 3. What are polyatomic ions? Give examples. 4. Write the chemical formulae of the following. A magnesium chloride B calcium oxide C copper nitrate D aluminium chloride E calcium carbonate. 5. Give the names of the elements present in the following compounds. A quicklime B hydrogen bromide C baking powder D potassium sulfate. 6. Calculate the molar mass of the following substances. Ethine, C2H2B sulfur molecule, S8C phosphorus molecule, P4 atomic mass of phosphorus 31 dihydrochloric acid, HCl nitric acid, NO3 7. What is the mass of a 1 mole of nitrogen atoms? B 4 moles of aluminium atoms. Atomic mass of aluminium 27 C 10 moles of sodium sulfide Na2SO3 8. Convert into mole. A 12 grams of oxygen gas. B 20 grams of water. C 22 grams of carbon dioxide. 9. What is the mass of a 0.2 mole of oxygen atoms? B 0.5 mole of water molecules. 10. Calculate the number of molecules of sulfur S8 present in 16 grams of solid sulfur. 11. Calculate the number of aluminium ions present in 0.051 grams of aluminium oxide. Hint: the mass of an ion is the same as that of an atom of the same element. Atomic mass of Al 27U. Atoms and molecules. 45 Group activity. Play a game for writing formulae. Example 1. Make placards with symbols and valencies of the elements separately. Each student should hold 2 placards, one with the symbol in the right hand and the other with the valency in the left hand. Keeping the symbols in place, students should crisscross their valencies to form the formula of a compound. Example 2. A low-cost model for writing formulae. Take empty blister packs of medicines. Cut them in groups, according to the valency of the element, as shown in the figure. Now, you can make formulae by fixing one type of ion into other. For example, NaSO4 2P04 3 formula for sodium sulfate. 2 sodium ions can be fixed on one sulfate ion. Hence, the formula will be Na2SO4. Do it yourself. Now, write the formula of sodium phosphate. In Chapter 3, we have learned that atoms and molecules are the fundamental building blocks of matter. The existence of different kinds of matter is due to different atoms constituting them. Now the questions arise: what makes the atom of one element different from the atom of another element, and are atoms really indivisible? As proposed by Dalton, or are there smaller constituents inside the atom? We shall find out the answers to these questions in this chapter. We will learn about subatomic particles and the various models that have been proposed to explain how these particles are arranged within the atom. A major challenge before the scientists at the end of the 19th century was to reveal the structure of the atom as well as to explain its important properties. The elucidation of the structure of atoms is based on a series of experiments. One of the first indications that atoms are not indivisible comes from studying static electricity and the condition under which electricity is conducted by different substances. 4.1 Charged particles in matter. For understanding the nature of charged particles in matter, let us carry out the following activities. Activity 4.1a. Comb dry hair. Does the comb then attract small pieces of paper? B. Rub a glass rod with a silk cloth and bring the rod near an inflated balloon. Observe what happens. From these activities, can we conclude that on rubbing two objects together, they become electrically charged? Where does this charge come from? This question can be answered by knowing that an atom is divisible and consists of charged particles. Many scientists contributed in revealing the presence of charged particles in an atom. It was known by 1900 that the atom was an indivisible particle but contained at least one subatomic particle, the electron, identified by J.J. Thomson. Even before the electron was identified, E. Goldstein in 1886 discovered the presence of new radiations in a gas discharge and called them canal rays. These rays were positively charged radiations, which ultimately led to the discovery of another subatomic particle. This subatomic particle had a charge, equal in magnitude but opposite in sign to that of the electron. Its mass was approximately 2,000 times as that of the electron. It was given the name of proton. In general, an electron is represented as E and a proton as single quote P. The mass of a proton is taken as 1 unit and its charge is +1. the mass of an electron is considered to be negligible and its charge is -1. It seemed that an atom was composed of protons and electrons, mutually balancing their charges. It also appeared that the protons were in the interior of the atom, for whereas electrons could easily be removed off but not protons. Now the big question was, what sort of structure did these particles of the atom form? We will find the answer to this question below. For SSSTRUCTURETRUCTURETRUCTURETRUCTURE of of the atom chapter. Questions 1. What are Canel raised to? If an atom contains one electron and one proton, will it carry any charge or not? 4.2 The structure of an atom. We have learned Dalton's atomic theory in Chapter 3, which suggested that the atom was indivisible and indestructible. But the discovery of two fundamental particles, electrons and protons, inside the atom, led to the failure of this aspect of Dalton's atomic theory. It was then considered necessary to know how electrons and protons are arranged within an atom. For explaining this, many scientists proposed various atomic models. J. Thomson was the first one to propose a model for the structure of an atom. 4.2.1 Thomson's model of an atom. Thomson proposed the model of an atom to be similar to that of a Christmas pudding. The electrons, in a sphere of positive charge, were like currants, dry fruits in a spherical Christmas pudding. We can also think of a watermelon. The positive charge in the atom is spread all over like the red edible part of the watermelon, while the electrons are studded in the positively charged sphere, like the seeds in the watermelon figure. 4.1. Thomson proposed that an atom consists of a positively charged sphere and the electrons are embedded in it. 2. The negative and positive charges are equal in magnitude. So, the atom as a whole is electrically neutral. Although Thomson's model explained that atoms are electrically neutral, the results of experiments carried out by other scientists could not be explained by this model, as we will see below. 4.2.2 Rutherford's model of an atom. Ernest Rutherford was interested in knowing how the electrons are arranged within an atom. Rutherford designed an experiment for this. In this experiment, fast-moving alpha particles were made to fall on a thin gold foil. He selected a gold foil because he wanted as thin a layer as possible. This gold foil was about 1,000 atoms thick. Particles are doubly charged helium ions. Since they have a mass of 4U, the fast-moving particles have a considerable amount of energy. It was expected that particles would be deflected by the subatomic particles in the gold atoms. Since the particles were much heavier than the protons, he did not expect to see large deflections. QFIG.4.1 Thomson's model of an atom. J. Thomson 1856–1940, a British physicist, was born in Cheetham Hill, a suburb of Manchester, on the 18th of December 1856. He was awarded the Nobel Prize in Physics in 1906 for his work on the discovery of electrons. He directed the Cavendish Laboratory at Cambridge for 35 years, and 7 of his research assistants subsequently won Nobel Prizes. Structure of the atom. 47. SCIENCE 48 Figure 4.2, Scattering of particles by a gold foil. But the particle scattering experiment gave totally unexpected results. Figure 4.2. The following observations were made. Most of the fast-moving particles pass straight through the gold foil. 2. Some of the particles were deflected by the foil by small angles. 3. Surprisingly, 1 out of every 12,000 particles appeared to rebound. In the words of Rutherford, this result was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you. Hear a sound when each stone strikes the wall. If he repeats this 10 times, he will hear the sound 10 times. But if a blindfolded child were to throw stones at a barbed wire fence, most of the stones would not hit the fencing and no sound would be heard. This is because there are lots of gaps in the fence which allow the stone to pass through them. Following a similar reasoning, Rutherford concluded from the particle scattering experiment that most of the space inside the atom is empty, because most of the particles pass through the gold foil without getting deflected. Very few particles were deflected from their path, indicating that the positive charge of the atom occupies very little space. A very small fraction of particles were deflected by 1800, indicating that all the positive charge and mass of the gold atom were concentrated in a very small volume within the atom. From the data he also calculated that the radius of the nucleus is about 105 times less than the radius of the atom. On the basis of his experiment, Rutherford put forward the nuclear model of an atom, which had the following features. There is a positively charged center in an atom called the nucleus. Nearly all the mass of an atom resides in the nucleus. The electrons revolve around the nucleus in circular paths. The size of the nucleus is very small as compared to the size of the atom. Drawbacks of Rutherford's model of the atom: the revolution of the electron in a circular orbit is not expected to be stable. Any particle in a circular orbit would undergo acceleration. During acceleration, charged particles would radiate energy. Thus, the revolving electron would lose energy and finally fall into the nucleus. If this were so, the atom should be highly unstable and hence matter would not exist in the form that we know. We know that atoms are quite stable. E. Rutherford 1871–1937 was born at Spring Grove on the 30th of August 1871. He was known as the father of nuclear physics. He is famous for his work on radioactivity and the discovery of the nucleus of an atom with the gold foil experiment. He got the Nobel Prize in Chemistry in 1908. Let us think of an activity in an open field to understand the implications of this experiment. Let a child stand in front of a wall with his eyes closed. Let him throw stones at the wall from a distance. He will. Structure of the atom. 49.4.2.3 Bohr's model of atom. In order to overcome the objections raised against Rutherford's model of the atom, Niels Bohr put forward the following postulates about the model of an atom. Only certain special orbits known as discrete orbits of electrons are allowed inside the atom. 2. While revolving in discrete orbits, the electrons do not radiate energy. Questions 1. On the basis of Thomson's model of an atom, explain how the atom is neutral as a whole. 2. On the basis of Rutherford's model of an atom, which subatomic particle is present in the nucleus of an atom? 3. Draw a sketch of Bohr's model of an atom with 3 shells. 4. What do you think would be the observation if the particle scattering experiment is carried out using a foil of a metal other than gold? 4.2.4 Neutrons. In 1932, J. Chadwick discovered another subatomic particle which had no charge and a mass nearly equal to that of a proton. It was eventually named as neutron. Neutrons are present in the nucleus of all atoms, except hydrogen. In general, a neutron is represented as n. The mass of an atom is therefore given by the sum of the masses of protons and neutrons present in the nucleus. Questions 1. Name the 3 subatomic particles of an atom. 2. Helium atom has an atomic mass of 4U and 2 protons in its nucleus. How many neutrons does it have? 4.3 How are electrons distributed in different orbit shells? The distribution of electrons into different orbits of an atom was suggested by Bohr and Berry. The following rules are followed for writing the number of electrons in different energy levels or shells. The maximum number of electrons present in a shell is given by the Niels Bohr. 1885–1962 was born in Copenhagen on the 7th of October 1885. He was appointed professor of physics at Copenhagen University in 1916. He got the Nobel Prize for his work on the structure of atom in 1922. Among Professor Bohr's numerous writings, 3 appearing as books are, I. The Theory of Spectra and Atomic Constitution, 2. Atomic Theory and 3. The Description of Nature. These orbits or shells are called energy levels. Energy levels in an atom are shown in Figure 4.3. Q. Figure 4.3. A few energy levels in an atom. These orbits or shells are represented by the letters K, L, M, N, or the numbers N1, 2, 3, 4. Q. SCIENCE50 Formula 2 and 2, where N is the orbit number or energy level index, 1, 2, 3. Hence the maximum number of electrons in different shells are as follows. First orbit or K shell will be 2 times 12, 2. Second orbit or L shell will be 2 times 22, 8. Third orbit or M shell will be 2 times 32, 18. Fourth orbit or N shell will be 2 times 42, 32, and so on. 2. The maximum number of electrons that can be accommodated in the outermost orbit is 8. 3 electrons are not accommodated in a given shell, unless the inner shells are filled. That is, the shells are filled in a stepwise manner. Atomic structure of the first 18 elements is shown schematically in Figure 4.4. Middle dot. The composition of atoms of the first 18 elements is given in Table 4.1. Questions 1. Write the distribution of electrons in carbon and sodium atoms. 2. If K and L shells of an atom are full, then what would be the total number of electrons in the atom? 4.4 Valency. We have learned how the electrons in an atom are arranged in different shells orbits. The electrons present in the outermost shell of an atom are known as the valence electrons. From the Bohr-Berry scheme, we also know that the outermost shell of an atom can activity 4.2 middle dot make a static atomic model displaying electronic configuration of the first 18 elements. Fig.4.4 Schematic atomic structure of the first 18 elements. Q accommodate a maximum of 8 electrons. It was observed that the atoms of elements, completely filled with 8 electrons in the outermost shell, show little chemical activity. In other words, their combining capacity or valency is 0. Of these inert elements, the structure of the atom. 51 Table 4.1 Composition of atoms of the first 18 elements with electron distribution in various shells. Helium atom has 2 electrons in its outermost shell, and all other elements have atoms with 8 electrons in the outermost shell. The combining capacity of the atoms of elements, that is, their tendency to react and form molecules with atoms of the same or different elements, was thus explained as an attempt to attain a fully filled outermost shell. An outermost shell, which had 8 electrons, was said to possess an octet. Atoms would thus react, so as to achieve an octet in the outermost shell. This was done by sharing, gaining or losing electrons. The number of electrons gained, lost or shared so as to make the octet of electrons in the outermost shell, gives us directly the combining capacity of the element, that is, the valency discussed in the previous chapter. For example, hydrogen, lithium, sodium atoms contain 1 electron each in their outermost shell, therefore each one of them can lose 1 electron. So, they are said to have valency of 1. Can you tell what is valency of magnesium and aluminium? It is 2 and 3, respectively, because magnesium has 2 electrons in its outermost shell and aluminium has 3 electrons in its outermost shell. If the number of electrons in the outermost shell of an atom is close to its full capacity, then valency is determined in a different way. For example, the fluorine atom has 7 electrons in the outermost shell, and its valency could be 7. but it is easier for name of simple atomic number Veil element number of C protons neutrons electrons KLMN hydrogen H1 1 helium He2 2 0 lithium Li3 3 4 3 2 1 beryllium B4 4 5 4 2 boron B5 5 6 5 2 3 carbon C6 6 2 4 nitrogen and 7 2 5 3 oxygen or 8 2 6 2 fluorine F9 9 2 7 1 neon 10 2 8 0 sodium 11 12 2 8 1 magnesium milligrams 12 2 8 2 aluminium Al 13 14 2 8 3 silicon C 14 2 8 4 phosphorus P 15 16 2 8 5 3 5 sulfur S16 2 8 6 2 chlorine Cl 17 18 2 8 7 1 argon Arkansas 18 22 2 8 0 distribution of electrons SCIENCE 52 fluorine to gain 1 electron instead of losing 7 electrons. Hence, its valency is determined by subtracting 7 electrons from the octet, and this gives you a valency of 1 for fluorine. Valency can be calculated in a similar manner for oxygen. What is the valency of oxygen that you get from this calculation? Therefore, an atom of each element has a definite combining capacity, called its valency. Valency of the first 18 elements is given in the last column of table 4.1. Question 1. How will you find the valency of chlorine, sulfur and magnesium 4.5 atomic number and mass number 4.5.1 atomic number? We know that protons are present in the nucleus of an atom. It is a number of protons of an atom, which determines its atomic number. It is denoted by Z. All atoms of an element have the same atomic number, Z. In fact, elements are defined by the number of protons they possess. For hydrogen, Z1, because in hydrogen atom, only 1 proton is present in the nucleus. Similarly, for carbon, Z6. Therefore, the atomic number is defined as the total number of protons present in the nucleus of an atom. 4.5.2 mass number. After studying the properties of the subatomic particles of an atom, we can conclude that mass of an atom is practically due to protons and neutrons alone. These are present in the nucleus of an atom. Hence protons and neutrons are also called nucleons. Therefore, the mass of an atom resides in its nucleus. For example, mass of carbon is 12U because it has 6 protons and 6 neutrons. 6U 6U 12U. Similarly, the mass of aluminium is 27U 13 protons 14 neutrons. The mass number is defined as the sum of the total number of protons and neutrons present in the nucleus of an atom. It is denoted by A. In the notation for an atom, the atomic number, mass number and symbol of the element are to be written as mass number Q symbol of element atomic number. For example, nitrogen is written as 14(7N). Questions 1. If number of electrons in an atom is 8 and number of protons is also 8, then I. What is the atomic number of the atom? And 2. What is the charge on the atom? 2. With the help of table 4.1, find out the mass number of oxygen and sulfur atom. 4.6 Isotopes in nature. A number of atoms of some elements have been identified, which have the same atomic number but different mass numbers. For example, take the case of hydrogen atom. It has 3 atomic species, namely protium 1,1H, deuterium 2,1H, or D, and tritium 3,1H or T. The atomic number of each one is 1, but the mass number is 1, 2 and 3, respectively. Other such examples are I carbon, 12, 6C and 14, 6C, 2 chlorine, 35, 17 Cl and 37, 17 Cl, etc. On the basis of these examples, isotopes are defined as the atoms of the same element, having the same atomic number but different mass numbers. Therefore, we can say that there are 3 isotopes of hydrogen atom, namely protium, deuterium and tritium. QXZ. Structure of the atom 53Q. Many elements consist of a mixture of isotopes. Each isotope of an element is a pure substance. The chemical properties of isotopes are similar, but their physical properties are different. Chlorine occurs in nature in 2 isotopic forms, with masses 35U and 37U in the ratio of 3:1. Obviously, the question arises, what should we take as the mass of chlorine atom? Let us find out. The average atomic mass of chlorine atom, on the basis of above data, will be 35,75,100,37,25,100 times 105, 4, 37, 4, 142, 4, 35, 5. The mass of an atom of any natural element is taken as the average mass of all the naturally occurring atoms of that element. If an element has no isotopes, then the mass of its atom would be the same as the sum of protons and neutrons in it. But if an element occurs in isotopic forms, then we have to know the percentage of each isotopic form, and then the average mass is calculated. This does not mean that any one atom of chlorine has a fractional mass of 35.5 U. It means that if you take a certain amount of chlorine, it will contain both isotopes of chlorine and the average mass is 35.5 U. Applications. Since the chemical properties of all the isotopes of an element are the same, normally we are not concerned about taking a mixture. But some isotopes have special properties which find them useful in various fields. Some of them are, an isotope of uranium is used as a fuel in nuclear reactors. 2. An isotope of cobalt is used in the treatment of cancer. 3. An isotope of iodine is used in the treatment of goiter. 4.6.1 Isobars. Let us consider 2 elements: calcium, atomic number 20, and argon, atomic number 18. The number of protons in these atoms is different, but the mass number of both these elements is 40. That is, the total number of nucleons is the same in the atoms of this pair of elements. Atoms of different elements with different atomic numbers, which have the same mass number, are known as isobars. Questions 1. For the symbol H, D and T, tabulate 3 subatomic particles found in each of them. 2. Write the electronic configuration of any one pair of isotopes and isobars. What you have learned. Credit for the discovery of electron and proton goes to J.J. Thomson and E. Goldstein, respectively. J.J. Thomson proposed that electrons are embedded in a positive sphere. SCIENCE 54 Rutherford's alpha particle scattering experiment led to the discovery of the atomic nucleus. Rutherford's model of the atom proposed that a very tiny nucleus is present inside the atom and electrons revolve around this nucleus. The stability of the atom could not be explained by this model. Niels Bohr's model of the atom was more successful. He proposed that electrons are distributed in different shells with discrete energy around the nucleus. If the atomic shells are complete, then the atom will be stable and less reactive. J. Chadwick discovered presence of neutrons in the nucleus of an atom. So, the 3 subatomic particles of an atom are I electrons, 2 protons and 3 neutrons. Electrons are negatively charged, protons are positively charged and neutrons have no charges. The mass of an electron is about 1/2000 times the mass of an hydrogen atom. The mass of a proton and a neutron is taken as 1 unit each. Middle dot shells of an atom are designated as K, L, M, N. Middle dot valency is the combining capacity of an atom. Middle dot the atomic number of an element is the same as the number of protons in the nucleus of its atom. Middle dot the mass number of an atom is equal to the number of nucleons in its nucleus. Middle dot isotopes are atoms of the same element, which have different mass numbers. Middle dot isobars are atoms having the same mass number, but different atomic numbers. Middle dot elements are defined by the number of protons they possess. Exercises 1. Compare the properties of electrons, protons and neutrons. 2. What are the limitations of J.J. Thomson's model of the atom? 3. What are the limitations of Rutherford's model of the atom? 4. Describe Bohr's model of the atom. 5. Compare all the proposed models of an atom given in this chapter. 6. Summarize the rules for writing of distribution of electrons in various shells for the first 18 elements. 7. Define valency by taking examples of silicon and oxygen. Structure of the atom 55. 8. Explain with examples I atomic number, II mass number, III isotopes and IV isobars. Give any two uses of isotopes. 9. Na has completely filled K and L shells. Explain. 10. If bromine atom is available in the form of, say, two isotopes 79, 35 branch 49.7 and 81, 35 branch 50.3, calculate the average atomic mass of bromine atom. 11. The average atomic mass of a sample of an element X is 16.2 U. What are the percentages of isotopes 16, 8X and 18, 8X in the sample 12? If C3, what would be the valency of the element? Also, name the element. 13. Composition of the nuclei of two atomic species X and Y are given as under XY protons 6, 6 neutrons 6, 8. Give the mass numbers of X and Y. What is the relation between the two species? 14. For the following statements, write T for true and F for false. A J.J. Thomson proposed that the nucleus of an atom contains only nucleons. B. A neutron is formed by an electron and a proton combining together. Therefore, it is neutral. C. The mass of an electron is about 1/2000 times that of proton. D. An isotope of iodine is used for making tincture iodine, which is used as a medicine. Put TQ diaresis against correct choice and cross times against wrong choice in questions 15, 16 and 17. 15. Rutherford's alpha particle scattering experiment was responsible for the discovery of atomic nucleus B electron C proton D neutron. 16. Isotopes of an element have the same physical properties B different chemical properties C different number of neutrons D different atomic numbers. 17. Number of valence electrons in Cl ion are A 16 B8 C17 D18 SCIE CE 5618. Which one of the following is a correct electronic configuration of sodium? A 2, 8B8, 2, 1C2, 1, 8D2, 8, 1. 19. Complete the following table. Atomic mass number name of the atomic neutrons protons electrons species 9, 10, 16, 32 sulfur 24, 12, 2, 1, 1, 0, 1, 0. While examining a thin slice of cork, Robert Hooke saw that the cork resembled the structure of a honeycomb consisting of many little compartments. Cork is a substance which comes from the bark of a tree. This was in the year 1665 when Hooke made this chance observation through a self-designed microscope. Robert Hooke called these boxes cells. Cell is a Latin word for a little room. This may seem to be a very small and insignificant incident, but it is very important in the history of science. This was the very first time that someone had observed that living things appear to consist of separate units. The use of the word cell to describe these units is being used till this day in biology. Let us find out about cells. 5.1 What are living organisms made up of? Activity 5.1 Middle dot. Let us take a small piece from an onion bulb. With the help of a pair of forceps, we can peel off the skin called epidermis from the concave side inner layer of the onion. This layer can be put immediately in a watch glass containing water. This will prevent the peel from getting folded or getting dry. What do we do with this peel? Middle dot. Let us take a glass slide, put a drop of water on it and transfer a small piece of the peel from the watch glass to the slide. Make sure that the peel is perfectly flat on the slide. A thin camel hair paintbrush might be necessary to help transfer the peel. Now we put a drop of saffron in solution on this piece followed by a cover slip. Take care to avoid air bubbles while putting the cover slip with the help of a mounting needle. Ask your teacher for help. We have prepared a temporary mount of onion peel. We can observe this slide under low power followed by high powers of a compound microscope. Figure 5.1 Compound microscope. What do we observe as we look through the lens? Can we draw the structures that we are able to see through the microscope on an observation sheet? Does it look like figure 5.2 Eyepiece coarse adjustment fine adjustment arm objective lens stage swivel mirror base body tube clip microscope slide condenser figure 5.2 Cells of an onion peel 5 fundamental unit nit of of life of 5 chapter nucleus cells SCIENCE 58 Chlamydomonas, Paramecium and bacteria. These organisms are called unicellular organisms unisingle. On the other hand, many cells group together in a single body and assume different functions in it to form various body parts in multicellular organisms many such as some fungi, plants and animals. Can we find out names of some more unicellular organisms? Every multicellular organism has come from a single cell. How cells divide to produce cells of their own kind. All cells thus come from pre-existing cells. Activity 5.2 Middle dot. We can try preparing temporary mounts of leaf peels, tip of roots of onion or even peels of onions of different sizes. Middle dot. After performing the above activity, let us see what the answers to the following questions would be. A. Do all cells look alike in terms of shape and size? B. Do all cells look alike in structure? C. Could we find differences among cells from different parts of a plant body? D. What similarities could we find? Some organisms can also have cells of different kinds. Look at the following picture. It depicts some cells from the human body. Sperm, bone cell, smooth muscle cell, blood cells, ovum figure. 5.3 Various cells from the human body. More to know. We can try preparing temporary mounts of peels of onions of different sizes. What do we observe? Do we see similar structures or different structures? What are these structures? These structures look similar to each other. Together they form a big structure like an onion bulb. We find from this activity that onion bulbs of different sizes have similar small structures visible under a microscope. The cells of the onion peel will all look the same, regardless of the size of the onion they came from. These small structures that we see are the basic building units of the onion bulb. These structures are called cells. Not only onions, but all organisms that we observe around are made up of cells. However, there are also single cells that live on their own. Cells were first discovered by Robert Hooke in 1665. He observed the cells in a cork slice with the help of a primitive microscope. Leeuwenhoek 1674, with the improved microscope, discovered the free-living cells in pond water for the first time. It was Robert Brown in 1831 who discovered the nucleus in the cell. Perkins in 1839 coined the term protoplasm for the fluid substance of the cell. The cell theory, that all the plants and animals are composed of cells and that the cell is the basic unit of life, was presented by two biologists, Schleid in 1838 and Schwann 1839. The cell theory was further expanded by Virchow 1855 by suggesting that all cells arise from pre-existing cells. With the discovery of the electron microscope in 1940, it was possible to observe and understand the complex structure of the cell and its various organelles. The invention of magnifying lenses led to the discovery of the microscopic world. It is now known that a single cell may constitute a whole organism, as an amoeba. Nerve cell, fat cell. The fundamental unit of life 59. The shape and size of cells are related to the specific function they perform. Some cells, like amoeba, have changing shapes. In some cases the cell shape could be more or less fixed and peculiar for a particular type of cell. For example, nerve cells have a typical shape. Each living cell has the capacity to perform certain basic functions that are characteristic of all living forms. How does a living cell perform these basic functions? We know that there is a division of labor in multicellular organisms such as human beings. This means that different parts of the human body perform different functions. The human body has a heart to pump blood, a stomach to digest food, and so on. Similarly, division of labor is also seen within a single cell. In fact, each such cell has got certain specific components within it known as cell organelles. Each kind of cell organelle performs a special function, such as making new material in the cell, clearing up the waste material from the cell, and so on. A cell is able to live and perform all its functions because of these organelles. These organelles together constitute the basic unit called the cell. It is interesting that all cells are found to have the same organelles, no matter what their function is or what organism they are found in. Questions 1. Who discovered cells, and how to? Why is the cell called the structural and functional unit of life? 5.2 What is a cell made up of? What is the structural organization of a cell? We saw above that the cell has special components called organelles. How is a cell organized? If we study a cell under a microscope, we would come across three features in almost every cell: plasma membrane, nucleus, and cytoplasm. All activities inside the cell and interactions of the cell with its environment are possible due to these features. Let us see how. 5.2.1 Plasma membrane or cell membrane. This is the outermost covering of the cell that separates the contents of the cell from its external environment. The plasma membrane allows or permits the entry and exit of some materials in and out of the cell. It also prevents movement of some other materials. The cell membrane, therefore, is called a selectively permeable membrane. How does the movement of substances take place into the cell? How do substances move out of the cell? Some substances like carbon dioxide or oxygen can move across the cell membrane by a process called diffusion. We have studied the process of diffusion in earlier chapters. We saw that there is spontaneous movement of a substance from a region of high concentration to a region where its concentration is low. Something similar to this happens in cells when, for example, some substance like CO2, which is cellular waste and requires to be excreted out by the cell, accumulates in high concentrations inside the cell. In the cell's external environment, the concentration of CO2 is low as compared to that inside the cell. As soon as there is a difference of concentration of CO2 inside and outside a cell, CO2 moves out of the cell, from a region of high concentration, to a region of low concentration outside the cell by the process of diffusion. Similarly, O2 enters the cell by the process of diffusion when the level or concentration of O2 inside the cell decreases. Thus, diffusion plays an important role in gaseous exchange between the cells as well as the cell and its external environment. Water also obeys the law of diffusion. The movement of water molecules through such a selectively permeable membrane is called Q. SCIENCE 60 osmosis. The movement of water across the plasma membrane is also affected by the amount of substance dissolved in water. Thus, osmosis is the passage of water from a region of high water concentration through a selectively permeable membrane to a region of low water concentration till equilibrium is reached. What will happen if we put an animal cell or a plant cell into a solution of sugar or salt in water? One of the following three things could happen. 1. If the medium surrounding the cell has a higher water concentration than the cell, meaning that the outside solution is very dilute, the cell will gain water by osmosis. Such a solution is known as a hypotonic solution. Water molecules are free to pass across the cell membrane in both directions, but more water will come into the cell than will leave. The net overall result is that water enters the cell. The cell is likely to swell up. 2. If the medium has exactly the same water concentration as the cell, there will be no net movement of water across the cell membrane. Such a solution is known as an isotonic solution. Water crosses the cell membrane in both directions, but the amount going in is the same as the amount going out, so there is no overall movement of water. The cell will stay the same size. 3. If the medium has a lower concentration of water than the cell, meaning that it is a very concentrated solution, the cell will lose water by osmosis. Such a solution is known as a hypertonic solution. Again, water crosses the cell membrane in both directions, but this time more water leaves the cell than enters it. Therefore the cell will shrink. Thus, osmosis is a special case of diffusion through a selectively permeable membrane. Now let us try out the following activity. Activity 5.3 Osmosis with an egg. Remove the shell of an egg by dissolving it in dilute hydrochloric acid. The shell is mostly calcium carbonate. A thin outer skin now encloses the egg. Put the egg in pure water and observe after 5 minutes. What do we observe? The egg swells because water passes into it by osmosis. B. Place a similar de-shelled egg in a concentrated salt solution and observe for 5 minutes. The egg shrinks. Why? Water passes out of the egg solution into the salt solution because the salt solution is more concentrated. We can also try a similar activity with dried raisins or apricots. Activity 5.4 Middle. Put dried raisins or apricots in plain water and leave them for some time. Then place them into a concentrated solution of sugar or salt. You will observe the following. A. Each gains water and swells when placed in water. B. However, when placed in the concentrated solution it loses water, and consequently shrinks. Unicellular freshwater organisms and most plant cells tend to gain water through osmosis. Absorption of water by plant roots is also an example of osmosis. Thus, diffusion is important in exchange of gases and water in the life of a cell. In addition to this, the cell also obtains nutrition from its environment. Different molecules move in and out of the cell through a type of transport requiring use of energy. The plasma membrane is flexible and is made up of organic molecules called lipids and proteins. However, we can observe the structure of the plasma membrane only through an electron microscope. The flexibility of the cell membrane also enables the cell to engulf in food and other material from its external environment. Such processes are known as endocytosis. Amoeba acquires its food through such processes. The fundamental unit of life. 61 Activity 5.5 Middle. Find out about electron microscopes from resources in the school library or through the internet. Discuss it with your teacher. Questions 1. How do substances like CO2 and water move in and out of the cell? Discuss. 2. Why is the plasma membrane called a selectively permeable membrane? 5.2.2 Cell wall. Plant cells, in addition to the plasma membrane, have another rigid outer covering called the cell wall. The cell wall lies outside the plasma membrane. The plant cell wall is mainly composed of cellulose. Cellulose is a complex substance and provides structural strength to plants. When a living plant cell loses water through osmosis, there is shrinkage or contraction of the contents of the cell away from the cell wall. This phenomenon is known as plasmolysis. We can observe this phenomenon by performing the following activity. Activity 5.6 Middle dot. Mount the peel of a raw leaf in water on a slide and examine cells under the high power of a microscope. Note the small green granules, called chloroplasts. They contain a green substance called chlorophyll. Put a strong solution of sugar or salt on the mounted leaf on the slide. Wait for a minute and observe under a microscope. What do we see? Middle dot. Now place some raw leaves in boiling water for a few minutes. This kills the cells. Then mount one leaf on a slide and observe it under a microscope. Put a strong solution of sugar or salt on the mounted leaf on the slide. Wait for a minute and observe it again. What do we find? Did plasmolysis occur? Now what do we infer from this activity? It appears that only living cells, and not dead cells, are able to absorb water by osmosis. Cell walls permit the cells of plants, fungi and bacteria to withstand very dilute hypotonic external media without bursting. In such media the cells tend to take up water by osmosis. The cell swells, building up pressure against the cell wall. The wall exerts an equal pressure against the swollen cell. Because of their walls, such cells can withstand much greater changes in the surrounding medium than animal cells. 5.2.3 Nucleus. Remember the temporary mount of onion peel we prepared? We had put iodine solution on the peel. Why, what would we see if we tried observing the peel without putting the iodine solution? Try it and see what the difference is. Further, when we put iodine solution on the peel, did each cell get evenly colored according to their chemical composition? Different regions of cells get colored differentially. Some regions appear darker than other regions. Apart from iodine solution, we could also use safranin solution or methylene blue solution to stain the cells. We have observed cells from an onion. Let us now observe cells from our own body. Activity 5.7 Middle dot. Let us take a glass slide with a drop of water on it. Using an ice cream spoon, gently scrape the inside surface of the cheek. Does any material get stuck on the spoon? With the help of a needle we can transfer this material and spread it evenly on the glass slide kept ready for this. To color the material we can put a drop of methylene blue solution on it. Now the material is ready for observation under microscope. Do not forget to put a cover slip on it. Middle dot. What do we observe? What is the shape of the cells we see? Draw it on the observation sheet. Q. SCIENCE 62 Middle dot. Was there a darkly colored, spherical or oval, dot-like structure near the center of each cell? This structure is called nucleus. Were there similar structures in onion peel cells? The nucleus has a double-layered covering called nuclear membrane. The nuclear membrane has pores which allow the transfer of material from inside the nucleus to its outside, that is, to the cytoplasm, which we will talk about in section 5.2.4. The nucleus contains chromosomes, which are visible as rod-shaped structures only when the cell is about to divide. Chromosomes contain information for inheritance of characters from parents to next generation in the form of DNA deoxyribonucleic acid molecules. Chromosomes are composed of DNA and protein. DNA molecules contain the information necessary for constructing and organizing cells. Functional segments of DNA are called genes. In a cell which is not dividing, this DNA is present as part of chromatin material. Chromatin material is visible as entangled mass of thread-like structures. Whenever the cell is about to divide, the chromatin material gets organized into chromosomes. The nucleus plays a central role in cellular reproduction, the process by which a single cell divides and forms two new cells. It also plays a crucial part, along with the environment, in determining the way the cell will develop and what form it will exhibit at maturity, by directing the chemical activities of the cell. In some organisms like bacteria, the nuclear region of the cell may be poorly defined due to the absence of a nuclear membrane. Such an undefined nuclear region containing only nucleic acids is called a nucleoid. Such organisms, whose cells lack a nuclear membrane, are called prokaryotes, proprimitive or primary. Karyote carry a nucleus. Organisms with cells having a nuclear membrane are called eukaryotes. Prokaryotic cells, see figure 5.4, also lack most of the other cytoplasmic organelles present in eukaryotic cells. Many of the functions of such organelles are also performed by poorly organized parts of the cytoplasm, see section 5.2.4. The chlorophyll in photosynthetic prokaryotic bacteria is associated with membranous vesicles, bag-like structures, but not with plastids as in eukaryotic cells, see section 5.2.5. Ribosomes, plasma membrane, cell wall, nucleoid, figure 5.4, prokaryotic cell 5.2.4, cytoplasm. When we look at the temporary mounts of onion peel as well as human cheek cells, we can see a large region of each cell enclosed by the cell membrane. This region takes up very little stain. It is called the cytoplasm. The cytoplasm is a fluid content inside the plasma membrane. It also contains many specialized cell organelles. Each of these organelles performs a specific function for the cell. Cell organelles are enclosed by membranes. In prokaryotes, beside the absence of a defined nuclear region, the membrane-bound cell organelles are also absent. On the other hand, the eukaryotic cells have nuclear membrane as well as membrane-enclosed organelles. The significance of membranes can be illustrated with the example of viruses. Viruses lack any membranes and hence do not show characteristics of life until they enter a living body and use its cell machinery to multiply. The fundamental unit of life. 63. Question 1. Fill in the gaps in the following table illustrating differences between prokaryotic and eukaryotic cells. Prokaryotic cell, eukaryotic cell. 1. Size, generally 1. Size, generally small 1, 10 microsyn m, large 5100 microsyn m, 1 microsyn m, 106 meters. 2. Nuclear region, 2. Nuclear region, well defined and surrounded by a and known as nuclear membrane. 3. Chromosome, 3. More than one single chromosome. 4. Membrane-bound. 4. Cell organelles absent. 5.2.5 Cell organelles. Every cell has a membrane around it to keep its own contents separate from the external environment. Large and complex cells, including cells from multicellular organisms, need a lot of chemical activities to support their complicated structure and function. To keep these activities of different kinds separate from each other, these cells use membrane-bound little structures or organelles within themselves. This is one of the features of the eukaryotic cells that distinguish them from prokaryotic cells. Some of these organelles are visible only with an electron microscope. We have talked about the nucleus in a previous section. Some important examples of cell organelles which we will discuss now are endoplasmic reticulum, Golgi apparatus, lysosomes, mitochondria and plastids. They are important because they carry out some very crucial functions in cells. 5.2.5 Endoplasmic reticulum ER. The endoplasmic reticulum ER is a large network of membrane-bound tubes and sheets. It looks like long tubules or round or oblong bags, vesicles. The ER membrane is similar in structure to the plasma membrane. There are two types of ER: rough endoplasmic reticulum (RER) and smooth endoplasmic reticulum (SER). RER looks rough under a microscope because it has particles called ribosomes attached to its surface. The ribosomes, which are present in all active cells, are the sites of protein manufacture. The manufactured proteins are then sent to various places in the cell depending on need. Using the ER This ER helps in the manufacture of fat molecules, or lipids, important for cell function. Some of these proteins and lipids help in building the cell membrane. This process is known as membrane biogenesis. Some other proteins and lipids function as enzymes and hormones. Although the ER varies greatly in appearance in different cells, it always forms a network system. Q Figure 5.5, Animal Cell Thus, one function of the ER is to serve as channels for the transport of materials, especially proteins, between various regions of the cytoplasm or between the cytoplasm and the nucleus. The ER also functions as a cytoplasmic framework, providing a surface. SCIENCE 64 Camillo Golgi was born at Corteno near Brescia in 1843. He studied medicine at the University of Pavia. After graduating in 1865, he continued to work in Pavia at the Hospital of St. Matteo. At that time most of his investigations were concerned with the nervous system. In 1872 he accepted the post of Chief Medical Officer at the Hospital for the Chronically Sick at Obbia di Grasso. He first started his investigations into the nervous system in a little kitchen of this hospital, which he had converted into a laboratory. However, the work of greatest importance, which Golgi carried out, was a revolutionary method of staining individual nerve and cell structures. This method is referred to as the black reaction. This method uses a weak solution of silver nitrate and is particularly valuable in tracing the processes and most delicate ramifications of cells. All through his life, he continued to work on these lines, modifying and improving this technique. Golgi received the highest honors and awards in recognition of his work. He shared the Nobel Prize in 1906 with Santiago Ramón y Cajal for their work on the structure of the nervous system. 5.2.53 Lysosomes. Structurally, lysosomes are membrane-bound sacs filled with digestive enzymes. These enzymes are made by RR. Lysosomes are a kind of waste disposal system of the cell. These help to keep the cell clean by digesting any foreign material as well as worn-out cell organelles. Foreign materials entering the cell, such as bacteria or food, as well as old organelles, end up in the lysosomes, which break complex substances into simpler substances. Lysosomes are able to do this because they contain powerful digestive enzymes capable of breaking down all organic material. During the disturbance in cellular metabolism, for example, when the cell gets Figure 5.6, plant cell for some of the biochemical activities of the cell. In the liver cells of the group of animals called vertebrates, see Chapter 7, CER plays a crucial role in detoxifying many poisons and drugs. 5.2.52 Golgi apparatus. The Golgi apparatus, first described by Camillo Golgi, consists of a system of membrane-bound vesicles, flattened sacs arranged approximately parallel to each other in stacks called cisterns. These membranes often have connections with the membranes of ER and therefore constitute another portion of a complex cellular membrane system. The material synthesized near the ER is packaged and dispatched to various targets inside and outside the cell through the Golgi apparatus. Its functions include the storage, modification and packaging of products and vesicles. In some cases, complex sugars may be made from simple sugars in the Golgi apparatus. The Golgi apparatus is also involved in the formation of lysosomes. See 5.2.53. The fundamental unit of life. 65 Damaged, lysosomes may burst and the enzymes digest their own cell. Therefore, lysosomes are also known as the suicide bags of a cell. 5.2.55 Mitochondria. Mitochondria are known as the powerhouses of the cell. Mitochondria have two membrane coverings. The outer membrane is porous while the inner membrane is deeply folded. These folds increase surface area for ATP-generating chemical reactions. The energy required for various chemical activities needed for life is released by mitochondria in the form of ATP adenosine triphosphate molecules. ATP is known as the energy currency of the cell. The body uses energy stored in ATP for making new chemical compounds and for mechanical work. Mitochondria are strange organelles in the sense that they have their own DNA and ribosomes. Therefore, mitochondria are able to make some of their own proteins. 5.2.5v Plastids. Plastids are present only in plant cells. There are two types of plastids: chromoplasts, colored plastids, and leucoplasts, white or colorless plastids. Chromoplasts containing the pigment chlorophyll are known as chloroplasts. Chloroplasts are important for photosynthesis in plants. Chloroplasts also contain various yellow or orange pigments in addition to chlorophyll. Leucoplasts are primarily organelles in which materials such as starch, oils and protein granules are stored. The internal organization of the chloroplast consists of numerous membrane layers embedded in a material called the stroma. These are similar to mitochondria in external structure. Like the mitochondria, plastids also have their own DNA and ribosomes. 5.2.56 Vacuoles. Vacuoles are storage sacs for solid or liquid contents. Vacuoles are small-sized in animal cells, while plant cells have very large vacuoles. The central vacuole of some plant cells may occupy 50-90% of the cell volume. In plant cells, vacuoles are full of cell sap and provide turgidity and rigidity to the cell. Many substances of importance in the life of the plant cell are stored in vacuoles. These include amino acids, sugars, various organic acids, and some proteins. In single-celled organisms like amoeba, the food vacuole contains the food items that the amoeba has consumed. In some unicellular organisms, specialized vacuoles also play important roles in expelling excess water and some wastes from the cell. Questions 1. Can you name the two organelles we have studied that contain their own genetic material? 2. If the organization of a cell is destroyed due to some physical or chemical influence, what will happen? 3. Why are lysosomes known as suicide bags? 4. Where are proteins synthesized inside the cell? Each cell thus acquires its structure and ability to function because of the organization of its membrane and organelles in specific ways. The cell thus has a basic structural organization. This helps the cells to perform functions like respiration, obtaining nutrition, and clearing of waste material, or forming new proteins. Thus, the cell is a fundamental structural unit of living organisms. It is also the basic functional unit of life. Cell division. New cells are formed in organisms in order to grow, to replace old, dead and injured cells, and to form gametes required for reproduction. The process by which new cells are made is called cell division. There are two main types of cell division, mitosis and meiosis. The process of cell division by which most of the cells divide for growth is called mitosis. In this process, each cell called mother cell Q SCIENCE 66. What you have learned. The fundamental organizational unit of life is the cell. Cells are enclosed by a plasma membrane composed of lipids and proteins. The cell membrane is an active part of the cell. It regulates the movement of materials between the ordered interior of the cell and the outer environment. In plant cells, a cell wall composed mainly of cellulose is located outside the cell membrane. The presence of the cell wall enables the cells of plants, fungi and bacteria to exist in hypotonic media without bursting. The nucleus in eukaryotes is separated from the cytoplasm by double-layered membrane, and it directs the life processes of the cell. The ER functions both as a passageway for intracellular transport and as a manufacturing surface. The Golgi apparatus consists of stacks of membrane-bound vesicles that function in the storage, modification and packaging of substances manufactured in the cell. Most plant cells have large membranous organelles called plastids, which are of two types: chromoplasts and leucoplasts. Figure 5.7, mitosis. Figure 5.8, meiosis divides to form two identical daughter cells. Figure 5.7. The daughter cells have the same number of chromosomes as mother cell. It helps in growth and repair of tissues in organisms. Specific cells of reproductive organs or tissues in animals and plants divide to form gametes, which after fertilization give rise to offspring. They divide by a different process called meiosis, which involves two consecutive divisions. When a cell divides by meiosis, it produces 4 new cells instead of just 2. Figure 5.8. The new cells only have half the number of chromosomes than that of the mother cells. Can you think as to why the chromosome number has reduced to half in daughter cells? The fundamental unit of life 67 chromoplasts that contain chlorophyll are called chloroplasts, and they perform photosynthesis. The primary function of leucoplasts is storage. Most mature plant cells have a large central vacuole that helps to maintain the turgidity of the cell and stores important substances including waste. Prokaryotic cells have no membrane-bound organelles. Their chromosomes are composed of only nucleic acid, and they have only very small ribosomes as organelles. Cells in organisms divide for growth of body, for repulsing dead cells, and for forming gametes for reproduction. Exercises 1. Make a comparison and write down ways in which plant cells are different from animal cells. 2. How is a prokaryotic cell different from a eukaryotic cell? 3. What would happen if the plasma membrane ruptures or breaks down? 4. What would happen to the life of a cell if there was no Golgi apparatus? 5. Which organelle is known as the powerhouse of the cell? 6. Where do the lipids and proteins constituting the cell membrane get synthesized? 7. How does an amoeba obtain its food? 8. What is osmosis? 9. Carry out the following osmosis experiment. Take 4 peeled potato halves and squeeze each one out to make potato cups. One of these potato cups should be made from a boiled potato. Put each potato cup in a trough containing water. Now, A keep cup empty. B. Put 1 teaspoon sugar in cup B. C. Put 1 teaspoon salt in cup C. D. Put 1 teaspoon sugar in the boiled potato cup D. Keep these for 2 hours. Then observe the 4 potato cups and answer the following. I explain why water gathers in the hollowed portion of B and C. 2. Why is potato necessary for this experiment? 3. Explain why water does not gather in the hollowed out portions of A and D. 10. Which type of cell division is required for growth and repair of body, and which type is involved in formation of gametes? From the last chapter, we recall that all living organisms are made of cells. In unicellular organisms, a single cell performs all basic functions. For example, in amoeba, a single cell carries out movement, intake of food, gaseous exchange and excretion. But in multicellular organisms there are millions of cells. Most of these cells are specialized to carry out specific functions. Each specialized function is taken up by a different group of cells. Since these cells carry out only a particular function, they do it very efficiently. In human beings, muscle cells contract and relax to cause movement, nerve cells carry messages, blood flows to transport oxygen, food, hormones and waste material and so on. In plants, vascular tissues conduct food and water from one part of the plant to other parts. So, multicellular organisms show division of labor. Cells specializing in one function are often grouped together in the body. This means that a particular function is carried out by a cluster of cells at a definite place in the body. This cluster of cells, called a tissue, is arranged and designed so as to give the highest possible efficiency of function. Blood, phloem and muscle are all examples of tissues. A group of cells that are similar in structure and or work together to achieve a particular function forms a tissue. 6.1 Are plants and animals made of same types of tissues? Let us compare their structure and functions. Do plants and animals have the same structure? Do they both perform similar functions? There are noticeable differences between the two. Plants are stationary or fixed, they don't move. Since they have to be upright, they have a large quantity of supportive tissue. The supportive tissue generally has dead cells. Animals, on the other hand, move around in search of food, mates and shelter. They consume more energy as compared to plants. Most of the tissues they contain are living. Another difference between animals and plants is in the pattern of growth. The growth in plants is limited to certain regions, while this is not so in animals. There are some tissues in plants that divide throughout their life. These tissues are localized in certain regions. Based on the dividing capacity of the tissues, various plant tissues can be classified as growing or meristematic tissue and permanent tissue. Cell growth in animals is more uniform. So, there is no such demarcation of dividing and non-dividing regions in animals. The structural organization of organs and organ systems is far more specialized and localized in complex animals than even in very complex plants. This fundamental difference reflects the different modes of life pursued by these two major groups of organisms, particularly in their different feeding methods. Also, they are differently adapted for a sedentary existence on one hand, plants, and active locomotion on the other, animals, contributing to this difference in organ system design. It is with reference to these complex animal and plant bodies that we will now talk about the concept of tissues in some detail. 6 Issues Chapter Lateral meristeme. Questions 1. What is a tissue? 2. What is the utility of tissues in multicellular organisms? 6.2 Plant tissues. 6.2.1 Meristematic tissue. From the above observations, answer the following questions. 1. Which of the two onions has longer roots? Why? 2. Do the roots continue growing even after we have removed their tips? 3. Why would the tips stop growing in jar 2 after we cut them? The growth of plants occurs only in certain specific regions. This is because the dividing tissue, also known as meristematic tissue, is located only at these points. Depending on the region where they are present, meristematic tissues are classified as apical, lateral and intercalary. Figure 6.2. New cells produced by meristeme are initially like those of meristeme itself, but as they grow and mature, their characteristics slowly change and they become differentiated as components of other tissues. Figure 6.1. Growth of roots in onion bulbs. Activity 6.1 Take 2 glass jars and fill them with water. Now, take 2 onion bulbs and place one on each jar, as shown in figure 6.1. Observe the growth of roots in both the bulbs for a few days. Measure the length of roots on day 1, 2 and 3. On day 4, cut the root tips of the onion bulb in jar 2 by about 1 centimeter. After this, observe the growth of roots in both the jars and measure their lengths each day for 5 more days and record the observations in tables. Like the table below, length day 1, day 2, day 3, day 4, day 5. Jar 1, jar 2. Apical meristeme is present at the growing tips of stems and roots and increases the length of the stem and the root. The girth of the stem or root increases due to lateral meristeme. Cambium. Intercalary meristeme seen in some plants is located near the node. Figure 6.2. Location of meristematic tissue in plant body. Jar 1, jar 2 tissues. 69 Apical meristeme. Intercalary meristeme. SCIENCE 70 Cuticle epidermis. Collenchyma parenchyma vascular bundle. Xylem. Figure 6.3. Section of the stem cells of meristematic tissue are very active. They have dense cytoplasm, thin cellulose walls and prominent nuclei. They lack vacuoles. Can we think why they would lack vacuoles? You might want to refer to the functions of vacuoles in the chapter on cells. 6.2.2 Permanent tissue. What happens to the cells formed by meristematic tissue? They take up a specific role and lose the ability to divide. As a result, they form a permanent tissue. This process of taking up a permanent shape, size, and a function is called differentiation. Differentiation leads to the development of various types of permanent tissues. 3. Can we think of reasons why there would be so many types of cells? We can also try to cut sections of plant roots. We can even try cutting sections of root and stem of different plants. 6.2.2 Simple permanent tissue. A few layers of cells beneath the epidermis are generally simple permanent tissue. Parenchyma is the most common simple permanent tissue. It consists of relatively unspecialized cells with thin cell walls. They are living cells. They are usually loosely arranged, thus large spaces between cells. Intercellular spaces are found in this tissue figure. 6.4a. This tissue generally stores food. Activity 6.2 Take a plant stem and with the help of your teacher cut into very thin slices or sections. Now, stain the slices with safranin. Place one neatly cut section on a slide, and put a drop of glycerin. Cover with a cover slip and observe under a microscope. Observe the various types of cells and their arrangement. Compare it with figure 6.3. Now, answer the following on the basis of your observation. 1. Are all cells similar in structure? 2. How many types of cells can be seen in some situations? It contains chlorophyll and performs photosynthesis, and then it is called chlorenchyma. In aquatic plants, large air cavities are present in parenchyma to help them float. Such a parenchyma type is called arenchyma. The flexibility in plants is due to another permanent tissue, collenchyma. It allows bending of various parts of a plant like tendrils and stems of climbers without breaking. It also provides mechanical support. We can find this tissue in leaf stalks below the epidermis. The cells of this tissue are living, elongated and irregularly thickened at the corners. There is very little intercellular space. Figure 6.4b. Tissues 71. Figure 6.4. Various types of simple tissues. A parenchyma. B. Collenchyma. C. Sclerenchyma. I. Transverse section. 2. Longitudinal section. Yet another type of permanent tissue is sclerenchyma. It is a tissue which makes the plant hard and stiff. We have seen the husk of a coconut. It is made of sclerenchymatous tissue. The cells of this tissue are dead. They are long and narrow as the walls are thickened due to lignin. Often these walls are so thick that there is no internal space inside the cell. Figure 6.4c. This tissue is present in stems, around vascular bundles, in the veins of leaves and in the hard covering of seeds and nuts. It provides strength to the plant parts. Activity 6.3 Take a freshly plucked leaf of royo. Stretch and break it by applying pressure. While breaking it, keep it stretched gently so that some peel or skin projects out from the cut. Remove this peel and put it in a petri dish filled with water. Add a few drops of safranin. Wait for a couple of minutes and then transfer it onto a slide. Gently place a cover slip over it. Observe under microscope. What you observe is the outermost layer of cells, called epidermis. The epidermis is usually made of a single layer of cells. In some plants living in very dry habitats, the epidermis may be thicker since protection against water loss is critical. The entire surface of a plant has an outer covering epidermis. It protects all the parts of the plant. Epidermal cells on the areola. Intercellular spaces. B. Wall thickenings. Nucleus. Vacuole cell wall. Narrow lumen. Lignified thick wall. C2ci. Thick lignified walls. Figure 6.5. Guard cells and epidermal cells. A lateral view. B. Surface view. A B. Guard cell. Stoma. Epidermal cell. Guard cells. Parts of the plant often secrete a waxy, water-resistant layer on their outer surface. This aids in protection against loss of water, mechanical injury and invasion by parasitic fungi. Since it has a protective role to play, cells of epidermal tissue form a continuous layer without intercellular spaces. Most epidermal cells are relatively flat. Often their outer and side walls are thicker than the inner wall. We can observe small pores here and there in the epidermis of the leaf. These pores are called stomata. Figure 6.5. Stomata are enclosed by two kidney-shaped cells called guard cells. They are necessary for exchanging gases with the atmosphere. Transpiration. Loss of water in the form of water vapor also takes place through stomata. SCIENCE 72. Recall which gas is required for photosynthesis. Find out the role of transpiration in plants. Epidermal cells of the roots, whose function is water absorption, commonly bear long hair-like parts that greatly increase the total absorptive surface area. In some plants like desert plants, epidermis has a thick waxy coating of cut-in chemical substance with waterproof quality on its outer surface. Can we think of a reason for this? Is the outer layer of a branch of a tree different from the outer layer of a young stem as plants grow older? The outer protective tissue undergoes certain changes. A strip of secondary meristeme located in the cortex forms layers of cells which constitute the cork. Cells of cork are dead and compactly arranged without intercellular spaces. Figure 6.6. They also have a substance called suberin in their walls that makes them impervious to gases and water. Is a distinctive feature of the complex plants, one that has made possible their survival in the terrestrial environment. In Figure 6.3 showing a section of stem, can you see different types of cells in the vascular bundle? Xylem consists of tracheids, vessels, xylem parenchyma. Figure 6.7a, b, c and xylem fibers. Tracheids and vessels have thick walls, and many are dead cells when mature. Tracheids and vessels are tubular structures. This allows them to transport water and minerals vertically. The parenchyma stores food. Xylem fibers are mainly supportive in function. Phloem is made up of 5 types of cells: sieve cells, sieve tubes, companion cells, phloem fibers and the phloem parenchyma. Figure 6.7d. Sieve tubes are tubular cells with perforated walls. Phloem transports food from leaves to other parts of the plant. Except phloem fibers, other phloem cells are living cells. 6.2.22 Complex permanent tissue. The different types of tissues we have discussed until now are all made of one type of cells, which look like each other. Such tissues are called simple permanent tissue. Yet another type of permanent tissue is complex tissue. Complex tissues are made of more than one type of cells. All these cells coordinate to perform a common function. Xylem and phloem are examples of such complex tissues. They are both conducting tissues and constitute a vascular bundle. Vascular tissue. Figure 6.6. Protective tissue. Cork cells, ruptured epidermis, nucleus, cytoplasm, pits, pit, tracheid, B vessel, C xylem parenchyma. Figure 6.7. Types of complex tissue. Sieve plate, sieve tube, phloem parenchyma, companion cell, D section of phloem. Tissues. 73 Questions. 1. Name types of simple tissues. 2. Where is apical meristeme found? 3. Which tissue makes up the husk of coconut? 4. What are the constituents of phloem? 6.3 Animal tissues. When we breathe, we can actually feel the movement of our chest. How do these body parts move? For this we have specialized cells called muscle cells. Figure 6.8. The contraction and relaxation of these cells result in movement. Q. Figure 6.8. Location of muscle fibers. Smooth muscle fibers. Smooth muscle fiber cell nucleus. During breathing we inhale oxygen. Where does this oxygen go? It is absorbed in the lungs and then is transported to all the body cells through blood. Why would cells need oxygen? The functions of mitochondria we studied earlier provide a clue to this question. Blood flows and carries various substances from one part of the body to the other. For example, it carries oxygen and food to all cells. It also collects waste from all parts of the body and carries them to the liver and kidney for disposal. Blood and muscles are both examples of tissues found in our body. On the basis of the functions they perform, we can think of different types of animal tissues, such as epithelial tissue, connective tissue, muscular tissue and nervous tissue. Blood is a type of connective tissue, and muscle forms muscular tissue. 6.3.1 Epithelial tissue. The covering or protective tissues in the animal body are epithelial tissues. Epithelium covers most organs and cavities within the body. It also forms a barrier to keep different body systems separate. The skin, the lining of the mouth, the lining of blood vessels, lung alveoli and kidney tubules are all made of epithelial tissue. Epithelial tissue cells are tightly packed and form a continuous sheet. They have only a small amount of cementing material between them and almost no intercellular spaces. Obviously, anything entering or leaving the body must cross at least one layer of epithelium. As a result, the permeability of the cells of various epithelia play an important role in regulating the exchange of materials between the body and the external environment, and also between different parts of the body. Regardless of the type, all epithelium is usually separated from the underlying tissue by an extracellular fibrous basement membrane. Different epithelia. Figure 6.9 show differing structures that correlate with their unique functions. For example, in cells lining blood vessels or lung alveoli, where transportation of substances occurs through a selectively permeable surface, there is a simple flat kind. Figure 6.9, different types of epithelial tissues of skin. Simple squamous epithelial cells are extremely thin and flat and form a delicate lining. The oesophagus and the lining of the mouth are also covered with squamous epithelium. The skin, which protects the body, is also made of squamous epithelium. Skin epithelial cells are arranged in many layers to prevent wear and tear. Since they are arranged in a pattern of layers, the epithelium is called stratified squamous epithelium. Where absorption and secretion occur, as in the inner lining of the intestine, tall epithelial cells are present. This columnar, meaning pillar-like epithelium, facilitates movement across the epithelial barrier. In the respiratory tract, the columnar epithelial tissue also has cilia, which are hair-like projections on the outer surfaces of epithelial cells. These cilia can move, and their movement pushes the mucus forward to clear it. This type of epithelium is thus ciliated columnar epithelium. Cuboidal epithelium with cube-shaped cells forms the lining of kidney tubules and ducts of salivary glands, where it provides mechanical support. Epithelial cells often acquire additional specialization as gland cells, which can secrete substances at the epithelial surface. Sometimes a portion of the epithelial tissue folds inward, and a multicellular gland is formed. This is glandular epithelium. 6.3.2 Connective tissue. Blood is a type of connective tissue. Why would it be called connective tissue? A clue is provided in the introduction of this chapter. Now, let us look at this type of tissue in some more detail. The cells of connective tissue are loosely spaced and embedded in an intercellular matrix. Figure 6.10. The matrix may be jelly-like, fluid, dense or rigid. The nature of matrix differs in concordance with the function of the particular connective tissue. Activity 6.4 Take a drop of blood on a slide and observe different cells present in it under a microscope. Of epithelium. This is called the simple squamous epithelium. Squama means scalous, squamous B stratified, squamous C cuboidal D columnar ciliated. Tissues 75 Blood has a fluid liquid matrix called plasma. in which red blood corpuscles RBCS, white blood corpuscles WBCS and platelets are suspended. The plasma contains proteins, salts and hormones. Blood flows and transports gases, digested food, hormones and waste materials to different parts of the body. Bone is another example of a connective tissue. It forms the framework that supports the body. It also anchors the muscles and supports the main organs of the body. It is a strong and non-flexible tissue. What would be the advantage of these properties for bone functions? Bone cells are embedded in a hard matrix that is composed of calcium and phosphorus compounds. Two bones can be connected to each other by another type of connective tissue called the ligament. This tissue is very elastic. It has considerable strength. Ligaments contain very little matrix and connect bones with bones. Tendons connect muscles to bones and are another type of connective tissue. Tendons are fibrous tissue with great strength but limited flexibility. Another type of connective tissue, cartilage, has widely spaced cells. The solid matrix is composed of proteins and sugars. Cartilage smoothens bone surfaces at joints and is also present in the nose, ear, trachea and larynx. We can fold the cartilage of the ears, but we cannot bend the bones in our arms. Think of how the two tissues are different. Areolar connective tissue is found between the skin and muscles, around blood vessels and nerves and in the bone marrow. It fills the space inside the organs, supports internal organs and helps in repair of tissues. Where are fats stored in our body? Fat storing adipose tissue is found below the skin and between internal organs. The cells of this tissue are filled with fat globules. Storage of fats also lets it act as an insulator. 6.3.3 Muscular tissue. Muscular tissue consists of elongated cells, also called muscle fibers. This tissue is responsible for movement in our body. Figure 6.10, Types of connective tissues, A. Types of blood cells, B. Compact bone, C. Hyaline cartilage, D. Areolar tissue, E. Adipose tissue. A. Different white blood corpuscles. Neutrophil, polynuclear leukocyte, basophil, eosinophil, nucleus, cytoplasm, lymphocyte, monocyte, platelets. Haversian canal contains blood vessels and nerve fibers. Canaliculus contains slender process of bone cell or osteocyte. Hyaline matrix, chondrocyte, red blood corpuscle. BC reticular fiber, fibroblast, macrophage, collagen fiber, mast cell, plasma cell. D. Fat droplet nucleus, adipocyte. E. Figure 6.11a. These muscles are also called skeletal muscles as they are mostly attached to bones and help in body movement. Under the microscope, these muscles show alternate light and dark bands or striations when stained appropriately. As a result, they are also called striated muscles. The cells of this tissue are long, cylindrical, unbranched and multinucleate, having many nuclei. The movement of food in the alimentary canal or the contraction and relaxation of blood vessels are involuntary movements. We cannot really start them or stop them simply by wanting to do so. Smooth muscles. Figure 6.11b or involuntary muscles control such movements. They are also found in the iris of the eye, in ureters and in the bronchi of the lungs. The cells are long with pointed ends, spindle-shaped and uninucleate, having a single nucleus. They are also called unstriated muscles. Why would they be called that? The muscles of the heart show rhythmic contraction and relaxation throughout life. These involuntary muscles are called cardiac muscles. Figure 6.11c. Heart muscle cells are cylindrical, branched and uninucleate. Activity 6.5 Compare the structures of different types of muscular tissues. Note down their shape, number of nuclei and position of nuclei within the cell in the Table 6.1. Table 6.1 features striated smooth cardiac shape, number of nuclei, position of nuclei. 6.3.4 Nervous tissue. All cells possess the ability to respond to stimuli. However, cells of the nervous tissue are highly specialized for being stimulated, and muscles contain special proteins called contractile proteins, which contract and relax to cause movement. Figure 6.11, Types of muscles. Fibers: A, striated muscle, B, smooth muscle, C, cardiac muscle. We can move some muscles by conscious will. Muscles present in our limbs move when we want them to, and stop when we so decide. Such muscles are called voluntary muscles. C, striations. Nucleus: spindle-shaped muscle cell. Nucleus. B, nucleus. Striations. A. Processes called dendrites. An individual nerve cell may be up to a meter long. Many nerve fibers bound together by connective tissue make up a nerve. The signal that passes along the nerve fiber is called a nerve impulse. Nerve impulses allow us to move our muscles when we want to. The functional combination of nerve and muscle tissue is fundamental to most animals. This combination enables animals to move rapidly in response to stimuli. Questions 1. Name the tissue responsible for movement in our body. 2. What does a neuron look like? 3. Give 3 features of cardiac muscles. 4. What are the functions of areolar tissue? Q, nucleus, dendrite, axon, nerve ending, cell body. Figure 6.12, neuron, unit of nervous tissue then transmitting the stimulus very rapidly from one place to another within the body. The brain, spinal cord and nerves are all composed of the nervous tissue. The cells of this tissue are called nerve cells or neurons. A neuron consists of a cell body with a nucleus and cytoplasm, from which long thin hair-like parts arise. Figure 6.12. Usually each neuron has a single long part process, called the axon, and many short, branched parts. What you have learned. Middle. Tissue is a group of cells similar in structure and function. Middle. Plant tissues are of 2 main types, meristematic and permanent. Middle. Meristematic tissue is the dividing tissue present in the growing regions of the plant. Middle. Permanent tissues are derived from meristematic tissue once they lose the ability to divide. They are classified as simple and complex tissues. Middle. Parenchyma, collenchyma and sclerenchyma are 3 types of simple tissues. Xylem and phloem are types of complex tissues. Middle. Animal tissues can be epithelial, connective, muscular and nervous tissue. Middle. Depending on shape and function, epithelial tissue is classified as squamous, cuboidal, columnar, ciliated and glandular. SCIE 78. Middle. The different types of connective tissues in our body include areolar tissue, adipose tissue, bone, tendon, ligament, cartilage and blood. Middle. Striated, unstriated and cardiac are 3 types of muscle tissues. Middle. Nervous tissue is made of neurons that receive and conduct impulses. Exercises 1. Define the term tissue. 2. How many types of elements together make up the xylem tissue? Name them. 3. How are simple tissues different from complex tissues in plants? 4. Differentiate between parenchyma, collenchyma and sclerenchyma on the basis of their cell wall. 5. What are the functions of the stomata? 6. Diagrammatically show the difference between the 3 types of muscle fibers. 7. What is the specific function of the cardiac muscle? 8. Differentiate between striated, unstriated and cardiac muscles on the basis of their structure and site location in the body. 9. Draw a labeled diagram of a neuron. 10. Name the following. A tissue that forms the inner lining of our mouth. B. Tissue that connects muscle to bone in humans. C. Tissue that transports food in plants. D. Tissue that stores fat in our body. E. Connective tissue with all fluid matrix. F. Tissue present in the brain. 11. Identify the type of tissue in the following: skin, bark of tree, bone, lining of kidney tubule, vascular bundle. Tissues. 79. 12. Name the regions in which parenchyma tissue is present. 13. What is the role of epidermis in plants? 14. How does the cork act as a protective tissue? 15. Complete the following chart. Have you ever thought of the multitude of life forms that surround us? Each organism is different from the other to a lesser or greater extent. For instance, consider yourself and a friend. Middle dot. Are you both of the same height? Middle dot. Does your nose look exactly like your friend's nose? Middle dot. Is your hand span the same as your friend's? However, if we were to compare ourselves and our friends with a monkey, what would we say? Obviously, we and our friends have a lot in common when we compare ourselves with a monkey. But suppose we were to add a cow to the comparison, we would then think that the monkey has a lot more in common with us than with the cow. Activity 7.1 Middle dot. We have heard of Desi cows and Jersey cows. Middle dot. Does a Desi cow look like a Jersey cow? Middle dot. Do all Desi cows look alike? Middle dot. Will we be able to identify a Jersey cow in a crowd of Desi cows that don't look like each other? Middle dot. What is the basis of our identification in this activity? We had to decide which characteristics were more important in forming the desired category. Hence, we were also deciding which characteristics could be ignored. Now, think of all the different forms in which life occurs on Earth. On one hand we have microscopic bacteria of a few micrometer in size, while on the other hand we have blue whale and redwood trees of California of approximate sizes of 30 meters and 100 meters respectively. Some pine trees live for thousands of years, while insects like mosquitoes die within a few days. Life also ranges from colorless or even transparent worms to brightly colored birds and flowers. This bewildering variety of life around us has evolved on the Earth over millions of years. However, we do not have more than a tiny fraction of this time to try and understand all these living organisms, so we cannot look at them one by one. Instead, we look for similarities among the organisms, which will allow us to put them into different classes and then study different classes or groups as a whole. In order to make relevant groups to study the variety of life forms, we need to decide which characteristics decide more fundamental differences among organisms. This would create the main broad groups of organisms. Within these groups, smaller subgroups will be decided by less important characteristics. Questions 1. Why do we classify organisms? 2. Give 3 examples of the range of variations that you see in life forms around you. 7.1 What is the basis of classification? Attempts at classifying living things into groups have been made since time immemorial. Greek thinker Aristotle classified animals according to whether they lived on Q7 diversity in living of in giving organisms land, in water or in the air. This is a very simple way of looking at life, but misleading too. For example, animals that live in the sea include corals, whales, octopuses, starfish and sharks. We can immediately see that these are very different from each other in numerous ways. In fact, habitat is the only point they share in common. This is not an appropriate way of making groups of organisms to study and think about. We therefore need to decide which characteristics to be used as the basis for making the broadest divisions. Then we will have to pick the next set of characteristics for making subgroups within these divisions. This process of classification within each group can then continue using new characteristics each time. Before we go on, we need to think about what is meant by characteristics. When we are trying to classify a diverse group of organisms, we need to find ways in which some of them are similar enough to be thought of together. These ways, in fact, are details of appearance or behavior, in other words, form and function. What we mean by a characteristic is a particular feature or a particular function. That most of us have 5 fingers on each hand is thus a characteristic. That we can run, but the banyan tree cannot, is also a characteristic. Now, to understand how some characteristics are decided as being more fundamental than others, Let us consider how a stone wall is built. The stones used will have different shapes and sizes. The stones at the top of the wall would not influence the choice of stones that come below them. On the other hand, the shapes and sizes of stones in the lowermost layer will decide the shape and size of the next layer, and so on. The stones in the lowermost layer are like the characteristics that decide the broadest divisions among living organisms. They are independent of any other characteristics and their effects on the form and function of the organism. The characteristics in the next level would be dependent on the previous one and would decide the variety in the next level. In this way, we can build up a whole hierarchy of mutually related characteristics to be used for classification. Nowadays, we look at many interrelated characteristics starting from the nature of the cell in order to classify all living organisms. What are some concrete examples of such characteristics used for a hierarchical classification? A eukaryotic cell has membrane-bound organelles, including a nucleus, which allows cellular processes to be carried out efficiently in isolation from each other. Therefore, organisms which do not have a clearly demarcated nucleus and other organelles would need to have their biochemical pathways organized in very different ways. This would have an effect on every aspect of cell design. Further, nucleated cells would have the capacity to participate in making a multicellular organism because they can take up specialized functions. Therefore, nucleus can be a basic characteristic of classification. Do the cells occur singly, or are they grouped together, and do they live as an indivisible group? Cells that group together to form a single organism use the principle of division of labor. In such a body design, all cells would not be identical. Instead, groups of cells will carry out specialized functions. This makes a very basic distinction in the body designs of organisms. As a result, an amoeba and a worm are very different in their body design. Do organisms produce their own food through the process of photosynthesis? Being able to produce one's own food versus having to get food from outside would make very different body designs. Of the organisms that perform photosynthesis: plants, what is the level of organization of their body? Of the animals, how does the individual's body develop and organize its different parts, and what are the specialized organs found for different functions? Diversity in living organisms. 81. SCIENCE82. We can see that, even in these few questions that we have asked, a hierarchy is developing. The characteristics of body design used for classification of plants will be very different from those important for classifying animals. This is because the basic designs are different, based on the need to make their own food: plants, or acquire it: animals. Therefore, these design features having a skeleton, for example, are to be used to make subgroups, rather than making broad groups. Questions 1. Which do you think is a more basic characteristic for classifying organisms: the place where they live? B. The kind of cells they are made of. Why 2. What is the primary characteristic on which the broad division of organisms is made? 3. On what basis are plants and animals put into different categories? 7.2 Classification and evolution. All living things are identified and categorized on the basis of their body design in form and function. Some characteristics are likely to make more wide-ranging changes in body design than others. There is a role of time in this as well. So, once a certain body design comes into existence, it will shape the effects of all other subsequent design changes, simply because it already exists. In other words, characteristics that came into existence earlier are likely to be more basic than characteristics that have come into existence later. This means that the classification of life forms will be closely related to their evolution. What is evolution? Most life forms that we see today have arisen by an accumulation of changes in body design that allow the organism possessing them to survive better. Charles Darwin first described this idea of evolution in 1859 in his book, The Origin of Species. When we connect this idea of evolution to classification, we will find some groups of organisms which have ancient body designs that have not changed very much. We will also find other groups of organisms that have acquired their particular body designs relatively recently. Those in the first group are frequently referred to as primitive or lower organisms, while those in the second group are called advanced or higher organisms. In reality, these terms are not quite correct since they do not properly relate to the differences. All that we can say is that some are older organisms, while some are younger organisms. Since there is a possibility that complexity in design will increase over evolutionary time, it may not be wrong to say that older organisms are simpler, while younger organisms are more complex. More to know. Biodiversity means the diversity of life forms. It is a word commonly used to refer to the variety of life forms found in a particular region. Diverse life forms share the environment, and are affected by each other too. As a result, a stable community of different species comes into existence. Humans have played their own part in recent times in changing the balance of such communities. Of course, the diversity in such communities is affected by particular characteristics of land, water, climate and so on. Rough estimates state that there are about 10 million species on the planet, although we actually know only 1 or 2 million of them. The warm and humid tropical regions of the Earth, between the Tropic of Cancer and the Tropic of Capricorn, are rich in diversity of plant and animal life. This is called the region of megadiversity. Of the biodiversity on the planet, more than half is concentrated in a few countries: Brazil, Colombia, Ecuador, Peru, Mexico, Zaire, Madagascar, Australia, China, India, Indonesia and Malaysia. Diversity in living organisms. 83 questions. 1. Which organisms are called primitive and how are they different from the so-called advanced organisms? 2. Will advanced organisms be the same as complex organisms? Why? 7.3 The hierarchy of classification groups. Biologists such as Ernst Haeckel 1894, Robert Whittaker 1969 and Carl Woese 1977 have tried to classify all living organisms into broad categories, called kingdoms. The classification Whittaker proposed has 5 kingdoms: Minera, Protista, Fungi, Plantae and Animalia, and is widely used. These groups are formed on the basis of their cell structure, mode and source of nutrition and body organization. The modification was introduced by dividing the Minera into Archaebacteria or Archaea and Eubacteria or bacteria is also in use. Further classification is done by naming the subgroups at various levels as given in the following scheme: kingdom, phylum for animals, division for plants, class, order, family, genus, species. Thus, by separating organisms on the basis of a hierarchy of characteristics into smaller and smaller groups, we arrive at the basic unit of classification, which is a species. So what organisms can be said to belong to the same species? Broadly, a species includes all organisms that are similar enough to breed and perpetuate. The important characteristics of the 5 kingdoms of Whittaker are as follows. 7.3.1 Minera. These organisms do not have a defined nucleus or organelles, nor do any of them show multicellular body designs. On the other hand, they show diversity based on many other characteristics. Some of them have cell walls while some do not. Of course, having or not having a cell wall has very different effects on body design here from having or not having a cell wall in multicellular organisms. The mode of nutrition of organisms in this group can be either by synthesizing their own food autotrophic or getting it from the environment heterotrophic. This group includes bacteria, blue-green algae or cyanobacteria, and mycoplasma. Some examples are shown in figure 7.1. Q. Bacteria resting spore heterocystanabana. Figure 7.1. Minera. 7.3.2 Protista. This group includes many kinds of unicellular eukaryotic organisms. Some of these organisms use appendages, such as hair-like cilia or whip-like flagella for moving around. Their mode of nutrition can be autotrophic or heterotrophic. Examples are unicellular algae, diatoms and protozoans. See figure 7.2 for examples. Protoplasm of a host organism for food. They are called parasites. Many of them have the capacity to become multicellular organisms at certain stages in their lives. They have cell walls made of a tough complex sugar called chitin. Examples are yeasts, molds and mushrooms. See figure 7.3 for examples. Macronucleus, micronucleus, waste, flagellum, long nucleus, nucleus, paramecium, amoeba, oigalena. Figure 7.2. Protozoa. 7.3.3 Fungi. These are heterotrophic eukaryotic organisms. Some of them use decaying organic material as food and are therefore called saprotrophs. Others require a living. Some fungal species live in permanent mutually dependent relationships with blue-green algae or cyanobacteria. Such relationships are called symbiotic. These symbiotic life forms are called lichens. We have all seen lichens as the slow-growing large colored patches on the bark of trees. 7.3.4 Plantae. These are multicellular eukaryotes with cell walls. They are autotrophs and use chlorophyll for photosynthesis. Thus, all plants are included in this group. Since plants and animals are most visible forms of the diversity of life around us, we will look at the subgroups in this category later. Section 7.4. 7.3.5 Animalia. These include all organisms which are multicellular eukaryotes without cell walls. They are heterotrophs. Again, we will look at their subgroups a little later in section 7.5. Figure 7.3. Fungi. Agaricus, mushroom, penicillium, molds, Saccharomyces, yeast. Diversity and living organisms. 85 Figure 7.4. The Five Kingdom Classification. Questions 1. What is the criterion for classification of organisms as belonging to Kingdom Monera or Protista? 2. In which kingdom will you place an organism which is single-celled, eukaryotic and photosynthetic? 3. In the hierarchy of classification, which grouping will have the smallest number of organisms with maximum common characteristics and which will have the largest number of organisms? Q 7.4 Plantae. The first level of classification among plants depends on whether the plant body has well differentiated, distinct parts. The next level of classification is based on whether the differentiated plant body has special tissues for the transport of water and other substances. Further classification looks at the ability to bear seeds and whether the seeds are enclosed within fruits. 7.4.1 Thallophyta. Plants that do not have well-differentiated body design fall in this group. The plants in this group are commonly called algae. These plants, SCIE 86, are predominantly aquatic. Examples are Spirogyra, Allothrix, Claudifera, Ulvencaris. Figure 7.5. 7.4.2 Bryophyta. These are called the amphibians of the plant kingdom. The plant body is commonly differentiated to form stem and leaf-like structures. However, there is no specialized tissue for the conduction of water and other substances from one part of the plant body to another. Examples are Mossvenaria and Merschantia. See Figure 7.6. Figure 7.5. Thallophyta. Algae cell wall, chloroplast, paranoids, nucleus, cytoplasm, Allothrix, Claudifera, Ulva, Spirogyra, Cara. Figure 7.6. Some common bryophytes. 7.4.3 Pteridophyta. In this group, the plant body is differentiated into roots, stem and leaves and has specialized tissue for the conduction of water and other substances from one part of the plant body to another. Some examples are Marsilia, ferns and horsetails. See Figure 7.7. The reproductive organs of plants in all these three groups are very inconspicuous, and they are therefore called cryptogames, or those with hidden reproductive organs. On the other hand, Plants with well-differentiated reproductive parts that ultimately make seeds are called Richtschirmschunchifenaria. Diversity in living organisms. 87 Phanerogames. Seeds are the result of sexual reproduction process. They consist of the embryo along with stored food, which assists for the initial growth of the embryo during germination. This group is further classified, based on whether the seeds are naked or enclosed in fruits, giving us two groups, gymnosperms and angiosperms. 7.4.4 Gymnosperms. This term is derived from two Greek words, gymno means naked and sperma means seed. The plants of this group bear naked seeds and are usually perennial, evergreen and woody. Examples are pines and deodar. See figure. 7.8 For examples. 7.4.5 Angiosperms. This word is made from two Greek words, angio means covered and sperma means seed. These are also called flowering plants. The seeds develop inside an ovary which is modified to become a fruit. Plant embryos and seeds have structures called cotyledons. Cotyledons are called seed leaves because in many instances they emerge and become green when the seed germinates. The angiosperms are divided into two groups on the basis of the number of cotyledons present in the seed. Plants with seeds having a single cotyledon are called monocotyledonous or monocots. Plants with seeds having two cotyledons are called dicots. See figures. 7.9 and 7.10. Marsilia fern leaf stem root figure 7.7, Pteridophyta penis figure 7.8, Gymnosperms cycas figure 7.9, monocot figure 7.10, dicot. NCERT activity 7.2 middle dot soak seeds of green gram, wheat, maize, peas and tamarind. Once they become tender, try to split the seed. Do all the seeds break into two nearly equal halves? Middle dot The seeds that do are the dicot seeds and the seeds that don't are the monocot seeds. Middle dot Now take a look at the roots, leaves and flowers of these plants. Middle dot Are the roots tap roots or fibers? Middle dot Do the leaves have parallel or reticulate venation? Figure 7.11 Classification of plants. Middle dot How many petals are found in the flower of these plants? Middle dot Can you write down further characteristics of monocots and dicots on the basis of these observations? Questions 1. Which division among plants has the simplest organisms? 2. How are pteridophytes different from the phanerogames? 3. How do gymnosperms and angiosperms differ from each other? Q. Diversity in living organisms. 89 7.5 Animalia. These are organisms which are eukaryotic, multicellular and heterotrophic. Their cells do not have cell walls. Most animals are mobile. They are further classified based on the extent and type of the body design differentiation found. 7.5.1 Porifera. The word porifera means organisms with holes. These are non-motile animals attached to some solid support. There are holes or pores all over the body. These lead to a canal system that helps in circulating water throughout the body to bring in food and oxygen. These animals are covered with a hard outside layer or skeleton. The body design involves very minimal differentiation and division into tissues. They are commonly called sponges, and are mainly found in marine habitats. Some examples are shown in figure 7.12. Layers of cells. One makes up cells on the outside of the body, and the other makes the inner lining of the body. Some of these species live in colonies corals, while others have a solitary like Hispanhydra. Jellyfish and sea anemones are common examples. See figure 7.13. Cicanoplectella spongilla figure 7.12. Porifera tentacles. Sea anemone tentacles. Stinging cell mouth. Epidermis. Mesoglea. Gastrodermis. Gastrovascular cavity. Foot figure 7.13. Coelenterata 7.5.3 Platyhelminthes. The body of animals in this group is far more complexly designed than in the two other groups we have considered so far. The body is bilaterally symmetrical, meaning that the left and the right halves of the body have the same design. There are 3 layers of cells from which differentiated tissues can be made, which is why such animals are called triploblastic. This allows outside and inside body linings as well as some organs to be made. There is thus some degree of tissue formation. However, there is no true internal body cavity or column, in which well-developed organs can be accommodated. The body is flattened dorsoventrally, meaning from top to bottom, which is why these animals are called flatworms. They are either free-living or parasitic. Some examples are free-living animals like planarians, or parasitic animals like liver flukes. See figure 7.14 for examples. Hydra 7.5.2 Coelenterata cnidaria. These are animals living in water. They show more body design differentiation. There is a cavity in the body. The body is made of 2 SCIENCE 97.5.5 Annelid animals are also bilaterally symmetrical and triploblastic, but in addition they have a true body cavity. This allows true organs to be packaged in the body structure. There is, thus, extensive organ differentiation. This differentiation occurs in a segmental fashion, with the segments lined up one after the other from head to tail. These animals are found in a variety of habitats: freshwater, marine water as well as land. Earthworms and leeches are familiar examples. See figure 7.16. Acetabulum scilex sucker net tapeworm liver fluke eyes branched gastrovascular cavity pharynx mouth and anus planaria figure 7.14. Platyhelminthes 7.5.4 Nematode. The nematode body is also bilaterally symmetrical and triploblastic. However, the body is cylindrical rather than flattened. There are tissues, but no real organs, although a sort of body cavity or a pseudocolumn is present. These are very familiar as parasitic worms causing diseases, such as the worms causing elephantiasis filaria worms or the worms in the intestines roundworm or pinworms. Some examples are shown in figure 7.15. Female male Ascaris wageraria figure 7.15, Nematoda Aschelminthes tentacle Parapodia inner earthworm leech figure 7.16. Annelida 7.5.6 Arthropoda. This is probably the largest group of animals. These animals are bilaterally symmetrical and segmented. There is an open circulatory system, and so the blood does not flow in well-defined blood vessels. The coelomic cavity is blood-filled. They have jointed legs. The word arthropod means jointed legs. Some familiar examples are prawns, butterflies, houseflies, spiders, scorpions and crabs. See figure 7.17. Genital papillae anus. Diversity in living organisms 91 Echinus sea urchin Asterias sea star figure 7.19, Echinodermatons and feather star Holothuria sea cucumber Palamnae scorpion 7.5.7 Mollusca. In the animals of this group, there is bilateral symmetry. The coelomic cavity is reduced. There is little segmentation. They have an open circulatory system and kidney-like organs for excretion. There is a foot that is used for moving around. Examples are snails and mussels. See figure 7.18. 7.5.8 Echinodermata. In Greek, echinos means hedgehog spiny mammal, and derma means skin. Thus, these are spiny-skinned organisms. These are exclusively free-living marine animals. They are triploblastic and have a coelomic cavity. They also have a peculiar water-driven tube system that they use for moving around. They have hard calcium carbonate structures that they use as a skeleton. Examples are sea stars and sea urchins. See figure 7.19. Periplaneta cockroach Polemon pronarinea spider figure 7.17, Arthropoda chitin octopus pilla unio figure 7.18, mollusca 7.5.9 Protochordata. These animals are bilaterally symmetrical, triploplastic and have a column. In addition, they show a new feature of body design, namely a notochord, at least at some stages during their lives. The notochord is a long rod-like support structure cord string that runs along the back of the animal, separating the nervous tissue from the gut. It provides a place for muscles to attach for ease of movement. Protochordates may not have a proper notochord present at all stages in their lives or for the entire length of the animal. Protochordates are marine animals. Examples are Balanoglossus, Herdmania and Amphioxus. See figure 7.20. Muscle housefly butterfly Scolopendra centipede. SCIENCE 92 Pterois volitans lionfish Coliforine Jordani anglerfish Synchiropus splendidus mandarin fish Proboscis colorat collar bronchial region gill pores dorsally curved genital wings mid-dorsal ridge hepatic cecohepatic region pulse hepatic region anus figure 7.20 Protochordata Balanoglossus spiracle eye pelvic fin dorsal fin caudal fin tail electric ray torpedo stingray mouth dorsal fin tail eye gills pectoral fin pelvic fin figure 7.22 Pisces scoliodon dogfish scolus. They are ectoparasites or borers of other vertebrates. Petromycin lamprey and Meekson hagfish are examples. July 5, 2010 2 Pisces. These are fish. They are exclusively aquatic animals. Their skin is covered with scales plates. They obtain oxygen dissolved in water by using gills. The body is streamlined, and a muscular tail is used for movement. They are cold-blooded and their hearts have only 2 chambers, unlike the 4 that humans have. They lay eggs. We can think of many kinds of fish, some with skeletons made entirely of cartilage, such as sharks, and some with a skeleton made of both bone and cartilage, such as tuna or ahu. See examples in figures 7.22a and 7.22b. Figure 7.21, a jawless vertebrate, Petromycin. July 5, 2010 Vertebrata. These animals have a true vertebral column and internal skeleton, allowing a completely different distribution of muscle attachment points to be used for movement. Vertebrates are bilaterally symmetrical, triploplastic, coelomic and segmented, with complex differentiation of body tissues and organs. All chordates possess the following features: I have a notochord, 2 have a dorsal nerve cord, 3 are triploplastic, I have paired gill pouches, V are columnate. Vertebrates are grouped into 6 classes. July 5, 2010 Icyclostomata. Cyclostomes are jawless vertebrates. They are characterized by having an elongated eel-like body, circular mouth, slimy skin and are. Diversity and living organisms. 93 July 5, 2010 3 Amphibia. These animals differ from the fish in the lack of scales, in having mucus glands in the skin, and a 3-chambered heart. Respiration is through either gills or lungs. They lay eggs. These animals are found both in water and on land. Frogs, toads and salamanders are some examples. See figure 7.23. July 5, 2010 Ivraptorlia. These animals are cold-blooded, have scales and breathe through lungs. While most of them have a 3-chambered heart, crocodiles have 4 heart chambers. They lay eggs with tough coverings and do not need to lay their eggs in water, unlike amphibians. Snakes, turtles, lizards and crocodiles fall in this category. See figure 7.24. Eye, head, nostril, mouth, pectoral fin, pelvic fin, caudal fin, labio-rohedera, ahu, pectoral fin, mouth, brood pouch, dorsal fin, tail, male hippocampus, seahorse, wing-like pectoral tail, pelvic fin, scales, exocoitus, flying fish, anubis, climbing perch figure 7.22b, Pisces figure 7.23, amphibia, rhino, tigrina, common frog, toad, hyla, tree frog, salamander, turtle, chameleon, king cobra, house wall lizard, homidactylus, flying lizard, Draco. July 5, 2010. The aves. These are warm-blooded animals and have a 4-chambered heart. They lay eggs. There is an outside covering of feathers, and 2 forelimbs are modified for flight. They breathe through lungs. All birds fall in this category. See Figure 7.25 for examples. Figure 7.24, Reptilia. SCIENCE 94. July 5, 2010. 6 mammalia. Mammals are warm-blooded animals with 4-chambered hearts. They have mammary glands for the production of milk to nourish their young. Their skin has hairs as well as sweat and oil glands. Most mammals familiar to us produce live young ones. However, a few of them, like the platypus and the echidna, lay eggs, and some, like kangaroos, give birth to very poorly developed young ones. Some examples are shown in Figure 7.26. The scheme of classification of animals is shown in Figure 7.27. White stork, Ciconia, ostrich, Struthio, camelus, male tufted duck, Athia, fulicula, pigeon, sparrow, crow. Figure 7.25, aves, birds. Figure 7.26, mammalia. Questions 1. How do puriferan animals differ from coelenterates animals? 2. How do annelid animals differ from arthropods? 3. What are the differences between amphibians and reptiles? 4. What are the differences between animals belonging to the aves group and those in the mammalia group? Q. Carolus Linnaeus. Carl von Linné was born in Sweden and was a doctor by profession. He was interested in the study of plants. At the age of 22, he published his first paper on plants. While serving as a personal physician of a wealthy government official, he studied the diversity of plants in his employer's garden. Later, he published 14 papers and also brought out the famous book Systematica, from which all fundamental taxonomical researches have taken off. His system of classification was a simple scheme for arranging plants so as to be able to identify them again. Carolus Linnaeus. 1707–1778. Whale, human, cat, rat, bat. Diversity in living organisms. 95. Figure 7.27, classification of animals. SCIENCE 96. 7.6, nomenclature. Why is there a need for systematic naming of living organisms? Activity 7.3 middle dot. Find out the names of the following animals and plants in as many languages as you can. 1. Tiger. 2. Peacock. 3. Ant. 4. Neem. 5. Lotus. 6. Potato. As you might be able to appreciate, it would be difficult for people speaking or writing in different languages to know when they are talking about the same organism. This problem was resolved by agreeing upon a scientific name for organisms in the same manner that chemical symbols and formulae for various substances are used the world over. The scientific name for an organism is thus unique and can be used to identify it anywhere in the world. The system of scientific naming or nomenclature we use today was introduced by Carolus Linnaeus in the 18th century. The scientific name of an organism is the result of the process of classification which puts it along with the organisms it is most related to. But when we actually name the species, we do not list out the whole hierarchy of groups it belongs to. Instead, we limit ourselves to writing the name of the genus and species of that particular organism. World over, it has been agreed that both these names will be used in Latin forms. Certain conventions are followed while writing the scientific names. 1. The name of the genus begins with a capital letter. 2. The name of the species begins with a small letter. 3. When printed, the scientific name is given in italics. 4. When written by hand, the genus name and the species name have to be underlined separately. Activity 7.4 middle dot. Find out the scientific names of any 5 common animals and plants. Do these names have anything in common with the names you normally use to identify them? What you have learned. Classification helps us in exploring the diversity of life forms. The major characteristics considered for classifying all organisms into 5 major kingdoms are: A. Whether they are made of prokaryotic or eukaryotic cells. B. Whether the cells are living singly or organized into multicellular and thus complex organisms. C. Whether the cells have a cell wall and whether they prepare their own food. All living organisms are divided on the above basis into 5 kingdoms, namely Monera, Protista, Fungi, Plantae and Animalia. The classification of life forms is related to their evolution. Diversity in living organisms. 97. Plantae and Animalia are further divided into subdivisions on the basis of increasing complexity of body organization. Plants are divided into 5 groups: Thallophytes, Bryophytes, Pteridophytes, Gymnosperms and Angiosperms. Animals are divided into 10 groups: Porifera, Coelenterata, Platyhelminthes, Nematoda, Annelida, Arthropoda, Mollusca, Echinodermata, Protochordata and Vertebrata. The binomial nomenclature makes for a uniform way of identification of the vast diversity of life around us. The binomial nomenclature is made up of 2 words: a generic name and a specific name. Exercises 1. What are the advantages of classifying organisms? 2. How would you choose between 2 characteristics to be used for developing a hierarchy in classification? 3. Explain the basis for grouping organisms into 5 kingdoms. 4. What are the major divisions in the Plantae? What is the basis for these divisions? 5. How are the criteria for deciding divisions in plants different from the criteria for deciding the subgroups among animals? 6. Explain how animals and vertebrata are classified into further subgroups. In everyday life, we see some objects at rest and others in motion. Birds fly, fish swim, blood flows through veins and arteries, and cars move. Atoms, molecules, planets, stars and galaxies are all in motion. We often perceive an object to be in motion when its position changes with time. However, there are situations where the motion is inferred through indirect evidences. For example, we infer the motion of air by observing the movement of dust and the movement of leaves and branches of trees. What causes the phenomena of sunrise, sunset and changing of seasons? Is it due to the motion of the earth? If it is true, why don't we directly perceive the motion of the earth? An object may appear to be moving for one person and stationary for some other. For the passengers in a moving bus, the roadside trees appear to be moving backwards. A person standing on the roadside perceives the bus along with the passengers as moving. However, a passenger inside the bus sees his fellow passengers to be at rest. What do these observations indicate? Most motions are complex. Some objects may move in a straight line, others may take a circular path. Some may rotate and a few others may vibrate. There may be situations involving a combination of these. In this chapter, we shall first learn to describe the motion of objects along a straight line. We shall also learn to express such motions through simple equations and graphs. Later, we shall discuss ways of describing circular motion. Activity 8.1 Discuss whether the walls of your classroom are at rest or in motion. Activity 8.2 Have you ever experienced that the train in which you are sitting appears to move while it is at rest? Discuss and share your experience. Think and act. We sometimes are endangered by the motion of objects around us, especially if that motion is erratic and uncontrolled, as observed in a flooded river, a hurricane or a tsunami. On the other hand, controlled motion can be a service to human beings, such as in the generation of hydroelectric power. Do you feel the necessity to study the erratic motion of some objects and learn to control them? 8.1 Describing motion. We describe the location of an object by specifying a reference point. Let us understand this by an example. Let us assume that a school in a village is 2 kilometers north of the railway station. We have specified the position of the school with respect to the railway station. In this example, the railway station is the reference point. We could have also chosen other reference points according to our convenience. Therefore, to describe the position of an object we need to specify a reference point called the origin. 8 Motion Ocean Chapter 8.1.1 Motion along a straight line. The simplest type of motion is the motion along a straight line. We shall first learn to describe this by an example. Consider the motion of an object moving along a straight path. The object starts its journey from O, which is treated as its reference point. Figure 8.1. Let A, B and C represent the position of the object at different instants. At first, the object moves through C and B and reaches A, then it moves back along the same path and reaches C through B. Displacement are used to describe the overall motion of an object and to locate its final position with reference to its initial position at a given time. Activity 8.3 Middle. Take a meter scale and a long rope. Middle. Walk from one corner of a basketball court to its opposite corner along its sides. Middle. Measure the distance covered by you and magnitude of the displacement. Middle. What difference would you notice between the two? In this case, activity 8.4 Middle. Automobiles are fitted with a device that shows the distance traveled. Such a device is known as an odometer. A car is driven from Bhubaneswar to New Delhi. The difference between the final reading and the initial reading of the odometer is 1850 kilometers. Middle. Find the magnitude of the displacement between Bhubaneswar and New Delhi by using the road map of India. The total path length covered by the object is OAC, that is 60 kilometers, 35 kilometers, 95 kilometers. This is the distance covered by the object. To describe distance, we need to specify only the numerical value and not the direction of motion. There are certain quantities which are described by specifying only their numerical values. The numerical value of a physical quantity is its magnitude. From this example, can you find out the distance of the final position C of the object from the initial position O? This difference will give you the numerical value of the displacement of the object from O to C through A. The shortest distance measured from the initial to the final position of an object is known as the displacement. Can the magnitude of the displacement be equal to the distance traveled by an object? Consider the example given in figure 8.1. For motion of the object from O to A, the distance covered is 60 kilometers and the magnitude of displacement is also 60 kilometers. During its motion from O to A and back to B, the distance covered 60 kilometers, 25 kilometers, 85 kilometers. Figure 8.1. Positions of an object on a straight line path while the magnitude of displacement 35 kilometers. Thus, the magnitude of displacement 35 kilometers is not equal to the path length 85 kilometers. Further, we will notice that the magnitude of the displacement for a course of motion may be 0, but the corresponding distance covered is not 0. If we consider the object to travel back to O, the final position coincides with the initial position, and therefore, the displacement is 0. However, the distance covered in this journey is O, 60 kilometers, 120 kilometers. Thus, two different physical quantities, the distance and the motion. 99. NCERT 100 Questions 1. An object has moved through a distance. Can it have 0 displacement? If yes, support your answer with an example. 2. A farmer moves along the boundary of a square field of side 10 meters in 40 seconds. What will be the magnitude of displacement of the farmer at the end of 2 minutes 20 seconds from his initial position? 3. Which of the following is true for displacement? A. It cannot be 0. B. Its magnitude is greater than the distance traveled by the object. 8.1.2 Uniform motion and non-uniform motion. Consider an object moving along a straight line. Let it travel 5 meters in the first second, 5 meters more in the next second, 5 meters in the third second, and 5 meters in the fourth second. In this case, the object covers 5 meters in each second. As the object covers equal distances in equal intervals of time, it is said to be in uniform motion. The time interval in this motion should be small. In our day-to-day life, we come across motions where objects cover unequal distances in equal intervals of time, for example, when a car is moving on a crowded street or a person is jogging in a park. These are some instances of non-uniform motion. Activity 8.5 Middle. The data regarding the motion of two different objects A and B are given in Table 8.1. Middle. Examine them carefully and state whether the motion of the objects is uniform or non-uniform. Q. A B figure. 8.2 Table 8.1 Time distance traveled by object A and M object B and M 9:30 am 10, 12 9:45 am 20, 19:10 am 30, 23:10 15 am 40, 35:10 30 am 50, 37:10 45 am 60, 41:11 am 70, 44. 8.2 Measuring the rate of motion. Motion 101. Look at the situations given in Figure 8.2. If the bowling speed is 143 km h1 in Figure 8.2, what does it mean? What do you understand from the signboard in Figure 8.2b? Different objects may take different amounts of time to cover a given distance. Some of them move fast and some move slowly. The rate at which objects move can be different. Also, different objects can move at the same rate. One of the ways of measuring the rate of motion of an object is to find out the distance traveled by the object in unit time. This quantity is referred to as speed. The C unit of speed is meter per second. This is represented by the symbol ms1 or ms. The other units of speed include centimeter per second, centimeters s1, and kilometer per hour, kilometers h1. To specify the speed of an object, we require only its magnitude. The speed of an object need not be constant. In most cases, objects will be in non-uniform motion. Therefore, we describe the rate of motion of such objects in terms of their average speed. The average speed of an object is obtained by dividing the total distance traveled by the total time taken. That is, average speed total distance traveled total time taken. If an object travels a distance s in time t, then its speed v is vst. 8.1 Let us understand this by an example. A car travels a distance of 100 km in 2h. Its average speed is 50 km h1. The car might not have traveled at 50 km h1 all the time. Sometimes it might have traveled faster and sometimes slower than this. Example 8.1 An object travels 16 meters in 4 seconds and then another 16 meters in 2 seconds. What is the average speed of the object? Solution: total distance traveled by the object 16 meters, 32 meters, total time taken 4 seconds, 2 seconds, 6 seconds, average speed total distance traveled total time taken 32 meters, 6 seconds, 5.33 meters s1. Therefore, the average speed of the object is 5.33 meters s1. 8.2.1 Speed with direction. The rate of motion of an object can be more comprehensive if we specify its direction of motion along with its speed. The quantity that specifies both these aspects is called velocity. Velocity is the speed of an object moving in a definite direction. The velocity of an object can be uniform or variable. It can be changed by changing the object's speed, direction of motion, or both. When an object is moving along a straight line at a variable speed, we can express the magnitude of its rate of motion in terms of average velocity. It is calculated in the same way as we calculate average speed. In case the velocity of the object is changing at a uniform rate, then average velocity is given by the arithmetic mean of initial velocity and final velocity for a given period of time. That is, average velocity, initial velocity, final velocity. 2 Mathematically, VAV U V2 8.2, where VAV is the average velocity, U is the initial velocity, and V is the final velocity of the object. Speed and velocity have the same units, that is, ms1 or ms. Activity 8.6 Middle dot. Measure the time it takes you to walk from your house to your bus stop or the school. If you consider that your average walking speed is 4 km h1, estimate the distance of the bus stop or school from your house. NCERT 102 50 km 1000 meters 1 h times h1 km 3613.9 meters s1. The average speed of the car is 50 km h1 or 13.9 meters s1. Example 8.3. Asha swims in a 90 meters long pool. She covers 180 meters in 1 minute by swimming from one end to the other and back along the same straight path. Find the average speed and average velocity of Asha. Solution: total distance covered by Asha in 1 minute is 180 meters. Displacement of Asha in 1 minute 0 meters. Average speed, total distance covered, total ultimate taken 180 meters. 180 meters 1 minute times 1 minute 1 minute 60 is 3 meters s1. Average velocity, displacement, total ultimate taken 0 meters 60 seconds 0 meters s1. The average speed of Asha is 3 meters s1 and her average velocity is 0 meters s1. 8.3 Rate of change of velocity during uniform motion of an object along a straight line. The velocity remains constant with time. In this case, the change in velocity of the object for any time interval is 0. However, in non-uniform motion, velocity varies with time. It has different values at different instants and at different points of the path. Thus, the change in velocity of the object during any time interval is not 0. Can we now express the change in velocity of an object? Activity 8.7 Middle dot. At a time when it is cloudy, there may be frequent thunder and lightning. The sound of thunder takes some time to reach you after you see the lightning. Middle dot. Can you answer why this happens? Middle dot. Measure this time interval using a digital wristwatch or a stopwatch. Middle dot. Calculate the distance of the nearest point of lightning. Speed of sound in air 346 meters s1. Questions 1. Distinguish between speed and velocity. 2. Under what condition S is the magnitude of average velocity of an object equal to its average speed? 3. What does the odometer of an automobile measure for? What does the path of an object look like when it is in uniform motion? 5. During an experiment, a signal from a spaceship reached the ground station in 5 minutes. What was the distance of the spaceship from the ground station? The signal travels at the speed of light, that is, 3 times 108 meters s1. Example 8.2. The odometer of a car reads 2,000 kilometers at the start of a trip and 2,400 kilometers at the end of the trip. If the trip took 8h, calculate the average speed of the car in kilometers h1 and ms1. Solution: distance covered by the car. S 2,400 kilometers 2,000 kilometers 400 kilometers. Time elapsed. T8h. Average speed of the car is V 400 kilometers 8h. 50 kilometers h1q. Motion 103. To answer such a question, we have to introduce another physical quantity called acceleration, which is a measure of the change in the velocity of an object per unit time. That is, acceleration, change in velocity time taken if the velocity of an object changes from an initial value u to the final value v in time t. The acceleration is vu at t. 8.3. This kind of motion is known as accelerated motion. The acceleration is taken to be positive if it is in the direction of velocity and negative when it is opposite to the direction of velocity. The c unit of acceleration is ms2. If an object travels in a straight line and its velocity increases or decreases by equal amounts in equal intervals of time, then the acceleration of the object is said to be uniform. The motion of a freely falling body is an example of uniformly accelerated motion. On the other hand, an object can travel with non-uniform acceleration if its velocity changes at a non-uniform rate. For example, if a car traveling along a straight road increases its speed by unequal amounts in equal intervals of time, then the car is said to be moving with non-uniform acceleration. Activity 8.8 Middle dot. In your everyday life you come across a range of motions in which acceleration is in the direction of motion. B. Acceleration is against the direction of motion. C. Acceleration is uniform. D. Acceleration is non-uniform. Middle dot. Can you identify one example each for the above type of motion? Example 8.4. Starting from a stationary position, Rahul paddles his bicycle to attain a velocity of 6 meters s1 in 30 seconds. Then he applies brakes such that the velocity of the bicycle comes down to 4 meters s1 in the next 5 seconds. Calculate the acceleration of the bicycle in both the cases. Solution: in the first case, initial velocity, u0. Final velocity, v 6 meters s1. Time, t 30 seconds. From Eq. 8.3, we have vu at t. Substituting the given values of u, v and t in the above equation, we get 6 meters s0 meters s 30 seconds is 0.2 meters s2 in the second case, initial velocity, u 6 meters s1. Final velocity, v 4 meters s1. Time, t 5 seconds. Then, 4 meters s6 meters s5 seconds is 0.4 meters s2. The acceleration of the bicycle in the first case is 0.2 meters s2 and in the second case, it is 0.4 meters s2. Questions 1. When will you say a body is in a uniform acceleration to non-uniform acceleration 2? A bus decreases its speed from 80 km h1 to 60 km h1 in 5 seconds. Find the acceleration of the bus. 3. A train starting from a railway station and moving with uniform acceleration attains a speed 40 km h1 in 10 minutes. Find its acceleration. Q. NCERT 104 8.4 Graphical representation of motion. Graphs provide a convenient method to present basic information about a variety of events. For example, in the telecast of a one-day cricket match, vertical bar graphs show the run rate of a team in each over. As you have studied in mathematics, a straight line graph helps in solving a linear equation having two variables. To describe the motion of an object, we can use line graphs. In this case, line graphs show dependence of one physical quantity, such as distance or velocity, on another quantity, such as time. 8.4.1 Distance-time graphs. The change in the position of an object with time can be represented on the distance-time graph adopting a convenient scale of choice. In this graph, time is taken along the z-axis and distance is taken along the y-axis. Distance-time graphs can be employed under various conditions where objects move with uniform speed, non-uniform speed, remain at rest, etc. Figure 8.3, Distance-time graph of an object moving with uniform speed. We know that when an object travels equal distances in equal intervals of time, it moves with uniform speed. This shows that the distance traveled by the object is directly proportional to time taken. Thus, for uniform speed, a graph of distance traveled against time is a straight line, as shown in figure 8.3. The portion ob of the graph shows that the distance is increasing at a uniform rate. Note that, you can also use the term uniform velocity in place of uniform speed if you take the magnitude of displacement equal to the distance traveled by the object along the y-axis. We can use the distance-time graph to determine the speed of an object. To do so, consider a small part A of the distance-time graph shown in Fig 8.3. Draw a line parallel to the x-axis from point A and another line parallel to the y-axis from point B. These two lines meet each other at point C to form a triangle ABC. Now, on the graph, AC denotes the time interval T2 T1 while BC corresponds to the distance S2 S1. We can see from the graph that as the object moves from the point A to B, it covers a distance s2 s1 in time t2 t1. The speed, v of the object, therefore can be represented as v2121 SSTT 8.4. We can also plot the distance-time graph for accelerated motion. Table 8.2 shows the distance traveled by a car in a time interval of 2 seconds. Table 8.2, distance traveled by a car at regular time intervals. Time in seconds. Distance in meters. 0, 0, 2, 1, 4, 4, 6, 9, 8, 16, 10, 25, 12, 36. Motion 105. The distance-time graph for the motion of the car is shown in Figure 8.4. Note that the shape of this graph is different from the earlier distance-time graph figure. 8.3 for uniform motion. The nature of this graph shows nonlinear variation of the distance traveled by the car with time. Thus, the graph shown in Fig 8.4 represents motion with non-uniform speed. 8.4.2 Velocity time graphs. The variation in velocity with time for an object moving in a straight line can be represented by a velocity time graph. In this graph, time is represented along the x-axis. Figure 8.4, distance time graph for a car moving with non-uniform speed. Figure 8.5, velocity time graph for uniform motion of a car, and the velocity is represented along the y-axis. If the object moves at uniform velocity, the height of its velocity time graph will not change with time. Figure 8.5. It will be a straight line parallel to the x-axis. Figure 8.5 shows the velocity time graph for a car moving with uniform velocity of 40 km h1. We know that the product of velocity and time give displacement of an object moving with uniform velocity. The area enclosed by velocity time graph and the time axis will be equal to the magnitude of the displacement. To know the distance moved by the car between time t1 and t2 using Figure 8.5, draw perpendiculars from the points corresponding to the time t1 and t2 on the graph. The velocity of 40 km h1 is represented by the height AC or BD, and the time t2 t1 is represented by the length AB. So, the distance s moved by the car in time t2 t1 can be expressed as SAC times CD 40 km h1 times t2 t1 h 40 t2 t1 km. Area of the rectangle AB shaded in Figure 8.5. We can also study about uniformly accelerated motion by plotting its velocity time graph. Consider a car being driven along a straight road for testing its engine. Suppose the person sitting next to the driver records its velocity after every 5 seconds by noting the reading of the speedometer of the car. The velocity of the car, in kilometers h1 as well as in ms1, at different instants of time is shown in Table 8.3. Table 8.3, velocity of a car at regular instants of time. Time velocity of the car SMS 1 kilometers h1 0, 0, 0, 5, 2.5, 9, 10, 5.0, 18, 15, 7.5, 27, 20, 10.0, 36, 25, 12.5, 45, 30, 15.0, 54. SCIE 106. In this case, the velocity time graph for the motion of the car is shown in Figure 8.6. The nature of the graph shows that velocity changes by equal amounts in equal intervals of time. Thus, for all uniformly accelerated motion, the velocity time graph is a straight line. Figure 8.6, velocity time graph for a car moving with uniform accelerations. You can also determine the distance moved by the car from its velocity time graph. The area under the velocity time graph gives a distance magnitude of displacement moved by the car in a given interval of time. If the car would have been moving with uniform velocity, the distance traveled by it would be represented by the area amped under the graph. Figure 8.6. Since the magnitude of the velocity of the car is changing due to acceleration, the distance s traveled by the car will be given by the area apt under the velocity time graph figure. 8.6. That is, S area apt area of the rectangle apt area of the triangle 8 times BC1, 2AD times Delaware. In the case of non-uniformly accelerated motion, velocity time graphs can have any shape. Figure 8.7, velocity time graphs of an object in non-uniformly accelerated motion. Figure 8.7 shows a velocity time graph that represents the motion of an object whose velocity is decreasing with time, while figure 8.7b shows the velocity time graph representing the non-uniform variation of velocity of the object with time. Try to interpret these graphs. Activity 8.9 middle. The times of arrival and departure of a train at 3 stations A, B and C and the distance of stations B and C from station are given in Table 8.4. Table 8.4, distances of stations B and C from and times of arrival and departure of the train station. Distance time of from arrival departure kilometers hours is 08 o'clock 8:15 B 120 11 15 11 30 C 180 1300 hours 13:15 middle. Plot and interpret the distance time graph for the train assuming that its motion between any 2 stations is uniform. Velocity kilometers h1. Motion 107, 8.5 Equations of motion by graphical method. When an object moves along a straight line with uniform acceleration, it is possible to relate its velocity, acceleration during motion and the distance covered by it in a certain time interval by a set of equations known as the equations of motion. For convenience, a set of 3 such equations are given below. Vu at 8.5 s u 1/2 at 2, 8.62 s v2 u2, 8.7 where u is the initial velocity of the object which moves with uniform acceleration for time t, v is the final velocity, and s is the distance traveled by the object in time t. Eq. 8.5 describes the velocity-time relation and Eq. 8.6 represents the position-time relation. Eq. 8.7, which represents the relation between the position and the velocity, can be obtained from x. 8.5 and 8.6 by eliminating t. These 3 equations can be derived by graphical method. 8.5.1 Equation for velocity-time relation. Consider the velocity-time graph of an object that moves under uniform acceleration as activity 8.10 middle. Pharaohs and his sister Sania go to school on their bicycles. Both of them start at the same time from their home but take different times to reach the school, although they follow the same route. Table 8.5 shows the distance traveled by them in different times. Table 8.5. Distance covered by Pharaohs and Sania at different times on their bicycles. Time distance traveled by Pharaohs by Sania kilometers 8 am 0, 0805 am 1.0, 0.88 10 am 1.9, 1.68 15 am 2.8, 2.38 20 am 3.6, 3.08 25 am 3.6 q middle. Plot the distance time graph for their motions on the same scale and interpret. Questions 1. What is the nature of the distance-time graphs for uniform and non-uniform motion of an object? 2. What can you say about the motion of an object whose distance-time graph is a straight line parallel to the time axis? 3. What can you say about the motion of an object if its speed-time graph is a straight line parallel to the time axis? 4. What is the quantity which is measured by the area occupied below the velocity-time graph? Figure 8.8, velocity-time graph to obtain the equations of motion. SCIENCE 108 O times OC1, 2AD times BD 8.10 substituting OU, OCADT and BD at, we get SU times T1, 2T times at or SUT1, 2 at T2 8.5.3 Equation for position velocity relation from the velocity time graph shown in figure 8.8. The distance s traveled by the object in time t, moving under uniform acceleration a, is given by the area enclosed within the trapezium OAB under the graph. That is, S area of the trapezium OAB coa BC times OC2 substituting OU, BCV and OCT, we get 2U VTS 8.11 from the velocity-time relation E. 8.6. We get VUT 8.12 using X. 8.11 and 8.12 we have times VUS2A or 2SV2U2. Example 8.5. A train starting from rest attains a velocity of 72 km h1 in 5 minutes. Assuming that the acceleration is uniform, find I the acceleration and 2 the distance traveled by the train for attaining this velocity. Shown in figure 8.8 similar to figure 8.6, but now with U0. From this graph, you can see that initial velocity of the object is u at point A and then it increases to v at point B in time t. The velocity changes at a uniform rate A. In figure 8.8, the perpendicular lines BC and B are drawn from point B on the time and the velocity axes respectively, so that the initial velocity is represented by OA, the final velocity is represented by BC, and the time interval t is represented by OC. BD represents the change in velocity in time interval t. Let us draw AD parallel to OC. From the graph, we observe that BCBD is substituting BCV and OU. We get VBDU or BDVU 8.8 from the velocity time graph figure. 8.8. The acceleration of the object is given by a change in velocity to met A can BDBDADOC substituting OCT. We get a BDT or BD at 8.9 using X. 8.8 and 8.9 we get VU at 8.5.2 equation for position-time relation. Let us consider that the object has traveled a distance s in time t under uniform acceleration A. In figure 8.8, the distance traveled by the object is obtained by the area enclosed within OAB under the velocity-time graph A. Thus, the distance s traveled by the object is given by S area OAB, which is a trapezium area of the rectangle OD area of the triangle ABD. Motion 109 solution, we have been given U0, V 72 km h1, 20 meters s1, and t 5 minutes 300 seconds. I from Eq. 8.5 we know that VU at T1 12, 20 meters s0 meters s 300 seconds 1 meter s 15 2 from Eq. 8.7 we have 2 SV2 U2 V2 0 thus 2 1 2 2 220 miss 2 times 115 miss vs a 3000 meters 3 kilometers. The acceleration of the train is 15 meters s2 and the distance traveled is 3 kilometers. Example 8.6 A car accelerates uniformly from 18 km h1 to 36 km h1 in 5 seconds. Calculate I the acceleration and 2 the distance covered by the car in that time. Solution, we are given that U 18 km h1, 5 meters s1 v 36 km h1, 10 meters s1 and t 5 seconds. I from Eq. 8.5 we have VU at T1 110 meters s5 meters s5 seconds 1 meter s2 2 from Eq. 8.6 we have SUT1 2 at T2 5 meters s1 times 5 seconds 1 2 times 1 meter s2 times 5 seconds 2 25 meters 12.5 meters 37.5 meters. The acceleration of the car is 1 meter s2 and the distance covered is 37.5 meters. Example 8.7 The brakes applied to a car produce an acceleration of 6 meters s2 in the opposite direction to the motion. If the car takes 2 seconds to stop after the application of brakes, calculate the distance it travels during this time. Solution, we have been given a 6 meters s2, t 2 seconds and v 0 meters s1. From Eq. 8.5 we know that VU at 0 U 6 meters s2 times 2 seconds or U 12 meters s1. From Eq. 8.6 We get SUT1 to a T2 12 meters S1 times 2 seconds 1 2 6 meters S2 2 seconds 2 24 meters 12 meters 12 meters. Thus, the car will move 12 meters before it stops after the application of brakes. Can you now appreciate why drivers are cautioned to maintain some distance between vehicles while traveling on the road? Questions 1. A bus starting from rest moves with a uniform acceleration of 0.1 meters s2 for 2 minutes. Find the speed acquired. B. The distance traveled. Q. SCIENCE 110. 2. A train is traveling at a speed of 90 kilometers h1. Brakes are applied so as to produce a uniform acceleration of 0.5 meters s2. Find how far the train will go before it is brought to rest. 3. A trolley, while going down an inclined plane, has an acceleration of 2 centimeters s2. What will be its velocity 3 seconds after the start? 4. A racing car has a uniform acceleration of 4 meters s2. What distance will it cover in 10 seconds after start? 5. A stone is thrown in a vertically upward direction with a velocity of 5 meters s1. If the acceleration of the stone during its motion is 10 meters s2 in the downward direction, what will be the height attained by the stone, and how much time will it take to reach their 8.6 uniform circular motion when the velocity of an object changes? We say that the object is accelerating. The change in the velocity could be due to change in its magnitude or the direction of the motion, or both. Can you think of an example when an object does not change its magnitude of velocity, but only its direction of motion? Let us consider an example of the motion of a body along a closed path. Fig 8.9 shows the path of an athlete along a rectangular track. Let us assume that the athlete runs at a uniform speed on the straight parts A, B, C, D and DA of the track. In order to keep himself on track, he quickly changes his speed at the corners. How many times will the athlete have to change his direction of motion while he completes one round? It is clear that to move in a rectangular track once, he has to change his direction of motion 4 times. Now, suppose instead of a rectangular track, the athlete is running along a hexagonal-shaped path as shown in figure 8.9b. In this situation, the athlete will have to change his direction 6 times while he completes one round. What if the track was not a hexagon but a regular octagon, with 8 equal sides as shown by in figure 8.9c? It is observed that as the number of sides of the track increases, the athlete has to take turns more and more often. What would happen to the shape of the track as we go on increasing the number of sides indefinitely? If you do this, you will notice that the shape of the track approaches the shape of a circle and the length of each of the sides will decrease to a point. If the athlete moves with a velocity of constant magnitude along the circular path, the only change in his velocity is due to the change in the direction of motion. The motion of the athlete moving along a circular path is, therefore, an example of an accelerated motion. We know that the circumference of a circle of radius r is given by 2r. If the athlete takes t seconds to go once around the circular path of radius r, the speed v is given by 2r vt. 8.13 When an object moves in a circular path with uniform speed, its motion is called uniform circular motion. A rectangular track B, hexagonal track D, a circular track C, octagonal-shaped track. Figure 8.9. The motion of an athlete along closed tracks of different shapes. Motion 111. If you carefully note, on being released the stone moves along a straight line tangential to the circular path. This is because once the stone is released, it continues to move along the direction it has been moving at that instant. This shows that the direction of motion changed at every point when the stone was moving along the circular path. When an athlete throws a hammer or a discus in a sports meet, she holds the hammer or the discus in his/her hand and gives it a circular motion by rotating his/her own body. Once released in the desired direction, the hammer or discus moves in the direction in which it was moving at the time it was released, just like the piece of stone in the activity described above. There are many more familiar examples of objects moving under uniform circular motion, such as the motion of the Moon and the Earth, a satellite in a circular orbit around the Earth, a cyclist on a circular track at constant speed, and so on. Activity 8.11 Middle dot. Take a piece of thread and tie a small piece of stone at one of its ends. Move the stone to describe a circular path with constant speed by holding the thread at the other end, as shown in figure 8.10. Figure 8.10, a stone describing a circular path with a velocity of constant magnitude. Middle dot. Now, let the stone go by releasing the thread. Middle dot. Can you tell the direction in which the stone moves after it is released? Middle dot. By repeating the activity for a few times and releasing the stone at different positions of the circular path. Check whether the direction in which the stone moves remains the same or not. What you have learned. Middle dot. Motion is a change of position. It can be described in terms of the distance moved or the displacement. Middle dot. The motion of an object could be uniform or non-uniform depending on whether its velocity is constant or changing. Middle dot. The speed of an object is the distance covered per unit time, and velocity is the displacement per unit time. Middle dot. The acceleration of an object is the change in velocity per unit time. Middle dot. Uniform and non-uniform motions of objects can be shown through graphs. Middle dot. The motion of an object moving at uniform acceleration can be described with the help of the following equations. Namely, VU at S U 1/2 at 2 is V2 U2. SCIENCE 112, where U is initial velocity of the object, which moves with uniform acceleration for time t, V is its final velocity, and S is the distance it traveled in time t. Middle dot. If an object moves in a circular path with uniform speed, its motion is called uniform circular motion. Exercises 1. An athlete completes one round of a circular track of diameter 200 meters in 40 seconds. What will be the distance covered and the displacement at the end of 2 minutes 20 seconds? 2. Joseph jogs from one end to the other end B of a straight 300 meters road in 2 minutes 30 seconds, and then turns around and jogs 100 meters back to point C in another 1 minute. What are Joseph's average speeds and velocities in jogging from A to B and B from A to C? 3. Abdul, while driving to school, computes the average speed for his trip to be 20 kilometers h1. On his return trip along the same route, there is less traffic and the average speed is 30 kilometers h1. What is the average speed for Abdul's trip? 4. A motorboat starting from rest on a lake accelerates in a straight line at a constant rate of 3.0 meters s2 for 8.0 seconds. How far does the boat travel during this time? 5. A driver of a car traveling at 52 kilometers h1 applies the brakes and accelerates uniformly in the opposite direction. The car stops in 5 seconds. Another driver going at 3 kilometers h1 in another car applies his brakes slowly and stops in 10 seconds. On the same graph paper, plot the speed versus time graphs for the two cars. Which of the two cars traveled farther after the brakes were applied? 6. Fig 8.11 shows the distance-time graph of three objects A, B and C. Study the graph and answer the following questions. Figure 8.11. Motion 113. Which of the three is traveling the fastest? B. Are all three ever at the same point on the road? C. How far has C traveled when B passes A? D. How far has B traveled by the time it passes C? 7. A ball is gently dropped from a height of 20 meters if its velocity increases uniformly at the rate of 10 meters s2. With what velocity will it strike the ground? After what time will it strike the ground? 8. The speed-time graph for a car is shown as figure 8.12. Figure 8.12. Find how far does a car travel in the first 4 seconds. Shade the area on the graph that represents the distance traveled by the car during the period. B. Which part of the graph represents uniform motion of the car? 9. State which of the following situations are possible and give an example for each of these. A. An object with a constant acceleration but with zero velocity. B. An object moving with an acceleration but with uniform speed. C. An object moving in a certain direction with an acceleration in the perpendicular direction. 10. An artificial satellite is moving in a circular orbit of radius 42,250 kilometers. Calculate its speed if it takes 24 hours to revolve around the Earth. In the previous chapter, we described the motion of an object along a straight line in terms of its position, velocity and acceleration. We saw that such a motion can be uniform or non-uniform. We have not yet discovered what causes the motion. Why does the speed of an object change with time? Do all motions require a cause? If so, what is the nature of this cause? In this chapter we shall make an attempt to quench all such curiosities. For many centuries, the problem of motion and its causes had puzzled scientists and philosophers. A ball on the ground, when given a small hit, does not move forever. Such observations suggest that rest is the natural state of an object. This remained the belief until Galileo Galilei and Isaac Newton developed an entirely different approach to understand motion. In our everyday life we observe that some effort is required to put a stationary object into motion or to stop a moving object. We ordinarily experience this as a muscular effort and say that we must push or hit or pull on an object to change its state of motion. The concept of force is based on this push, hit or pull. Let us now ponder about a force. What is it in fact? No one has seen, tasted or felt a force. However, we always see or feel the effect of a force. It can only be explained by describing what happens when a force is applied to an object. Pushing, hitting and pulling of objects are all ways of bringing objects in motion. Figure 9.1. They move because we make a force act on them. From your studies in earlier classes, you are also familiar with the fact that a force can be used to change the magnitude of velocity of an object, that is, to make the object move faster or slower or to change its direction of motion. We also know that a force can change the shape and size of objects. Figure 9.2. A. The trolley moves along the direction we push it. C. The hockey stick hits the ball forward. B. The drawer is pulled. Figure 9.1. Pushing, pulling, or hitting objects change their state of motion. A. B. Figure 9.2. A spring expands on application of force. B. A spherical rubber ball becomes oblong as we apply force on it. 9. FFF for C or C or C or C or and LLLL laws osas of OFA fem motion ocean chapped. Box with a small force. The box does not move because of friction acting in a direction opposite to the push. Figure 9.4a. This friction force arises between two surfaces in contact. In this case, between the bottom of the box and floor's rough surface. It balances the pushing force and therefore the box does not move. In figure 9.4b, the children push the box harder but the box still does not move. This is because the friction force still balances the pushing force. If the children push the box harder still, the pushing force becomes bigger than the friction force. Figure 9.4c. There is an unbalanced force. So the box starts moving. What happens when we ride a bicycle? When we stop pedaling, the bicycle begins to slow down. This is again because of the friction forces acting opposite to the direction of motion. In order to keep the bicycle moving, we have to start pedaling again. It thus appears that an object maintains its motion under the continuous application of an unbalanced force. However, it is quite incorrect. An object moves with a uniform velocity when the forces pushing force and frictional force acting on the object are balanced and there is no net external force on it. If an unbalanced force is applied on the object, there will be a change either in its speed or in the direction of its motion. Thus, to accelerate the motion of an object, an unbalanced force is required. And the change in its speed or in the direction of motion would continue as long as this unbalanced force is applied. However, if this force is 9.1 balanced and unbalanced forces, figure 9.3 shows a wooden block on a horizontal table. Two strings X and Y are tied to the two opposite faces of the block as shown. If we apply a force by pulling the string X, the block begins to move to the right. Similarly, if we pull the string Y, the block moves to the left. But, if the block is pulled from both the sides with equal forces, the block will not move. Such forces are called balanced forces and do not change the state of rest or of motion of an object. Now, let us consider a situation in which two opposite forces of different magnitudes pull the block. In this case, the block would begin to move in the direction of the greater force. Thus, the two forces are not balanced and the unbalanced force acts in the direction the block moves. This suggests that an unbalanced force acting on an object brings it in motion. Figure 9.3. Two forces acting on a wooden block. What happens when some children try to push a box on a rough floor if they push the ABC figure? 9.4 Force and Laws of Motion 11. NCERT 116 removed completely, the object would continue to move with the velocity it has acquired till then. 9.2 First Law of Motion. By observing the motion of objects on an inclined plane, Galileo deduced that objects move with a constant speed when no force acts on them. He observed that when a marble rolls down an inclined plane, its velocity increases. Figure 9.5a. In the next chapter, you will learn that the marble falls under the unbalanced force of gravity as it rolls down and attains a definite velocity by the time it reaches the bottom. Its velocity decreases when it climbs up as shown in figure 9.5b. Figure 9.5c shows a marble resting on an ideal frictionless plane inclined on both sides. Galileo argued that when the marble is released from left, it would roll down the slope and go up on the opposite side to the same height from which it was released. If the inclinations of the planes on both sides are equal, then the marble will climb the same distance that it covered while rolling down. If the angle of inclination of the right side plane were gradually decreased, then the marble would travel further distances till it reaches the original height. If the right side plane were ultimately made horizontal, that is, the slope is reduced to zero, the marble would continue to travel forever trying to reach the same height that it was released from. The unbalanced forces on the marble in this case are zero. It thus suggests that an unbalanced external force is required to change the motion of the marble, but no net force is needed to sustain the uniform motion of the marble. In practical situations, it is difficult to achieve a zero unbalanced force. This is because of the presence of the frictional force acting opposite to the direction of motion. Thus, in practice, the marble stops after traveling some distance. The effect of the frictional force may be minimized by using a smooth marble and a smooth plane and providing a lubricant on top of the planes. Figure 9.5. A. The downward motion. B. The upward motion of a marble on an inclined plane. And C. On a double inclined plane. Newton further studied Galileo's ideas on force and motion and presented three fundamental laws that govern the motion of objects. These three laws are known as Newton's laws of motion. The first law of motion is stated as, an object remains in a state of rest or of uniform motion in a straight line unless compelled to change that state by an applied force. In other words, all objects resist a change in their state of motion. In a qualitative way, the tendency of undisturbed objects to stay at rest or to keep moving with the same velocity is called inertia. This is why, the first law of motion is also known as the law of inertia. Certain experiences that we come across while traveling in a motor car can be explained on the basis of the law of inertia. We tend to remain at rest with respect to the seat until the driver applies a braking force to stop the motorcar. With the application of brakes, the car slows down, but our body tends to continue in the same state of motion because of its inertia. A sudden application of brakes may thus cause injury to us. Force and laws of motion. 117. Impact or collision with the panels in front. Safety belts are worn to prevent such accidents. Safety belts exert a force on our body to make the forward motion slower. An opposite experience is encountered when we are standing in a bus and the bus begins to move suddenly. Now we tend to fall backwards. This is because the sudden start of the bus brings motion to the bus as well as to our feet in contact with the floor of the bus. But the rest of our body opposes this motion because of its inertia. When a motorcar makes a sharp turn at a high speed, we tend to get thrown to one side. This can again be explained on the basis of the law of inertia. We tend to continue in our straight-line motion. When an unbalanced force is applied by the engine to change the direction of motion of the motorcar, we slip to one side of the seat due to the inertia of our body. The fact that a body will remain at rest unless acted upon by an unbalanced force can be illustrated through the following activities. Activity 9.1 Middle. Make a pile of similar carom coins on a table, as shown in figure 9.6. Middle. Attempt a sharp horizontal hit at the bottom of the pile using another carom coin or the striker. If the hit is strong enough, the bottom coin moves out quickly. Once the lowest coin is removed, the inertia of the other coins makes them fall vertically on the table. Galileo Galilei was born on the 15th of February 1564 in Pisa, Italy. Galileo, right from his childhood, had interest in mathematics and natural philosophy. But his father Vincenzo Galilei wanted him to become a medical doctor. Accordingly, Galileo enrolled himself for a medical degree at the University of Pisa in 1581, which he never completed because of his real interest in mathematics. In 1586, he wrote his first scientific book, The Little Balance La Balancita, in which he described Archimedes' method of finding the relative densities or specific gravities of substances using a balance. In 1589, in his series of essays De Motu, he presented his theories about falling objects using an inclined plane to slow down the rate of descent. In 1592, he was appointed professor of mathematics at the University of Padua in the Republic of Venice. Here he continued his observations on the theory of motion and through his study of inclined planes and the pendulum, formulated the correct law for uniformly accelerated objects that the distance the object moves is proportional to the square of the time taken. Galileo was also a remarkable craftsman. He developed a series of telescopes whose optical performance was much better than that of other telescopes available during those days. Around 1640, he designed the first pendulum clock. In his book Starry Messenger on his astronomical discoveries, Galileo claimed to have seen mountains on the Moon, the Milky Way made up of tiny stars, and 4 small bodies orbiting Jupiter. In his books Discourse on Floating Bodies and Letters on the Sunspots, he disclosed his observations of sunspots. Using his own telescopes and through his observations on Saturn and Venus, Galileo argued that all the planets must orbit the Sun and not the Earth, contrary to what was believed at that time. Galileo Galilei 1564–1642 Figure 9.6. Only the carom coin at the bottom of a pile is removed when a fast-moving carom coin or striker hits it. SCIENCE 118 5 rupees coin. If we use a 1 rupee coin, we find that a lesser force is required to perform the activity. A force that is just enough to cause a small car to pick up a large velocity will produce a negligible change in the motion of a train. This is because, in comparison to the cart, the train has a much lesser tendency to change its state of motion. Accordingly, we say that the train has more inertia than the cart. Clearly, heavier or more massive objects offer larger inertia. Quantitatively, the inertia of an object is measured by its mass. We may thus relate inertia and mass as follows. Inertia is the natural tendency of an object to resist a change in its state of motion or of rest. The mass of an object is a measure of its inertia. Questions 1. Which of the following has more inertia, a rubber ball and a stone of the same size? B. A bicycle and a train. C. A 5 rupees coin and a 1 rupee coin. 2. In the following example, try to identify the number of times the velocity of the ball changes. A football player kicks a football to another player of his team who kicks the football towards the goal. The goalkeeper of the opposite team collects the football and kicks it towards a player of his own team. Also identify the agent supplying the force in each case. 3. Explain why some of the leaves may get detached from a tree if we vigorously shake its branch. 4. Why do you fall in the forward direction when a moving bus brakes to a stop and fall backwards when it accelerates from rest? 9.4 Second law of motion. The first law of motion indicates that when an unbalanced external force acts on an activity. 9.2 Middle dot. Set a 5 rupee coin on a stiff card covering an empty glass tumbler standing on a table as shown in figure. 9.7 Middle dot. Give the card a sharp horizontal flick with a finger. If we do it fast, then the card shoots away, allowing the coin to fall vertically into the glass tumbler due to its inertia. Middle dot. The inertia of the coin tries to maintain its state of rest even when the card flows off. Figure 9.7 When the card is flicked with a finger, the coin placed over it falls in the tumbler. Activity 9.3 Middle dot. Place a water-filled tumbler on a tray. Middle dot. Hold the tray and turn around as fast as you can. Middle dot. We observe that the water spills. Why? Observe that a groove is provided in a saucer for placing the teacup. It prevents the cup from toppling over in case of sudden jerks. 9.3 Inertia and mass. All the examples and activities given so far illustrate that there is a resistance offered by an object to change its state of motion. If it is at rest, it tends to remain at rest. If it is moving, it tends to keep moving. This property of an object is called its inertia. Do all bodies have the same inertia? We know that it is easier to push an empty box than a box full of books. Similarly, if we kick a football, it flies away. But if we kick a stone of the same size with equal force, it hardly moves. We may, in fact, get an injury in our foot while doing so. Similarly, in activity 9.2, instead of a force and laws of motion 119 object, its velocity changes, that is, the object gets an acceleration. We would now like to study how the acceleration of an object depends on the force applied to it and how we measure a force. Let us recount some observations from our everyday life. During the game of table tennis, if the ball hits a player, it does not hurt him. On the other hand, when a fast-moving cricket ball hits a spectator, it may hurt him. A truck at rest does not require any attention when parked along a roadside. But a moving truck, even at speeds as low as 5 meters s1, may kill a person standing in its path. A small mass, such as a bullet, may kill a person when fired from a gun. These observations suggest that the impact produced by the objects depends on their mass and velocity. Similarly, if an object is to be accelerated, we know that a greater force is required to give a greater velocity. In other words, there appears to exist some quantity of importance that combines the object's mass and its velocity. One such property called momentum was introduced by Newton. The momentum, p, of an object is defined as the product of its mass, m, and velocity, v. That is, pmv. 9.1 momentum has both direction and magnitude. Its direction is the same as that of velocity, v. The c unit of momentum is kilogram-meter per second, kilograms ms1. Since the application of an unbalanced force brings a change in the velocity of the object, it is therefore clear that a force also produces a change of momentum. Let us consider a situation in which a car with a dead battery is to be pushed along a straight road to give it a speed of 1 meter s1, which is sufficient to start its engine. If one or two persons give a sudden push and balanced force to it, it hardly starts. But a continuous push over some time results in a gradual acceleration of the car to this speed. It means that the change of momentum of the car is not only determined by the magnitude of the force, but also by the time during which the force is exerted. It may then also be concluded that the force necessary to change the momentum of an object depends on the time rate at which the momentum is changed. The second law of motion states that the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of force. 9.4.1 Mathematical formulation of second law of motion. Suppose an object of mass, m, is moving along a straight line with an initial velocity, u. It is uniformly accelerated to velocity, v, in time, t, by the application of a constant force, F, throughout the time, t. The initial and final momentum of the object will be p1 mu and p2 mv respectively. The change in momentum p2 p1 mv mu m times vu. The rate of change of momentum times mvut, or the applied force, F times mvut times kilometers vut. F 9.2 km 9.3. Here a vut is the acceleration, which is the rate of change of velocity. The quantity, k, is a constant of proportionality. The c units of mass and acceleration are kilograms and ms2 respectively. The unit of force is so chosen that the value of the constant, k, becomes 1. For this, 1 unit of force is defined as the amount that produces an acceleration of 1 meter s2 in an object of 1 kilogram mass. That is, 1 unit of force k times 1 kilogram times 1 meter s2. Thus, the value of k becomes 1. From Eq. 9.3 F mu 9.4. The unit of force is kilograms ms2 or Newton, which has a simple and the second law. NCERT 120 motion gives us a method to measure the force acting on an object as a product of its mass and acceleration. The second law of motion is often seen in action in our everyday life. Have you noticed that while catching a fast-moving cricket ball, a fielder in the ground gradually pulls his hands backwards with the moving ball? In doing so, the fielder increases the time during which the high velocity of the moving ball decreases to 0. Thus, the acceleration of the ball is decreased and therefore the impact of catching the fast-moving ball. Figure 9.8 is also reduced. If the ball is stopped suddenly, then its high velocity decreases to 0 in a very short interval of time. Thus, the rate of change of momentum of the ball will be large. Therefore, a large force would have to be applied for holding the catch that may hurt the palm of the fielder. In a high-jump athletic event, the athletes are made to fall either on a cushioned bed or on a sandbed. This is to increase the time of the athlete's fall to stop after making the jump. This decreases the rate of change of momentum and hence the force. Try to ponder how a karate player breaks a slab of ice with a single blow. The first law of motion can be mathematically stated from the mathematical expression for the second law of motion. Eq. 9.4 is F ma, or Fmvut 9.5 or 4 mv mu, that is, when f0, vu for whatever time, t is taken. This means that the object will continue moving with uniform velocity, u, throughout the time, t. If u is 0, then v will also be 0. That is, the object will remain at rest. Example 9.1. A constant force acts on an object of mass 5 kilograms for a duration of 2 seconds. It increases the object's velocity from 3 meters s1 to 7 meters s1. Find the magnitude of the applied force. Now, if the force was applied for a duration of 5 seconds, what would be the final velocity of the object? Solution. We have been given that u 3 meters s1 and v 7 meters s1, t 2 seconds and m 5 kilograms. From Eq. 9.5 we have FMVUT substitution of values in this relation gives F 5 kg 7 meters S1, 3 meters S1, 2 seconds, 10 m. Now, if this force is applied for a duration of 5 seconds t 5 seconds, then the final velocity can be calculated by rewriting eq. 9.5 as Fort VUM. On substituting the values of u, f, m and t, we get the final velocity, v 13 meters S1. Figure 9.8, a fielder pulls his hands gradually with the moving ball while holding a catch. Force and laws of motion 121. Example 9.2, which would require a greater force accelerating a 2 kg mass at 5 meters S2 or a 4 kg mass at 2 meters S2 solution, from eq. 9.4, we have F ma. Here we have M1 2 kg, A1 5 meters S2 and square meters 4 kg, A2 2 meters S2. Thus, F1 M1 A1 2 kg times 5 meters S2 10 n, and F2 M2 A2 4 kg times 2 meters S2 8 n. F1 greater than F2. Thus, accelerating a 2 kg mass at 5 meters S2 would require a greater force. Example 9.3, a motor car is moving with a velocity of 108 km/h and it takes 4 seconds to stop after the brakes are applied. Calculate the force exerted by the brakes on the motor car if its mass along with the passengers is 1000 kg. Solution: the initial velocity of the motor car u 108 km h 108 times 1000 meters 60 times 60 seconds 30 meters S1 and the final velocity of the motor car v 0 meters S1. The total mass of the motor car along with its passengers 1000 kg and the time taken to stop the motor car, t 4 seconds. From eq. 9.5 we have the magnitude of the force F applied by the brakes as mvut. On substituting the values, we get F 1000 kg times 0 30 ms1 4 seconds 7500 kg ms2 or 7500, and the negative sign tells us that the force exerted by the brakes is opposite to the direction of motion of the motor car. Example 9.4, a force of 5 n gives a mass m1, and acceleration of 10 meters s2 and a mass square meters, and acceleration of 20 meters s2. What acceleration would it give if both the masses were tied together? Solution: from eq. 9.4 we have m1 fa1, and square meters fa2. Here, a1 10 meters s2, a2 20 meters s2 and f5n, thus, m1 5n 10 meters s2 0.50 kilograms, and square meters 5n 20 meters s2 0.25 kilograms. If the two masses were tied together, the total mass, m would be m 0.50 kilograms 0.25 kilograms 0.75 kilograms. The acceleration, produced in the combined mass by the 5n force would be, Fm 5n 0.75 kilograms 6.67 meters s2. Example 9.5, the velocity time graph of a ball of mass 20 grams moving along a straight line on a long table is given in figure 9.9. Figure 9.9. How much force does the table exert on the ball to bring it to rest? Solution: the initial velocity of the ball is 20 centimeters s1. Due to the frictional force exerted by the table, the velocity of the ball decreases down to 0 in 10 seconds. Thus, u 20 centimeters s1, v 0 centimeters s1 and t 10 seconds. Since the velocity time graph is a straight line, it is clear that the ball moves with a constant acceleration. The acceleration is vu at t 0 centimeters s1, 20 centimeters s1, 10 seconds, 2 centimeters s2, 0.02 meters s2. The force exerted on the ball F is, F ma 21,000 kilograms times 0.02 meters s2, 0.0004, and the negative sign implies that the frictional force exerted by the table is opposite to the direction of motion of the ball. 9.5 Third law of motion. The first two laws of motion tell us how an applied force changes the motion and provide us with a method of determining the force. The third law of motion states that when one object exerts a force on another object, the second object instantaneously exerts a force back on the first. These two forces are always equal in magnitude but opposite in direction. These forces act on different objects and never on the same object. In the game of football, sometimes we, while looking at the football and trying to kick it with a greater force, collide with a player of the opposite team. Both feel hurt because each applies a force to the other. In other words, there is a pair of forces and not just one force. The two opposing forces are also known as action and reaction forces. Let us consider two spring balances connected together as shown in figure 9.10. The fixed end of balance B is attached with a rigid support, like a wall. When a force is applied through the free end of spring balance A, it is observed that both the spring balances show the same readings on their scales. It means that the force exerted by spring balance on balance B is equal but opposite in direction to the force exerted by the balance B on balance A. Any of these two forces can be called as action and the other as reaction. This gives us an alternative statement of the third law of motion, that is, to every action there is an equal and opposite reaction. However, it must be remembered that the action and reaction always act on two different objects simultaneously. Figure 9.10. Action and reaction forces are equal and opposite. Suppose you are standing at rest and intend to start walking on a road. You must accelerate, and this requires a force in accordance with the second law of motion. Which is this force? Is it the muscular effort you exert on the road? Is it in the direction we intend to move? No, you push the road below backwards. The road exerts an equal and opposite force on your feet to make you move forward. It is important to note that even though the action and reaction forces are always equal in magnitude, these forces may not produce accelerations of equal magnitudes. This is because each force acts on a different object that may have a different mass. When a gun is fired, it exerts a forward force on the bullet. The bullet exerts an equal and opposite force on the gun. This results in the recoil of the gun. Figure 9.11. Since the gun has a much greater mass than the bullet, the acceleration of the gun is much less than the acceleration of the bullet. The third law of motion can also be illustrated when a sailor jumps out of a rowing boat. As the sailor jumps forward, the force on the boat moves it backwards. Figure 9.12. Figure 9.11. A forward force on the bullet and recoil of the gun. Force and laws of motion 123. The cart shown in this activity can be constructed by using a 12 mm or 18 mm thick plywood board of about 50 cm times 100 cm with two pairs of hard ball-bearing wheels. Skate wheels are good to use. Skateboards are not as effective because it is difficult to maintain straight line motion. 9.6 Conservation of momentum. Suppose two objects, two balls and B, say of masses milliampere and mb, are traveling in the same direction along a straight line at different velocities u and u, respectively. Figure 9.14a. And there are no other external unbalanced forces acting on them. Let u greater than u and the two balls collide with each other as shown in figure 9.14b. During collision, which lasts for a time t, the ball A exerts a force Fab on ball B and the ball B exerts a force V on ball A. Suppose V and VB are the velocities of the two balls A and B after the collision, respectively. Figure 9.14c. Activity 9.4 Middle. Request two children to stand on two separate carts as shown in figure 9.13. Middle. Give them a bag full of sand or some other heavy object. Ask them to play a game of catch with the bag. Middle dot. Does each of them experience an instantaneous force as the result of throwing the sandbag? Middle dot. You can paint a white line on cartwheels to observe the motion of the two carts when the children throw the bag towards each other. Figure 9.12. As the sailor jumps in forward direction, the boat moves backwards. Figure 9.13. Now, place two children on one cart and one on another cart. The second law of motion can be seen, as this arrangement would show different accelerations for the same force. Figure 9.14. Conservation of momentum in collision of two balls. From EC. 9.1. The momentum plural of momentum of ball before and after the collision are ma and mava, respectively. The rate of change of its momentum or fab during the collision will be a VUMT. Similarly, the rate of change of momentum of ball beef during the collision will be BBBVUMT. According to the third law of motion, the force fab exerted by ball on ball. NCERT 124 Activity 9.6 Middle dot. Take a test tube of good quality glass material and put a small amount of water in it. Place a stop cork at the mouth of it. Middle dot. Now suspend the test tube horizontally by two strings or wires as shown in figure 9.16. Middle dot. Heat the test tube with a burner until water vaporizes and the cork blows out. Middle dot. Observe that the test tube recoils in the direction opposite to the direction of the cork. And the force exerted by the ball B on ball A must be equal and opposite to each other. Therefore, Fab 9.6 or a VUMT BBBVUMT. This gives Mao and Bub Mava MBVB 9.7 since Mao and Bub is the total momentum of the two balls A and B before the collision and Mava MBVB is their total momentum after the collision. From EC. 9.7 we observe that the total momentum of the two balls remains unchanged or conserved provided no other external force acts. As a result of this ideal collision experiment, we say that the sum of momenta of the two objects before collision is equal to the sum of momenta after the collision provided there is no external unbalanced force acting on them. This is known as the law of conservation of momentum. This statement can alternatively be given as the total momentum of the two objects is unchanged or conserved by the collision. Activity 9.5 Middle dot. Take a big rubber balloon and inflate it fully. Tie its neck using a thread. Also using adhesive tape, fix a straw on the surface of this balloon. Middle dot. Pass a thread through the straw and hold one end of the thread in your hand or fix it on the wall. Middle dot. Ask your friend to hold the other end of the thread or fix it on a wall at some distance. This arrangement is shown in figure 9.15. Middle dot. Now remove the thread tied on the neck of balloon. Let the air escape from the mouth of the balloon. Middle dot. Observe the direction in which the straw moves. Figure 9.15 Figure 9.16 Middle dot. Also, observe the difference in the velocity the cork appears to have and that of the recoiling test tube. Example 9.6 A bullet of mass 20 grams is horizontally fired with a velocity 150 meters s1 from a pistol of mass 2 kilograms. What is the recoil velocity of the pistol solution? We have the mass of bullet, M1, 20 grams, 0.02 kilograms and the mass of the pistol, square meters 2 kilograms. Initial velocities of the bullet U1 and pistol U2, 0, respectively. The final velocity of the bullet, V1 150 meters s1. The direction of bullet is taken from left to right positive, by convention, figure 9.17. Let V be the recoil velocity of the pistol. Total momenta of the pistol and bullet before the fire. When the gun is at rest 0.02 kilograms times 0 meters s1 0 kilograms ms1 total moment of the pistol and bullet after it is fired 0.02 kilograms times 150 meters s1 2 kilograms times vms1 32 v kilograms ms1 according to the law of conservation of momentum. Total moment after the fire, total momenta before the fire 32 v 0 v 1.5 meters s1. Negative sign indicates that the direction in which the pistol would recoil is opposite to that of bullet, that is, right to left. Example 9.7 A girl of mass 40 kilograms jumps with a horizontal velocity of 5 meters s1 onto a stationary cart with frictionless wheels. The mass of the cart is 3 kilograms. What is her velocity as the cart starts moving? Assume that there is no external unbalanced force working in the horizontal direction. Solution: let v be the velocity of the girl on the cart as the cart starts moving. The total moment of the girl and cart before the interaction 40 kilograms times 5 meters s1 3 kilograms times 0 meters s1 200 kilograms ms1. Total moment after the interaction 43 kilograms times vms1 43 v kilograms ms1. According to the law of conservation of momentum, the total momentum is conserved during the interaction. That is, 43 v 200 v 200 43 4.65 meters s1. The girl on cart would move with a velocity of 4.65 meters s1 in the direction in which the girl jumped. Figure 9.18. Figure 9.17, recoil of a pistol. Figure 9.18, the girl jumps onto the cart. B. SCIENCE 126 Example 9.82 Hockey players of opposite teams, while trying to hit a hockey ball on the ground, collide and immediately become entangled. One has a mass of 60 kilograms and was moving with a velocity 5.0 meters s1 while the other has a mass of 55 kilograms and was moving faster with a velocity 6.0 meters s1 towards the first player. In which direction and with what velocity will they move after they become entangled? Assume that the frictional force acting between the feet of the two players and ground is negligible. Solution: if v is the velocity of the two entangled players after the collision, the total momentum then m1 square meters times v 60 55 kilograms times vms1 115 times v kilograms ms1. Equating the momenta of the system before and after collision, in accordance with the law of conservation of momentum, we get v 30,115 0.26 meters s1. Thus, the two entangled players would move with velocity 0.26 meters s1 from right to left, that is, in the direction the second player was moving before the collision. Figure 9.19, a collision of two hockey players, A before collision and B after collision. Let the first player be moving from left to right. By convention, left to right is taken as the positive direction and thus right to left is the negative direction. Figure 9.19. If simple m and u represent the mass and initial velocity of the two players, respectively. Subscripts 1 and 2 and these physical quantities refer to the two hockey players. Thus, m1 60 kilograms, u1 5 meters s1, and square meters 55 kilograms, u2 6 meters s1. The total momentum of the two players before the collision 60 kilograms times 5 meters s1 55 kilograms times 6 meters s1 30 kilograms ms1. Questions 1. If action is always equal to the reaction, explain how a horse can pull a cart. 2. Explain, why is it difficult for a fireman to hold a hose, which ejects large amounts of water at a high velocity? 3. From a rifle of mass 4 kilograms, a bullet of mass 50 grams is fired with an initial velocity of 35 meters s1. Calculate the initial recoil velocity of the rifle. Force and laws of motion 127 4. Two objects of masses 100 grams and 200 grams are moving along the same line and direction with velocities of 2 meters s1 and 1 meter s1, respectively. They collide, and after the collision, the first object moves at a velocity of 1.67 meters s1. Determine the velocity of the second object. What you have learned. First law of motion: an object continues to be in a state of rest or of uniform motion along a straight line unless acted upon by an unbalanced force. The natural tendency of objects to resist a change in their state of rest or of uniform motion is called inertia. The mass of an object is a measure of its inertia. Its C unit is kilograms. Force of friction always opposes motion of objects. Second law of motion: the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of the force. The C unit of force is kilograms ms2. This is also known as Newton and represented by the symbol N. A force of 1 Newton produces an acceleration of 1 meter s2 on an object of mass 1 kilogram. The momentum of an object is the product of its mass and velocity and has the same direction as that of the velocity. Its C unit is kilograms ms1. Third law of motion: to every action, there is an equal and opposite reaction, and they act on two different bodies. In an isolated system where there is no external force, the total momentum remains conserved. Conservation laws: all conservation laws such as conservation of momentum, energy, angular momentum, charge etc. are considered to be fundamental laws in physics. These are based on observations and experiments. It is important to remember that a conservation law cannot be proved. It can be verified, or disproved, by experiments. An experiment whose result is in conformity with the law verifies or substantiates the law. It does not prove the law. On the other hand, a single experiment whose result goes against the law is enough to disprove it. The law of conservation of momentum has been deduced from large number of observations and experiments. This law was formulated nearly 3 centuries ago. It is interesting to note that not a single situation has been realized so far, which contradicts this law. Several experiences of everyday life can be explained on the basis of the law of conservation of momentum. NCERT 128 Exercises 1. An object experiences a net zero external unbalanced force. Is it possible for the object to be traveling with a non-zero velocity? If yes, state the conditions that must be placed on the magnitude and direction of the velocity. If no, provide a reason. 2. When a carpet is beaten with a stick, dust comes out of it. Explain. 3. Why is it advised to tie any luggage kept on the roof of a bus with a rope? 4. A batsman hits a cricket ball which then rolls on a level ground. After covering a short distance, the ball comes to rest. The ball slows to a stop because the batsman did not hit the ball hard enough. B. Velocity is proportional to the force exerted on the ball. C. There is a force on the ball opposing the motion. D. There is no unbalanced force on the ball, so the ball would want to come to rest. 5. A truck starts from rest and rolls down a hill with a constant acceleration. It travels a distance of 400 meters in 20 seconds. Find its acceleration. Find the force acting on it if its mass is 7 tons and 1 ton 1000 kilograms. 6. A stone of 1 kilogram is thrown with a velocity of 20 meters s1 across the frozen surface of a lake and comes to rest after traveling a distance of 50 meters. What is the force of friction between the stone and the ice? 7. A 8,000 kilograms engine pulls a train of 5 wagons, each of 2,000 kilograms, along a horizontal track. If the engine exerts a force of 40,000 N and the track offers a friction force of 5,000 N, then calculate A. The net accelerating force, and B. The acceleration of the train. 8. An automobile vehicle has a mass of 1500 kilograms. What must be the force between the vehicle and road if the vehicle is to be stopped with a negative acceleration of 1.7 meters s2? 9. What is the momentum of an object of mass m, moving with a velocity v a m v2 b m v2 c 1/2 m v2 d m v10? Using a horizontal force of 200 N, we intend to move a wooden cabinet across a floor at a constant velocity. What is the friction force that will be exerted on the cabinet? 11. Two objects, each of mass 1.5 kilograms, are moving in the same straight line but in opposite directions. The velocity of each object is 2.5 meters s1 before the collision, during which the stick together. What will be the velocity of the combined object after collision? 12. According to the third law of motion, when we push on an object, the object pushes back on us with an equal and opposite force. If the object is a massive truck parked along the roadside, it will probably not move. A student justifies this by answering that the two opposite and equal forces cancel each other. Comment on this logic and explain why the truck does not move. 13. A hockey ball of mass 200 grams traveling at 10 meters s1 is struck by a hockey stick so as to return it along its original path with a velocity at 5 meters s1. Calculate the magnitude of change of momentum occurred in the motion of the hockey ball by the force applied by the hockey stick. 14. A bullet of mass 10 grams traveling horizontally with a velocity of 150 meters s1 strikes a stationary wooden block and comes to rest in 0.03 seconds. Calculate the distance of penetration of the bullet into the block. Also calculate the magnitude of the force exerted by the wooden block on the bullet. 15. An object of mass 1 kilogram traveling in a straight line with a velocity of 10 meters s1 collides with, and sticks to, a stationary wooden block of mass 5 kilograms. Then they both move off together in the same straight line. Calculate the total momentum just before the impact and just after the impact. Also, calculate the velocity of the combined object. 16. An object of mass 100 kilograms is accelerated uniformly from a velocity of 5 meters s1 to 8 meters s1 in 6 seconds. Calculate the initial and final momentum of the object. Also, find the magnitude of the force exerted on the object. 17. Actor Kiran and Rahul were riding in a motor car that was moving with a high velocity on an expressway when an insect hit the windshield and got stuck on the windscreen. Actor and Kiran started pondering over the situation. Kiran suggested that the insect suffered a greater change in momentum as compared to the change in momentum of the motor car, because the change in the velocity of the insect was much more than that of the motor car. Actor said that since the motor car was moving with a larger velocity, it exerted a larger force on the insect. And as a result the insect died. Rahul, while putting an entirely new explanation, said that both the motor car and the insect experienced the same force and a change in their momentum. Comment on these suggestions. 18. How much momentum will a dumbbell of mass 10 kilograms transfer to the floor if it falls from a height of 80 centimeters? Take its downward acceleration to be 10 meters s2. NCERT 130 additional exercises. A1. The following is the distance timetable of an object in motion. Time in seconds, distance in meters: 0, 0, 1, 1, 2, 8, 3, 27, 4, 64, 5, 125, 6, 216, 7, 343. What conclusion can you draw about the acceleration? Is it constant, increasing, decreasing, or 0? B. What do you infer about the forces acting on the object? A2. Two persons managed to push a motor car of mass 1200 kilograms at a uniform velocity along a level road. the same motor car can be pushed by 3 persons to produce an acceleration of 0.2 meters s2. With what force does each person push the motor car? Assume that all persons push the motor car with the same muscular effort. A3. A hammer of mass 500 grams, moving at 50 meters s1, strikes a nail. The nail stops the hammer in a very short time of 0.01 seconds. What is the force of the nail on the hammer? A4. A motor car of mass 1200 kilograms is moving along a straight line with a uniform velocity of 90 km/h. Its velocity is slowed down to 18 km/h in 4 seconds by an unbalanced external force. Calculate the acceleration and change in momentum. Also calculate the magnitude of the force required. In chapters 8 and 9, we have learned about the motion of objects and force as the cause of motion. We have learned that a force is needed to change the speed or the direction of motion of an object. We always observe that an object dropped from a height falls towards the earth. We know that all the planets go around the sun. The moon goes around the earth. In all these cases, there must be some force acting on the objects, the planets and on the moon. Isaac Newton could grasp that the same force is responsible for all these. This force is called the gravitational force. In this chapter we shall learn about gravitation and the universal law of gravitation. We shall discuss the motion of objects under the influence of gravitational force on the earth. We shall study how the weight of a body varies from place to place. We shall also discuss the conditions for objects to float in liquids. 10.1 Gravitation. We know that the moon goes around the earth. An object when thrown upwards, reaches a certain height and then falls downwards. It is said that when Newton was sitting under a tree, an apple fell on him. The fall of the apple made Newton start thinking. He thought that, if the earth can attract an apple, can it not attract the moon? Is the force the same in both cases? He conjectured that the same type of force is responsible in both the cases. He argued that at each point of its orbit, the moon falls towards the earth, instead of going off in a straight line. So, it must be attracted by the earth. But we do not really see the moon falling towards the earth. Let us try to understand the motion of the moon by recalling Activity 8.11. Activity 10.1 Middle dot. Take a piece of thread. Middle dot. Tie a small stone at one end. Hold the other end of the thread and whirl it around, as shown in figure. 10.1. Middle dot. Note the motion of the stone. Middle dot. Release the thread. Middle dot again, note the direction of motion of the stone. Figure 10.1, a stone describing a circular path with a velocity of constant magnitude. Before the thread is released, the stone moves in a circular path with a certain speed and changes direction at every point. The change in direction involves change in velocity or acceleration. The force that causes this acceleration and keeps the body moving along the circular path is acting towards the center. This force is called the centripetal, meaning center-seeking force. In the absence of this 10 GGG gravitation chapter. SCIENCE 132.10.1.1 Universal Law of Gravitation. Every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. The force is along the line joining the centers of two objects. Force: the stone flies off along a straight line. This straight line will be a tangent to the circular path. More to know: tangent to a circle, a straight line that meets the circle at one and only one point is called a tangent to the circle. Straight line ABC is a tangent to the circle at point B. The motion of the moon around the earth is due to the centripetal force. The centripetal force is provided by the force of attraction of the earth. If there were no such force, the moon would pursue a uniform straight line motion. It is seen that a falling apple is attracted towards the earth. Does the apple attract the Earth? If so, we do not see the Earth moving towards an apple. Why? According to the third law of motion, the apple does attract the Earth. But according to the second law of motion, for a given force, acceleration is inversely proportional to the mass of an object e. 9.4. The mass of an apple is negligibly small compared to that of the Earth. So, we do not see the Earth moving towards the apple. Extend the same argument for why the Earth does not move towards the Moon. In our solar system, all the planets go around the Sun. By arguing the same way, we can say that there exists a force between the Sun and the planets. From the above facts, Newton concluded that not only does the Earth attract an apple and the Moon, but all objects in the universe attract each other. This force of attraction between objects is called the gravitational force. G2mmFD figure 10.2. The gravitational force between two uniform objects is directed along the line joining their centers. Let two objects A and B of masses m and n lie at a distance d from each other as shown in figure 10.2. Let the force of attraction between two objects be F according to the universal law of gravitation. The force between two objects is directly proportional to the product of their masses. That is, Fm times m. 10.1, and the force between two objects is inversely proportional to the square of the distance between them, that is, 2, 1 Fd 10.2 combining x. 10.1 and 10.2, we get F2 times mmd 10.3 or G2m times mfd 10.4 where G is a constant of proportionality and is called the universal gravitation constant. By multiplying crosswise, eq. 10.4 gives F times d2 gm times m. Gravitation 133. Isaac Newton was born in Woolsthorpe near Grantham, England. He is generally regarded as the most original and influential theorist in the history of science. He was born in a poor farming family. But he was not good at farming. He was sent to study at Cambridge University in 1661. In 1665 a plague broke out in Cambridge, and so Newton took a year off. It was during this year that the incident of the apple falling on him is said to have occurred. This incident prompted Newton to explore the possibility of connecting gravity with the force that kept the Moon in its orbit. This led him to the universal law of gravitation. It is remarkable that many great scientists before him knew of gravity but failed to realize it. Newton formulated the well-known laws of motion. He worked on theories of light and color. He designed an astronomical telescope to carry out astronomical observations. Newton was also a great mathematician. He invented a new branch of mathematics, called calculus. He used it to prove that for objects outside a sphere of uniform density, the sphere behaves as if the whole of its mass is concentrated at its center. Newton transformed the structure of physical science with his three laws of motion and the universal law of gravitation. As the keystone of the scientific revolution of the 17th century, Newton's work combined the contributions of Copernicus, Kepler, Galileo, and others into a new powerful synthesis. It is remarkable that though the gravitational theory could not be verified at that time, there was hardly any doubt about its correctness. This is because Newton based his theory on sound scientific reasoning and backed it with mathematics. This made the theory simple and elegant. These qualities are now recognized as essential requirements of a good scientific theory. Isaac Newton 1642–1727. How did Newton guess the inverse square rule? There has always been a great interest in the motion of planets. By the 16th century, a lot of data on the motion of planets had been collected by many astronomers. Based on these data, Johannes Kepler derived three laws, which govern the motion of planets. These are called Kepler's laws. These are, 1. The orbit of a planet is an ellipse with the Sun at one of the foci, as shown in the figure given below. In this figure O is the position of the Sun. 2. the line joining the planet and the Sun sweep equal areas in equal intervals of time. Thus, if the time of travel from A to B is the same as that from C to D, then the areas OAB and OCT are equal. 3. The cube of the mean distance of a planet from the Sun is proportional to the square of its orbital period T, or R3T2 constant. It is important to note that Kepler could not give a theory to explain the motion of planets. It was Newton who showed that the cause of the planetary motion is the gravitational force that the Sun exerts on them. Newton used the third law of Kepler to calculate the gravitational force of attraction. The gravitational force of the Earth is weakened by distance. A simple argument goes like this. We can assume that the planetary orbits are circular. Suppose the orbital velocity is v and the radius of the orbit is r. Then the force acting on an orbiting planet is given by F v2r. If t denotes the period, then v2rt, so that v2r2t2. We can rewrite this as v21r times r3t2. Since r3t2 is constant by Kepler's third law, we have v21r. Combining this with fv2r, we get f1r2. ABCDO. SCIENCE 134 from EC. 10.4. The force exerted by the Earth on the Moon is G2m times MFD 11, 2, 2, 24, 22, 8, 2, 6.7, 10 nm kilograms 6, 10 kilograms 7.4, 10 kilograms 3.84 10 meters times 2.02 times 1020 and thus the force exerted by the Earth on the Moon is 2.02 times 1020 n. Questions 1. State the universal law of gravitation. 2. Write the formula to find the magnitude of the gravitational force between the Earth and an object on the surface of the Earth. 10.1.2 Importance of the universal law of gravitation. The universal law of gravitation successfully explained several phenomena which were believed to be unconnected, I. The force that binds us to the Earth. 2. The motion of the Moon around the Earth. 3. The motion of planets around the Sun. And I. The tides due to the Moon and the Sun. 10.2 Free fall. Let us try to understand the meaning of free fall by performing this activity. Activity 10.2 Middle dot. Take a stone. Middle dot. Throw it upwards. Middle dot. It reaches a certain height and then it starts falling down. We have learned that the Earth attracts objects towards it. This is due to the gravitational force. Whenever objects fall towards the Earth under this force alone, we say that the objects are in free fall. Is there any or 2g times FDMM 10.5 The C unit of g can be obtained by substituting the units of force, distance and mass in E. 10.5 is n square meters kilograms 2. The value of g was found out by Henry Cavendish 1731-1810 by using a sensitive balance. The accepted value of g is 6.673 times 1011 n square meters kilograms 2. We know that there exists a force of attraction between any two objects. Compute the value of this force between you and your friend sitting close by. Conclude how you do not experience this force. The law is universal in the sense that it is applicable to all bodies. Whether the bodies are big or small, whether they are celestial or terrestrial. Inverse square. Saying that f is inversely proportional to the square of d means, for example, that if d gets bigger by a factor of 6, f becomes 136 times smaller. Example 10.1 The mass of the Earth is 6 times 1024 kilograms and that of the Moon is 7.4 times 1022 kilograms if the distance between the Earth and the Moon is 3.84 times 105 kilometers. Calculate the force exerted by the Earth on the Moon. Take g 6.7 times 1011 n square meters kilograms 2 Solution. The mass of the Earth, m 6 times 1024 kilograms The mass of the Moon, m 7.4 times 1022 kilograms, the distance between the Earth and the Moon. D 3.84 times 105 kilometers, 3.84 times 105 times 1000 meters, 3.84 times 108 meters. G 6.7 times 1011 n square meters, kilograms. 2 more to know. Q. Gravitation 135 calculations. We can take G to be more or less constant on or near the Earth. But for objects far from the Earth, the acceleration due to gravitational force of Earth is given by E. 10.7. 10.2.1 To calculate the value of G. To calculate the value of G, we should put the values of G, m and r in eq. 10.9, namely, universal gravitational constant, G 6.7 times 1011 n square meters, kilograms. 2, mass of the Earth, m 6 times 1024 kilograms, and radius of the Earth, r 6.4 times 106 meters. G2 mgr 11 2 2 24 6 2 6.7 10 nm kilograms 6 10 kilograms 6.4 10 meters times 9.8 meters s2. Thus, the value of acceleration due to gravity of the Earth, G 9.8 meters s2. 10.2.2 Motion of objects under the influence of gravitational force of the Earth. Let us do an activity to understand whether all objects, hollow or solid, big or small, will fall from a height at the same rate. Activity 10.3 Middle. Take a sheet of paper and a stone. Drop them simultaneously from the first floor of a building. Observe whether both of them reach the ground simultaneously. Middle. We see that paper reaches the ground little later than the stone. This happens because of air resistance. The air offers resistance due to friction to the motion of the falling objects. The resistance offered by air to the paper is more than the resistance offered to the stone. If we do the experiment in a glass jar from which air has been sucked out, the paper and the stone would fall at the same rate. Change in the velocity of falling objects. While falling, there is no change in the direction of motion of the objects. But due to the Earth's attraction, there will be a change in the magnitude of the velocity. Any change in velocity involves acceleration. Whenever an object falls towards the Earth, an acceleration is involved. This acceleration is due to the Earth's gravitational force. Therefore, this acceleration is called the acceleration due to the gravitational force of the Earth, or acceleration due to gravity. It is denoted by g. The unit of g is the same as that of acceleration, that is, ms2. We know from the second law of motion that force is the product of mass and acceleration. Let the mass of the stone in activity 10.2 be m. We already know that there is acceleration involved in falling objects due to the gravitational force, and is denoted by g. Therefore the magnitude of the gravitational force F will be equal to the product of mass and acceleration due to the gravitational force, that is, Fmg 10.6 from x. 10.4 and 10.6 we have 2g times mmmgd or g2mgd 10.7, where m is the mass of the Earth, and d is the distance between the object and the Earth. Let an object be on or near the surface of the Earth. The distance d in e. 10.7 will be equal to r, the radius of the Earth. Thus, for objects on or near the surface of the Earth, g2m times m milligrams are 10.8 g2m gr 10.9. The Earth is not a perfect sphere. As the radius of the Earth increases from the poles to the equator, the value of g becomes greater at the poles than at the equator. For most NCERT 136 we know that an object experiences acceleration during free fall. From Eq. 10.9, this acceleration experienced by an object is independent of its mass. This means that all objects, hollow or solid, big or small, should fall at the same rate. According to a story, Galileo dropped different objects from the top of the Leaning Tower of Pisa in Italy to prove the same. As g is constant near the Earth, all the equations for the uniformly accelerated motion of objects become valid with acceleration replaced by g. See section 8.5. The equations are Vu at 10.10 s U1, 2 at 2, 10.11 V2 U2, 2 is 10.12 where U and V are the initial and final velocities and s is the distance covered in time, t. In applying these equations, we will take acceleration, a to be positive when it is in the direction of the velocity, that is, in the direction of motion. The acceleration, a will be taken as negative when it opposes the motion. Example 10.2 A car falls off a ledge and drops to the ground in 0.5 seconds. Let g 10 meters s2 for simplifying the calculations. I. What is its speed on striking the ground? 2. What is its average speed during the 0.5 seconds? 3. How high is the ledge from the ground? Solution. Time. t 1/2 second initial velocity, u 0 meters s1 acceleration due to gravity, g 10 meters s2 acceleration of the car. A 10 meters s2 downward I speed v 10 meters s2 times 0.5 seconds, 5 meters s1 2 average speed 2 u v 0 meters s1, 5 meters s1, 2, 2.5 meters s1 3 distance traveled. S1 half a t2 and 1/2 times 10 meters s2 times 0.5 seconds 2 and 1/2 times 10 meters s2 times 0.25 seconds 2 1.25 meters. Thus, I its speed on striking the ground 5 meters s1 2 its average speed during the 0.5 seconds 2.5 meters s1 3 height of the ledge from the ground 1.25 meters. Example 10.3 An object is thrown vertically upwards and rises to a height of 10 meters. Calculate I the velocity with which the object was thrown upwards and 2 the time taken by the object to reach the highest point. Solution. Distance traveled, s 10 meters final velocity, v 0 meters s1 acceleration due to gravity, g 9.8 meters s2 acceleration of the object. A 9.8 meters s2 upward motion IV2 U2, 2 AS0 U2, 2 times 9.8 meters s2 times 10 meters U2, 2 times 9.8 times 10 meters 2 S2 U 196 meters S1 U 14 meters S1 2 VU a T0, 14 meters S1, 9.8 meters S2 times TT 1.43 seconds. Thus, I initial velocity, U 14 meters S1, and 2 time taken, t 1.43 seconds. Questions 1. What do you mean by free fall? 2. What do you mean by acceleration due to gravity? Q. Gravitation 137, 10.3 Mass. We have learned in the previous chapter that the mass of an object is the measure of its inertia. Section 9.3. We have also learned that greater the mass, the greater is the inertia. It remains the same whether the object is on the Earth, the Moon or even in outer space. Thus, the mass of an object is constant and does not change from place to place. 10.4 Weight. We know that the Earth attracts every object with a certain force, and this force depends on the mass m of the object and the acceleration due to the gravity g. The weight of an object is the force with which it is attracted towards the Earth. We know that Fm times a, 10.13 that is, Fm times g. 10.14 The force of attraction of the Earth on an object is known as the weight of the object. It is denoted by W substituting the same in E. 10.14. We have Wm times g. 10.15 as the weight of an object is the force with which it is attracted towards the Earth. The C unit of weight is the same as that of force, that is, Newton N. The weight is a force acting vertically downwards. It has both magnitude and direction. We have learned that the value of g is constant at a given place. Therefore, at a given place, the weight of an object is directly proportional to the mass, say m, of the object, that is, Wm. It is due to this reason that at a given place, we can use the weight of an object as a measure of its mass. The mass of an object remains the same everywhere, that is, on the Earth and on any planet, whereas its weight depends on its location, because g depends on location. 10.4.1 Weight of an object on the Moon. We have learned that the weight of an object on the Earth is the force with which the Earth attracts the object. In the same way, the weight of an object on the Moon is the force with which the Moon attracts that object. The mass of the Moon is less than that of the Earth. Due to this, the Moon exerts lesser force of attraction on objects. Let the mass of an object be m. Let its weight on the Moon be William. Let the mass of the Moon be mm and its radius be rm. By applying the universal law of gravitation, the weight of the object on the Moon will be 2g times mmmmmmwr 10.16. Let the weight of the same object on the Earth be v. The mass of the Earth is m and its radius is r. Table 10.1 Celestial mass kilograms. Radius m. Body Earth 5.98 times 1024 6.37 times 106 Moon 7.36 times 1022 1.74 times 106 From x 10.9 and 10.15 we have 2g times EMMWR 10.17. Substituting the values from table 10.1 in x 10.16 and 10.17, we get 22, 2, 6, 7.36, 10 kilograms g 1.74 10 meters times mmW 102.431 10 g times MWM 10.18 a and 111.474 10 g times UM 10.18 b. Dividing eq 10.18 a by eq 10.18 b. We get 10, 11, 2.431, 10, 1.474 10 times MEWW or 1, 0.1656 meters EWW 10.19 Weight of the object on the Moon 1 Weight of the object on the Earth 6 Weight of the object on the Moon 1, 6 times its weight on the Earth. SCIENCE 138 Example 10.4 Mass of an object is 10 kilograms. What is its weight on the Earth? Solution. Mass m 10 kilograms. Acceleration due to gravity, g 9.8 meters s2 times gw 10 kilograms times 9.8 meters s2 98 n. Thus, the weight of the object is 98 n. Example 10.5 An object weighs 10 n when measured on the surface of the Earth. What would be its weight when measured on the surface of the Moon? Solution. We know, weight of object on the Moon 1, 6 times its weight on the Earth. That is, 10.66 EMWW and 1.67 n. Thus, the weight of object on the surface of the Moon would be 1.67 n. Questions 1. What are the differences between the mass of an object and its weight? 2. Why is the weight of an object on the Moon 1, 60h its weight on the Earth 10.5 Thrust and pressure. Have you ever wondered why a camel can run in a desert easily? Why an army tank weighing more than 1,000 tons rests upon a continuous chain? Why a truck or a motor bus has much wider tires? Why cutting tools have sharp edges? In order to address these questions and understand the phenomena involved, it helps to introduce the concepts of the net force and a particular direction thrust and the force per unit area pressure acting on the object concerned. Let us try to understand the meanings of thrust and pressure by considering the following situations. Situation 1. You wish to fix a poster on a bulletin board, as shown in Fig 10.3. To do this task you will have to press drawing pins with your thumb. You apply a force on the surface area of the head of the pin. This force is directed perpendicular to the surface area of the board. This force acts on a smaller area at the tip of the pin. Q Figure 10.3. To fix a poster, drawing pins are pressed with the thumb perpendicular to the board. Situation 2. You stand on loose sand. Your feet go deep into the sand. Now, lie down on the sand. You will find that your body will not go that deep in the sand. In both cases the force exerted on the sand is the weight of your body. Gravitation 139 You have learned that weight is a force acting vertically downwards. Here the force is acting perpendicular to the surface of the sand. The force acting on an object perpendicular to the surface is called thrust. When you stand on loose sand, the force, that is, the weight of your body is acting on an area equal to area of your feet. When you lie down, the same force acts on an area equal to the contact area of your whole body, which is larger than the area of your feet. Thus, the effects of forces of the same magnitude on different areas are different. In the above cases, thrust is the same, but effects are different. Therefore, the effect of thrust depends on the area on which it acts. The effect of thrust on sand is larger while standing than while lying. The thrust on unit area is called pressure. Thus, thrust pressure area 10.20 substituting the C unit of thrust and area in Eq. 10.20, we get the C unit of pressure as N square meters or N square meters. In honor of scientist Blaise Pascal, the C unit of pressure is called Pascal, denoted as Pennsylvania. Let us consider a numerical example to understand the effects of thrust acting on different areas. Example 10.6 A block of wood is kept on a tabletop. The mass of wooden block is 5 kilograms and its dimensions are 40 centimeters times 20 centimeters times 10 centimeters. Find the pressure exerted by the wooden block on the tabletop if it is made to lie on the tabletop with its size of dimensions A 20 centimeters times 10 centimeters and B 40 centimeters times 20 centimeters. Solution: the mass of the wooden block 5 kilograms, the dimensions 40 centimeters times 20 centimeters times 10 centimeters. Here, the weight of the wooden block applies a thrust on the tabletop. That is, thrust Fm times G 5 kilograms times 9.8 meters S 249 N area of a side length times breadth 20 centimeters times 10 centimeters 200 centimeters 0.02 meters 2 from Eq. 10.20, pressure 249 N 0.02 meters 2450 nm2. When the block lies on its side of dimensions 40 centimeters times 20 centimeters, it exerts the same thrust. Area length times breadth 40 centimeters times 20 centimeters 800 centimeters 0.08 meters 2 from Eq. 10.20, pressure 249 N 0.08 meters 612.5 N square meters. The pressure exerted by the side 20 centimeters times 10 centimeters is 2450 N square meters and by the side 40 centimeters times 20 centimeters is 612.5 N square meters. Thus, the same force acting on a smaller area exerts a larger pressure, and a smaller pressure on a larger area. This is the reason why a nail has a pointed tip, knives have sharp edges and buildings have wide foundations. 10.5.1 Pressure in fluids. All liquids and gases are fluids. A solid exerts pressure on a surface due to its weight. Similarly, fluids have weight, and they alsifig. 10.4 SCIENCE 140 water on a bottle is greater than its weight. Therefore it rises up when released. To keep the bottle completely immersed, the upward force on the bottle due to water must be balanced. This can be achieved by an externally applied force acting downwards. This force must at least be equal to the difference between the upward force and the weight of the bottle. The upward force exerted by the water on the bottle is known as upthrust or buoyant force. In fact, all objects experience a force of buoyancy when they are immersed in a fluid. The magnitude of this buoyant force depends on the density of the fluid. 10.5.3 Why objects float or sink when placed on the surface of water. Let us do the following activities to arrive at an answer for the above question. Activity 10.5 Middle. Take a beaker filled with water. Middle. Take an iron nail and place it on the surface of the water. Middle. Observe what happens. The nail sinks. The force due to the gravitational attraction of the earth on the iron nail pulls it downwards. There is an upthrust of water on the nail, which pushes it upwards. but the downward force acting on the nail is greater than the upthrust of water on the nail. So it sinks. Figure 10.5. Exert pressure on the base and walls of the container in which they are enclosed. Pressure exerted in any confined mass of fluid is transmitted undiminished in all directions. 10.5.2 Buoyancy. Have you ever had a swim in a pool and felt lighter? Have you ever drawn water from a well and felt that the bucket of water is heavier when it is out of the water? Have you ever wondered why a ship made of iron and steel does not sink in seawater, but while the same amount of iron and steel in the form of a sheet would sink? These questions can be answered by taking buoyancy in consideration. Let us understand the meaning of buoyancy by doing an activity. Activity 10.4 Middle. Take an empty plastic bottle. Close the mouth of the bottle with an airtight stopper. Put it in a bucket filled with water. You see that the bottle floats. Middle. Push the bottle into the water. You feel an upward push. Try to push it further down. You will find it difficult to push deeper and deeper. This indicates that water exerts a force on the bottle in the upward direction. The upward force exerted by the water goes on increasing as the bottle is pushed deeper till it is completely immersed. Middle. Now, release the bottle. It bounces back to the surface. Middle. Does the force due to the gravitational attraction of the Earth act on this bottle? If so, why doesn't the bottle stay immersed in water after it is released? How can you immerse the bottle in water? The force due to the gravitational attraction of the Earth acts on the bottle in the downward direction. So the bottle is pulled downwards. But the water exerts an upward force on the bottle. Thus, the bottle is pushed upwards. We have learned that weight of an object is the force due to gravitational attraction of the Earth. When the bottle is immersed, the upward force exerted by the figure 10.5, an iron nail sinks and a cork floats when placed on the surface of water. Gravitation 141 Middle. Observe what happens to elongation of the string or the reading on the balance. You will find that the elongation of the string or the reading of the balance decreases as the stone is gradually lowered in the water. However, no further change is observed once the stone gets fully immersed in the water. What do you infer from the decrease in the extension of the string or the reading of the spring balance? We know that the elongation produced in the string or the spring balance is due to the weight of the stone. Since the extension decreases once the stone is lowered in water, it means that some force acts on the stone in upward direction. As a result, the net force on the string decreases and hence the elongation also decreases. As discussed earlier, this upward force exerted by water is known as the force of buoyancy. What is the magnitude of the buoyant force experienced by a body? Is it the same in all fluids for a given body? Do all bodies in a given fluid experience the same buoyant force? The answer to these questions is activity 10.6 Middle. Take a beaker filled with water. Middle. Take a piece of cork and an iron nail of equal mass. Middle. Place them on the surface of water. Middle. Observe what happens. The cork floats while the nail sinks. This happens because of the difference in their densities. The density of a substance is defined as the mass per unit volume. The density of cork is less than the density of water. This means that the upthrust of water on the cork is greater than the weight of the cork. So it floats. Figure 10.5. The density of an iron nail is more than the density of water. This means that the upthrust of water on the iron nail is less than the weight of the nail. So it sinks. Therefore objects of density less than that of a liquid float on the liquid. The objects of density greater than that of a liquid sink in the liquid. Questions 1. Why is it difficult to hold a school bag having a strap made of a thin and strong string? 2. What do you mean by buoyancy? 3. Why does an object float or sink when placed on the surface of water? 10.6 Archimedes Principle. Activity 10.7 Middle. Take a piece of stone and tie it to an end of a rubber string or a spring balance. Middle dot suspend the stone by holding the balance or the string as shown in figure 10.6a. Middle dot note the elongation of the string or the reading on the spring balance due to the weight of the stone. Middle dot now, slowly dip the stone in the water in a container as shown in figure 10.6b. Figure 10.6, observe the elongation of the rubber string due to the weight of a piece of stone suspended from it in air. B. The elongation decreases as the stone is immersed in water. A BQ. Contained in Archimedes principle, stated as follows: when a body is immersed fully or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. Now, can you explain why a further decrease in the elongation of the string was not observed in activity 10.7, as the stone was fully immersed in water? Archimedes was a Greek scientist. He discovered the principle, subsequently named after him, after noticing that the water in a bathtub overflowed when he stepped into it. He ran through the streets shouting "Eureka!" which means "I have got it." This knowledge helped him to determine the purity of the gold in the crown made for the king. His work in the field of geometry and mechanics made him famous. His understanding of levers, pulleys, wheels and axle helped the Greek army in its war with Roman army. Archimedes principle has many applications. It is used in designing ships and submarines. Lactometers, which are used to determine the purity of a sample of milk, and hydrometers used for determining density of liquids, are based on this principle. Questions 1. You find your mass to be 42 kilograms on a weighing machine. Is your mass more or less than 42 kilograms 2? You have a bag of cotton and an iron bar, each indicating a mass of 100 kilograms when measured on a weighing machine. In reality, one is heavier than other. Can you say which one is heavier and why? 10.7 Relative density. As you know, the density of a substance is defined as mass of a unit volume. The unit of density is kilogram per meter cube, kilograms m3. The density of a given substance, under specified conditions, remains the same. Therefore, the density of a substance is one of its characteristic properties. It is different for different substances. For example, the density of gold is 19,300 kilograms m3 while that of water is 1,000 kilograms m3. The density of a given sample of a substance can help us to determine its purity. It is often convenient to express density of a substance in comparison with that of water. The relative density of a substance is the ratio of its density to that of water. Density of a substance relative a density of water. Since the relative density is the ratio of similar quantities, it has no unit. Example 10.7 Relative density of silver is 10.8. The density of water is 103 kilograms m3. What is the density of silver in C unit? Solution: relative density of silver 10.8. Relative density of silver, density of water, density of silver, relative density of silver times density of water, 10.8 times 103 kilograms m3. Archimedes Q. Gravitation 143. What you have learned. Middle dot. The law of gravitation states that the force of attraction between any two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. The law applies to objects anywhere in the universe. Such a law is said to be universal. Middle dot. Gravitation is a weak force unless large masses are involved. Middle dot. The force of gravity decreases with altitude. It also varies on the surface of the Earth, decreasing from poles to the equator. Middle dot. The weight of a body is the force with which the Earth attracts it. Middle dot. The weight is equal to the product of mass and acceleration due to gravity. Middle dot. The weight may vary from place to place but the mass stays constant. Middle dot. All objects experience a force of buoyancy when they are immersed in a fluid. Middle dot. Objects having density less than that of the liquid in which they are immersed float on the surface of the liquid. If the density of the object is more than the density of the liquid in which it is immersed, then it sinks in the liquid. Exercises 1. How does the force of gravitation between two objects change when the distance between them is reduced to half 2? Gravitational force acts on all objects in proportion to their masses. Why then, a heavy object does not fall faster than a light object? 3. What is the magnitude of the gravitational force between the Earth and a 1 kilogram object on its surface? Mass of the Earth is 6 times 1024 kilograms and radius of the Earth is 6.4 times 106 meters. 4. The Earth and the Moon are attracted to each other by gravitational force. Does the Earth attract the Moon with a force that is greater or smaller or the same as the force with which the Moon attracts the Earth? Why? 5. If the Moon attracts the Earth, why does the Earth not move towards the Moon? 6. What happens to the force between two objects, if the mass of one object is doubled? 2. The distance between the objects is doubled and tripled. 3. The masses of both objects are doubled. 7. What is the importance of universal law of gravitation? 8. What is the acceleration of free fall? 9. What do we call the gravitational force between the Earth and an object? 10. Amit buys few grams of gold at the poles as per the instruction of one of his friends. He hands over the same when he meets him at the equator. Will the friend agree with the weight of gold bought? If not, why? And the value of G is greater at the poles than at the equator. 11. Why will a sheet of paper fall slower than one that is crumpled into a ball? 12. Gravitational force on the surface of the Moon is only 1/6 as strong as gravitational force on the Earth. What is the weight in newtons of a 10 kilograms object on the Moon and on the Earth? 13. A ball is thrown vertically upwards with a velocity of 49 meters s. Calculate the maximum height to which it rises, to the total time it takes to return to the surface of the Earth. 14. A stone is released from the top of a tower of height 19.6 meters. Calculate its final velocity just before touching the ground. 15. A stone is thrown vertically upward with an initial velocity of 40 meters s. Taking g 10 meters s2, find the maximum height reached by the stone. What is the net displacement and the total distance covered by the stone? 16. Calculate the force of gravitation between the Earth and the Sun, given that the mass of the Earth 6 times 1024 kilograms and of the Sun 2 times 1030 kilograms. The average distance between the two is 1.5 times 1011 meters. 17. A stone is allowed to fall from the top of a tower 100 meters high, and at the same time another stone is projected vertically upwards from the ground with a velocity of 25 meters s. Calculate when and where the two stones will meet. 18. A ball thrown up vertically returns to the thrower after 6 seconds. Find the velocity with which it was thrown up, b the maximum height it reaches, and c its position after 4 seconds. Gravitation 145. 19. In what direction does the buoyant force on an object immersed in a liquid act? 20. Why does a block of plastic released under water come up to the surface of water? 21. The volume of 50 grams of a substance is 20 centimeters. 3. If the density of water is 1 gram centimeters 3, will the substance float or sink? 22. The volume of a 500 grams sealed packet is 350 centimeters 3. Will the packet float or sink in water? If the density of water is 1 gram centimeters 3, what will be the mass of the water displaced by this packet? In the previous few chapters we have talked about ways of describing the motion of objects, the cause of motion and gravitation. Another concept that helps us understand and interpret many natural phenomena is work. Closely related to work are energy and power. In this chapter we shall study these concepts. All living beings need food. Living beings have to perform several basic activities to survive. We call such activities life processes. The energy for these processes comes from food. We need energy for other activities like playing, singing, reading, writing, thinking, jumping, cycling and running. Activities that are strenuous require more energy. Animals too get engaged in activities. For example, they may jump and run. They have to fight, move away from enemies, find food or find a safe place to live. Also, we engage some animals to lift weights, carry loads, pull carts or plow fields. All such activities require energy. Think of machines. List the machines that you have come across. What do they need for their working? Why do some engines require fuel like petrol and diesel? Why do living beings and machines need energy? 11.1 Work. What is work? There is a difference in the way we use the term work in day-to-day life and the way we use it in science. To make this point clear, let us consider a few examples. 1.1.1. Not much work in spite of working hard. Kamali is preparing for examinations. She spends a lot of time in studies. She reads books, draws diagrams, organizes her thoughts, collects question papers, attends classes, discusses problems with her friends, and performs experiments. She expends a lot of energy on these activities. In common parlance, she is working hard. All this hard work may involve very little work if we go by the scientific definition of work. You are working hard to push a huge rock. Let us say the rock does not move despite all the effort. You get completely exhausted. However, you have not done any work on the rock as there is no displacement of the rock. You stand still for a few minutes with a heavy load on your head. You get tired. You have exerted yourself and have spent quite a bit of your energy. Are you doing work on the load the way we understand the term work in science? Work is not done. You climb up the steps of a staircase and reach the second floor of a building just to see the landscape from there. You may even climb up a tall tree. If we apply the scientific definition, these activities involve a lot of work. In day-to-day life, we consider any useful physical or mental labor as work. Activities like playing in a field, talking with friends, humming a tune, watching a movie, attending a function are sometimes not considered to be work. What constitutes work depends on the way we define it. We use and define the term work differently in science. To understand this, let us do the following activities. Activity 11.1 We have discussed in the above paragraphs a number of activities which we normally consider to be work. 11 work and energy chapter. Activity 11.3 Think of situations when the object is not displaced in spite of a force acting on it. Also think of situations when an object gets displaced in the absence of a force acting on it. List all the situations that you can think of for each. Discuss with your friends whether work is done in these situations. 1.1.3 Work done by a constant force. How is work defined in science? To understand this, we shall first consider the case when the force is acting in the direction of displacement. Let a constant force, F, act on an object. Let the object be displaced through a distance, S, in the direction of the force figure. 11.1 Let W be the work done. We define work to be equal to the product of the force and displacement. Work done force times displacement WFS. 11.1 In day-to-day life. For each of these activities, ask the following questions and answer them. I. What is the work being done on? 2. What is happening to the object? 3. Who. What is doing the work? 1.1.2 Scientific conception of work. To understand the way we view work and define work from the point of view of science, let us consider some situations. Push a pebble lying on a surface. The pebble moves through a distance. You exerted a force on the pebble and the pebble got displaced. In this situation, work is done. A girl pulls a trolley and the trolley moves through a distance. The girl has exerted a force on the trolley and it is displaced. Therefore, work is done. Lift a book through a height. To do this you must apply a force. The book rises up. There is a force applied on the book and the book has moved. Hence, work is done. A closer look at the above situations reveals that two conditions need to be satisfied for work to be done. A force should act on an object, and 2. The object must be displaced. If any one of the above conditions does not exist, work is not done. This is the way we view work in science. A bullock is pulling a cart. The cart moves. There is a force on the cart and the cart has moved. Do you think that work is done in this situation? Activity 11.2 Middle. Think of some situations from your daily life involving work. Middle. List them. Middle. Discuss with your friends whether work is being done in each situation. Middle. Try to reason out your response. Middle. If work is done, which is the force acting on the object? Middle. What is the object on which the work is done? Middle. What happens to the object on which work is done? Figure 11.1. Thus, work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Work has only magnitude and no direction. In E. 11.1, if F1 n and S1 meter, then the work done by the force will be 1 nm. Here the unit of work is Newton meter nm or joule J. Thus 1 J is the amount of work and energy 147. NCERT 148 done on an object when a force of 1 n displaces it by 1 meter along the line of action of the force. Look at E. 11.1 carefully. What is the work done when the force on the object is 0? What would be the work done when the displacement of the object is 0? Refer to the conditions that are to be satisfied to say that work is done. Example 11.1 A force of 5 n is acting on an object. The object is displaced through 2 meters in the direction of the force. Figure 11.2. If the force acts on the object all through the displacement, then work done is 5n times 2 meters, 10 nm or 10 J. Figure 11.4 Consider a situation in which an object is moving with a uniform velocity along a particular direction. Now a retarding force F is applied in the opposite direction. That is, the angle between the two directions is 180 superscript O. Let the object stop after a displacement S. In such a situation, the work done by the force, F is taken as negative and denoted by the minus sign. The work done by the force is F times S or F times S. It is clear from the above discussion that the work done by a force can be either positive or negative. To understand this, let us do the following activity. Activity 11.4 Middle. Lift an object up. Work is done by the force exerted by you on the object. The object moves upwards. The force you exerted is in the direction of displacement. However, there is the force of gravity acting on the object. Middle. Which one of these forces is doing positive work? Middle. Which one is doing negative work? Middle. Give reasons. Work done is negative when the force acts opposite to the direction of displacement. Work done is positive when the force is in the direction of displacement. Example 11.2 A porter lifts a luggage of 15 kilograms from the ground and puts it on his head 1.5 meters above the ground. Calculate the work done by him on the luggage. Solution: mass of luggage, m 15 kilograms and displacement, s 1.5 meters. Figure 11.2 Question 1. A force of 7n acts on an object. The displacement is, say 8 meters, in the direction of the force. Figure 11.3. Let us take it that the force acts on the object through the displacement. What is the work done in this case? Figure 11.3 Consider another situation in which the force and the displacement are in the same direction, a baby pulling a toy car parallel to the ground, as shown in figure. 11.4 The baby has exerted a force in the direction of displacement of the car. In this situation, the work done will be equal to the product of the force and displacement. In such situations, the work done by the force is taken as positive. Q. Work and energy. 149 Raised hammer falls on a nail placed on a piece of wood, it drives the nail into the wood. We have also observed children winding a toy such as a toy car, and when the toy is placed on the floor, it starts moving. When a balloon is filled with air and we press it, we notice a change in its shape. As long as we press it gently, it can come back to its original shape when the force is withdrawn. However, if we press the balloon hard, it can even explode, producing a blasting sound. In all these examples, the objects acquire, through different means, the capability of doing work. An object having a capability to do work is said to possess energy. The object which does the work loses energy, and the object on which the work is done gains energy. How does an object with energy do work? An object that possesses energy can exert a force on another object. When this happens, energy is transferred from the former to the latter. The second object may move as it receives energy and therefore do some work. Thus, the first object had a capacity to do work. This implies that any object that possesses energy can do work. The energy possessed by an object is thus measured in terms of its capacity of doing work. The unit of energy is, therefore, the same as that of work, that is, joule J. 1 J is the energy required to do 1 joule of work. Sometimes a larger unit of energy called kilojoule is used. 1 kilojoule equals 1000 J. 1.2.1 Forms of energy. Luckily, the world we live in provides energy in many different forms. The various forms include mechanical energy, potential energy, kinetic energy, heat energy, chemical energy, electrical energy, and light energy. Think it over. How do you know that some entity is a form of energy? Discuss with your friends and teachers. Work done, WF times S milligrams times S 15 kilograms times 10 meters S 2 times 1.5 meters 225 kilograms MS 2 meters 225 Nm 225 J. Work done is 225 J. West 1. When do we say that work is done? 2. Write an expression for the work done when a force is acting on an object in the direction of its displacement. 3. Define 1 J of work. 4. A pair of bullocks exerts a force of 140 N on a plow. The field being plowed is 15 meters long. How much work is done in plowing the length of the field? 11.2 Energy. Life is impossible without energy. The demand for energy is ever increasing. Where do we get energy from? The sun is the biggest natural source of energy to us. Many of our energy sources are derived from the sun. We can also get energy from the nuclei of atoms, the interior of the earth, and the tides. Can you think of other sources of energy? Activity 11.5 Middle dot. A few sources of energy are listed above. There are many other sources of energy. List them. Middle dot. Discuss in small groups how certain sources of energy are due to the sun. Middle dot. Are there sources of energy which are not due to the sun? The word energy is very often used in our daily life, but in science we give it a definite and precise meaning. Let us consider the following examples. When a fast-moving cricket ball hits a stationary wicket, the wicket is thrown away. Similarly, an object when raised to a certain height gets the capability to do work. You must have seen that when a Q SCIENCE 150 figure 11.5 middle dot. The trolley moves forward and hits the wooden block. Middle dot. Fix a stop on the table in such a manner that the trolley stops after hitting the block. The block gets displaced. Middle dot. Note down the displacement of the block. This means work is done on the block by the trolley as the block has gained energy. Middle dot. From where does this energy come? Middle dot. Repeat this activity by increasing the mass on the pan. In which case is the displacement more? Middle dot. In which case is the work done more? Middle dot. In this activity, the moving trolley does work and hence it possesses energy. A moving object can do work. An object moving faster can do more work than an identical object moving relatively slow. A moving bullet, blowing wind, a rotating wheel, a speeding stone can do work. How does a bullet pierce the target? How does the wind move the blades of a windmill? Objects in motion possess energy. We call this energy kinetic energy. A falling coconut, a speeding car, a rolling stone, a flying aircraft, flowing water, blowing wind, a running athlete, etc. possess kinetic energy. In short, kinetic energy is the energy possessed by an object due to its motion. The kinetic energy of an object increases with its speed. How much energy is possessed by a moving body by virtue of its motion? By definition, we say that the kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity. 1.1.2.2 Kinetic energy activity 11.6 Middle dot. Take a heavy ball. Drop it on a thick bed of sand. A wet bed of sand would be better. Drop the ball on a sand bed from height of about 25 centimeters. The ball creates a depression. Middle dot. Repeat this activity from heights of 50 centimeters, 1 meter and 1.5 meters. Middle dot. Ensure that all the depressions are distinctly visible. Middle dot. Mark the depressions to indicate the height from which the ball was dropped. Middle dot. Compare their depths. Middle dot. Which one of them is deepest? Middle dot. Which one is shallowest? Why? Middle dot. What has caused the ball to make a deeper dent? Middle dot. Discuss and analyze. Activity 11.7 Middle dot. Set up the apparatus as shown in figure 11.5. Middle dot. Place a wooden block of known mass in front of the trolley at a convenient fixed distance. Middle dot. Place a known mass on the pan so that the trolley starts moving. James Prescott Joule was an outstanding British physicist. He is best known for his research in electricity and thermodynamics. Amongst other things, he formulated a law for the heating effect of electric current. He also verified experimentally the law of conservation of energy and discovered the value of the mechanical equivalent of heat. The unit of energy and work called joule is named after him. James Prescott Joule 1889. Work and energy 151. Let us now express the kinetic energy of an object in the form of an equation. Consider an object of mass, m moving with a uniform velocity, u. Let it now be displaced through a distance s when a constant force, F acts on it in the direction of its displacement. From Eq. 11.1, the work done, W is Fs. The work done on the object will cause a change in its velocity. Let its velocity change from u to v. Let a be the acceleration produced. In section 8.5, we studied three equations of motion. The relation connecting the initial velocity u and final velocity v of an object moving with a uniform acceleration a, and the displacement, s is v2u2, 2as 8.7. This gives 22vus 2a 11.2 from section 9.4, we know fma. Thus, using Eq. 11.2 and Eq. 11.1, we can write the work done by the force, F is times 22VUWM at 2A or 1222WMVU 11.3 if the object is starting from its stationary position. That is, U0, then 122WMV 11.4. It is clear that the work done is equal to the change in the kinetic energy of an object. If U0, the work done will be 2 meters v. Thus, the kinetic energy possessed by an object of mass m and moving with a uniform velocity, v is 122 km v 11.5 Example 11.3 An object of mass 15 kilograms is moving with a uniform velocity of 4 meters s1. What is the kinetic energy possessed by the object? Solution: mass of the object, m 15 kilograms, velocity of the object, v 4 meters s1. From Eq. 11.5, 122 km v1, 2 times 15 kilograms times 4 meters s1 times 4 meters s1, 120 J. The kinetic energy of the object is 120 J. Example 11.4 What is the work to be done to increase the velocity of a car from 30 km h1 to 60 km h1 if the mass of the car is 1500 kg? Solution: mass of the car, m 1500 kg, initial velocity of car, u 30 km h1, 30 times 1000 meters, 60 times 60 is 25, 3 meters s1. Similarly, the final velocity of the car, v 60 km h1 50, 3 meters s1. Therefore, the initial kinetic energy of the car, EQ12, 2 mu1, 2 times 1500 kilograms times 25, 3 meters s1, 2, 156,250, 3 J. The final kinetic energy of the car, EQ1, 2 times 1500 kilograms times 50, 3 meters s1, 2, 625,000, 3 J. Thus, the work done change in kinetic energy EQ 156,250 J. NCERT 152 Questions 1. What is the kinetic energy of an object? 2. Write an expression for the kinetic energy of an object. 3. The kinetic energy of an object of mass, m moving with a velocity of 5 meters s1 is 25 J. What will be its kinetic energy when its velocity is doubled? What will be its kinetic energy when its velocity is increased 3 times 1.2.3 Potential energy activity 11.8 Middle. Take a rubber band. Middle. Hold it at one end and pull from the other. The band stretches. Middle. Release the band at one of the ends. Middle. What happens? Middle. The band will tend to regain its original length. Obviously the band had acquired energy in its stretched position. Middle. How did it acquire energy when stretched? Activity 11.9 Middle. Take a slinky as shown below. Middle. Ask a friend to hold one of its ends. You hold the other end and move away from your friend. Now you release the slinky. Activity 11.11 Middle. Lift an object through a certain height. The object can now do work. It begins to fall when released. Middle. This implies that it has acquired some energy. If raised to a greater height it can do more work and hence possesses more energy. Middle. From where did it get the energy? Think and discuss. In the above situations, the energy gets stored due to the work done on the object. The energy transferred to an object is stored as potential energy if it is not used to cause a change in the velocity or speed of the object. You transfer energy when you stretch a rubber band. The energy transferred to the band is its potential energy. You do work while winding the key of a toy car. The energy transferred to the spring inside is stored as potential energy. The potential energy possessed by the object is the energy present in it by virtue of its position or configuration. Activity 11.12 Middle. Take a bamboo stick and make a bow as shown in figure 11.6. Middle. Place an arrow made of a light stick on it with one end supported by the stretched string. Middle. Now stretch the string and release the arrow. Middle. Notice the arrow flying off the bow. Notice the change in the shape of the bow. Middle. The potential energy stored in the bow due to the change of shape is thus used in the form of kinetic energy in throwing off the arrow. QFIG.11.6, an arrow and the stretched string on the bow. Middle. What happened? Middle. How did the slinky acquire energy when stretched? Middle. Would the slinky acquire energy when it is compressed? Activity 11.10 Middle. Take a toy car. Wind it using its key. Middle dot, place the car on the ground. Middle dot, did it move? Middle dot, from where did it acquire energy? Middle dot, does the energy acquired depend on the number of windings? Middle dot, how can you test this? Work and energy 153. When 1.2.4 potential energy of an object at a height, an object increases its energy when raised through a height. This is because work is done on it against gravity while it is being raised. The energy present in such an object is the gravitational potential energy. The gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground to that point against gravity. It is easy to arrive at an expression for the gravitational potential energy of an object at a height. Figure 11.7. Consider an object of mass, m. Let it be raised through a height, h, from the ground. A force is required to do this. The minimum force required to raise the object is equal to the weight of the object, milligrams. The object gains energy equal to the work done on it. Let the work done on the object against gravity be W, that is, work done, W force times displacement milligrams times h mgh. Since work done on the object is equal to mgh, an energy equal to mgh units is gained by the object. This is the potential energy EP of the object. EP mgh 11.7. More to know the potential energy of an object at a height depends on the ground level or the zero level you choose. An object in a given position can have a certain potential energy with respect to one level and a different value of potential energy with respect to another level. It is useful to note that the work done by gravity depends on the difference in vertical heights of the initial and final positions of the object and not on the path along which the object is moved. Figure 11.8 shows a case where a block is raised from position A to B by taking two different paths. Let the height A be h. In both the situations the work done on the object is mgh. Figure 11.8. Example 11.5. Find the energy possessed by an object of mass 10 kilograms when it is at a height of 6 meters above the ground. Given, g 9.8 meters s2. Solution, mass of the object, m 10 kilograms, displacement height, h 6 meters, and acceleration due to gravity, g 9.8 meters s2. From Eq. 11.6, potential energy mgh 10 kilograms times 9.8 meters s2 times 6 meters, 588 J. The potential energy is 588 J. SCIENCE 154. Example 11.6. An object of mass 12 kilograms is at a certain height above the ground. If the potential energy of the object is 480 J, find the height at which the object is with respect to the ground. Given, g 10 meters s2. Solution, mass of the object, m 12 kilograms, potential energy, EP 480 J. EP mgh 480 J 12 kilograms times 10 meters s2 times h 2480 J 120 kilograms ms 4 meters. The object is at the height of 4 meters when 1.2.5 are various energy forms interconvertible. Can we convert energy from one form to another? We find in nature a number of instances of conversion of energy from one form to another. Activity 11.13. Middle dot, sit in small groups. Middle dot, discuss the various ways of energy conversion in nature. Middle dot, discuss following questions in your group. A. How do green plants produce food? B. Where do they get their energy from? C. Why does the air move from place to place? D. How are fuels such as coal and petroleum formed? D. What kinds of energy conversions sustain the water cycle? Activity 11.14. Middle dot, many of the human activities and the gadgets we use involve conversion of energy from one form to another. Middle dot, make a list of such activities and gadgets. Middle dot, identify in each activity gadget the kind of energy conversion that takes place. 1.2.6 Law of Conservation of Energy in Activities 11.13 and 11.14, we learned that the form of energy can be changed from one form to another. What happens to the total energy of a system during or after the process? Whenever energy gets transformed, the total energy remains unchanged. This is the law of conservation of energy. According to this law, energy can only be converted from one form to another. It can neither be created or destroyed. The total energy before and after the transformation remains the same. The law of conservation of energy is valid in all situations and for all kinds of transformations. Consider a simple example. Let an object of mass, m be made to fall freely from a height, h. At the start, the potential energy is mgh and kinetic energy is 0. Why is the kinetic energy 0? It is 0 because its velocity is 0. The total energy of the object is thus mgh. As it falls, its potential energy will change into kinetic energy. If v is the velocity of the object at a given instant, the kinetic energy would be 1/2 mv2. As the fall of the object continues, the potential energy would decrease while the kinetic energy would increase. When the object is about to reach the ground, h0 and v will be the highest. Therefore, the kinetic energy would be the largest and potential energy the least. However, the sum of the potential energy and kinetic energy of the object would be the same at all points. That is, potential energy kinetic energy constant or one constant. 2 mgh mv 11.7 The sum of kinetic energy and potential energy of an object is its total mechanical energy. We find that during the free fall of the object, the decrease in potential energy, at any point in its path, appears as an equal amount of increase in kinetic energy. Here the effect of air resistance on the motion of the object has been ignored. There is thus a continual transformation of gravitational potential energy into kinetic energy. Work and energy 155 A stronger person may do certain work in relatively less time. A more powerful vehicle would complete a journey in a shorter time than a less powerful one. We talk of the power of machines like motorbikes and motorcars. The speed with which these vehicles change energy or do work is the basis for their classification. Power measures the speed of work done, that is, how fast or slow work is done. Power is defined as the rate of doing work or the rate of transfer of energy. If an agent does a work W in time t, then power is given by power work time or WPT 11.8. The unit of power is watt in honor of James Watt 1736–1819. Having the symbol W1, watt is the power of an agent which does work at the rate of 1 joule per second. We can also say that power is 1 W when the rate of consumption of energy is 1 JS1. 1 watt 1 joule second or 1 W 1 JS1. We express larger rates of energy transfer in kilowatts kW. 1 kilowatt 1000 watts 1 kW 1001 kW 1000 JS1. The power of an agent may vary with time. This means that the agent may be doing work at different rates at different intervals of time. Therefore the concept of average power is useful. We obtain average power by dividing the total energy consumed by the total time taken. Example 11.7 Two girls, each of weight 400 and climb up a rope through a height of 8 meters. We name one of the girls A and the other B. Girl A takes 20 seconds while B takes 50 seconds to accomplish this task. What is the power expended by each girl? Solution: I power expended by girl A, weight of the girl, milligrams 400 and displacement height, h 8 meters. Activity 11.15 middle dot. An object of mass 20 kilograms is dropped from a height of 4 meters. Fill in the blanks in the following table by computing the potential energy and kinetic energy in each case. Height at potential kinetic at peak. Which object energy is located at mgh mv2 to mjjj4 3 2 1 just above the ground. Middle dot. For simplifying the calculations, take the value of g as 10 meters s2. Think it over. What would have happened if nature had not allowed the transformation of energy? There is a view that life could not have been possible without transformation of energy. Do you agree with this 11.3 rate of doing work? Do all of us work at the same rate? Do machines consume or transfer energy at the same rate? Agents that transfer energy do work at different rates. Let us understand this from the following activity. Activity 11.16 middle dot. Consider two children. Say A and B. Let us say they weigh the same. Both start climbing up a rope separately. Both reach a height of 8 meters. Let us say A takes 15 seconds while B takes 20 seconds to accomplish the task. Middle dot. What is the work done by each? Middle dot. The work done is the same. However, A has taken less time than B to do the work. Middle dot. Who has done more work in a given time, say in 1 second? Questions 1. What is power? 2. Define 1 watt of power. 3. A lamp consumes 1000 J of electrical energy in 10 seconds. What is its power? 4. Define average power. 1.3.1 Commercial unit of energy. The unit joule is too small and hence is inconvenient to express large quantities of energy. We use a bigger unit of energy called kilowatt-hour kWh. What is 1 kWh? Let us say we have a machine that uses 1000 J of energy every second. If this machine is used continuously for 1 hour, it will consume 1 kWh of energy. Thus, 1 kWh is the energy used in 1 hour at the rate of 1000 Js1 or 1 kW. 1 kWh 1 kW times 1h 1000 W times 3600 seconds 3,600,000 J 1 kWh 3.6 times 106 J. The energy used in households, industries and commercial establishments are usually expressed in kilowatt-hour. For example, electrical energy used during a month is expressed in terms of units. Here, 1 unit means 1 kilowatt-hour. Example 11.9 An electric bulb of 60 W is used for 6H per day. Calculate the units of energy consumed in 1 day by the bulb. Solution: power of electric bulb 60 W 0.06 kW. Time used: T6H energy power times time taken 0.06 kW times 6H 0.36 kWh 0.36 units. The energy consumed by the bulb is 0.36 units. Time taken, T 20 seconds for meek. 11.8, power, P work done time taken mght 400 N times 8 meters 20s 160 W2 power expended by girl B, weight of the girl. Milligrams 400 N displacement height, H 8 meters time taken, T 50 seconds power, P mght 400 N times 8 meters 50s 64 W. Power expended by girl A is 160 W. Power expended by girl B is 64 W. Example 11.8 A boy of mass 50 kilograms runs up a staircase of 45 steps in 9 seconds. If the height of each step is 15 centimeters, find his power. Take G 10 meters S2. Solution: weight of the boy, milligrams 50 kilograms times 10 meters S2 500 N height of the staircase, H 45 times 15,100 meters 6.75 meters time taken to climb, T 9 seconds for meek. 11.8, power, P work done time taken mght 500 N times 6.75 meters 9 seconds 375 W. Power is 375 W. Q. Work and energy 157 Activity 11.17 Middle dot. Take a close look at the electric meter installed in your house. Observe its features closely. Middle dot. Take the readings of the meter each day at 6:30 a.m. and 6:30 p.m. Middle dot. Do this activity for about a week. Middle dot how many units are consumed during daytime. Middle dot how many units are used during night. Middle dot tabulate your observations. Middle dot draw inferences from the data. Middle dot compare your observations with the details given in the monthly electricity bill. One can also estimate the electricity to be consumed by specific appliances by tabulating their known wattages and hours of operation. What you have learned. Middle dot work done on an object is defined as the magnitude of the force multiplied by the distance moved by the object in the direction of the applied force. The unit of work is joule. 1 joule 1 newton times 1 meter. Middle dot work done on an object by a force would be 0 if the displacement of the object is 0. Middle dot an object having capability to do work is said to possess energy. Energy has the same unit as height of work. Middle dot an object in motion possesses what is known as the kinetic energy of the object. An object of mass, m moving with velocity v has a kinetic energy of 2 mv1, 2. Middle dot the energy possessed by a body due to its change in position or shape is called the potential energy. The gravitational potential energy of an object of mass, m raised through a height, h from the Earth's surface is given by mgh. Middle dot according to the law of conservation of energy, energy can only be transformed from one form to another. It can neither be created nor destroyed. The total energy before and after the transformation always remains constant. Middle dot energy exists in nature in several forms such as kinetic energy, potential energy, heat energy, chemical energy, etc. The sum of the kinetic and potential energies of an object is called its mechanical energy. Middle dot power is defined as the rate of doing work. The C unit of power is watt. 1 W1 JS. Middle dot the energy used in 1 hour at the rate of 1 kW is called 1 kWh. Exercises 1. Look at the activities listed below. Reason out whether or not work is done in the light of your understanding of the term work. Middle dot Suma is swimming in a pond. Middle dot a donkey is carrying a load on its back. Middle dot a windmill is lifting water from a well. Middle dot a green plant is carrying out photosynthesis. Middle dot an engine is pulling a train. Middle dot food grains are getting dried in the sun. Middle dot a sailboat is moving due to wind energy. 2. An object thrown at a certain angle to the ground moves in a curved path and falls back to the ground. The initial and the final points of the path of the object lie on the same horizontal line. What is the work done by the force of gravity on the object? 3. A battery lights a bulb. Describe the energy changes involved in the process. 4. Certain force acting on a 20 kg mass changes its velocity from 5 meters s1 to 2 meters s1. Calculate the work done by the force. 5. A mass of 10 kilograms is at a point on a table. It is moved to a point B if the line joining A and B is horizontal. What is the work done on the object by the gravitational force? Explain your answer. 6. The potential energy of a freely falling object decreases progressively. Does this violate the law of conservation of energy? Why? 7. What are the various energy transformations that occur when you are riding a bicycle? 8. Does the transfer of energy take place when you push a huge rock with all your might and fail to move it, whereas the energy is spent going? 9. A certain household has consumed 250 units of energy during a month. How much energy is this in joules? 10. An object of mass 40 kilograms is raised to a height of 5 meters above the ground. What is its potential energy if the object is allowed to fall? Find its kinetic energy when it is halfway down. 11. What is the work done by the force of gravity on a satellite moving round the Earth? Justify your answer. 12. Can there be displacement of an object in the absence of any force acting on it? Think. Discuss this question with your friends and teacher. Work and energy 159.13. A person holds a bundle of hay over his head for 30 minutes and gets tired. Has he done some work or not? Justify your answer. 14. An electric heater is rated 1500 W. How much energy does it use in 10 hours? 15. Illustrate the law of conservation of energy by discussing the energy changes which occur when we draw a pendulum bob to one side and allow it to oscillate. Why does the bob eventually come to rest? What happens to its energy eventually? Is it a violation of the law of conservation of energy? 16. An object of mass, m, is moving with a constant velocity, v. How much work should be done on the object in order to bring the object to rest? 17. Calculate the work required to be done to stop a car of 1500 kilograms moving at a velocity of 60 kilometers h. 18. In each of the following F4s, F is acting on an object of mass, m. The direction of displacement is from west to east shown by the longer arrow. Observe the diagrams carefully and state whether the work done by the force is negative, positive or zero. 19. Sony says that the acceleration in an object could be zero even when several forces are acting on it. Do you agree with her? Why? 20. Find the energy in kWh consumed in 10 hours by 4 devices of power 500 W each. 21. A freely falling object eventually stops on reaching the ground. What happens to its kinetic energy? Every day we hear sounds from various sources like humans, birds, bells, machines, vehicles, televisions, radios, etc. Sound is a form of energy which produces a sensation of hearing in our ears. There are also other forms of energy like mechanical energy, light energy, etc. We have talked about mechanical energy in the previous chapters. You have been taught about conservation of energy, which states that we can neither create nor destroy energy. We can just change it from one form to another. When you clap, a sound is produced. Can you produce sound without utilizing your energy? Which form of energy did you use to produce sound? In this chapter we are going to learn how sound is produced and how it is transmitted through a medium and received by our ears. 12.1 Production of sound activity. 12.1 Middle dot. Take a tuning fork and set it vibrating by striking its prong on a rubber pad. Bring it near your ear. Middle dot. Do you hear any sound? Middle dot. Touch one of the prongs of the vibrating tuning fork with your finger and share your experience with your friends. Middle dot. Now, suspend a table tennis ball or a small plastic ball by a thread from a support. Take a big needle and a thread. Put a knot at one end of the thread, and then with the help of the needle pass the thread through the ball. Touch the ball gently with the prong of a vibrating tuning fork. Figure 12.1. Middle dot. Observe what happens and discuss with your friends. Activity 12.2 Middle dot. Fill water in a beaker or a glass up to the brim. Gently touch the water surface with one of the prongs of the vibrating tuning fork, as shown in figure 12.2. Middle dot. Next dip the prongs of the vibrating tuning fork in water, as shown in figure 12.3. Middle dot. Observe what happens in both the cases. Middle dot. Discuss with your friends why this happens. Figure 12.1, vibrating tuning fork just touching the suspended table tennis ball. Figure 12.2, one of the prongs of the vibrating tuning fork touching the water surface. 12ss Sound Don't chapter. Plucked vibrates and produces sound. If you have never done this, then do it and observe the vibration of the stretched rubber band. Activity 12.3 Middle dot. Make a list of different types of musical instruments and discuss with your friends which part of the instrument vibrates to produce sound. 12.2 Propagation of sound. Sound is produced by vibrating objects. The matter or substance through which sound is transmitted is called a medium. It can be solid, liquid or gas. Sound moves through a medium from the point of generation to the listener. When an object vibrates, it sets the particles of the medium around it vibrating. The particles do not travel all the way from the vibrating object to the ear. A particle of the medium in contact with the vibrating object is first displaced from its equilibrium position. It then exerts a force on the adjacent particle, as a result of which the adjacent particle gets displaced from its position of rest. After displacing the adjacent particle, the first particle comes back to its original position. This process continues in the medium till the sound reaches your ear. The disturbance created by a source of sound in figure 12.3, both the prongs of the vibrating tuning fork dipped in water. From the above activities, what do you conclude? Can you produce sound without a vibrating object? In the above activities we have produced sound by striking the tuning fork. We can also produce sound by plucking, scratching, rubbing, blowing or shaking different objects. As per the above activities, what do we do to the objects? We set the objects vibrating and produce sound. Vibration means a kind of rapid to and fro motion of an object. The sound of the human voice is produced due to vibrations in the vocal cords. When a bird flaps its wings, do you hear any sound? Think how the buzzing sound accompanying a bee is produced. A stretched rubber band. When figure 12.4, a beam of light from a light source is made to fall on a mirror. The reflected light is falling on the wall. Can sound make a light spot dance? Take a tin can. Remove both ends to make it a hollow cylinder. Take a balloon and stretch it over the can, then wrap a rubber band around the balloon. Take a small piece of mirror. Use a drop of glue to stick the piece of mirror to the balloon. Allow the light through a slit to fall on the mirror. After reflection, the light spot is seen on the wall, as shown in figure 12.4. Talk or shout directly into the open end of the can and observe the dancing light spot on the wall. Discuss with your friends what makes the light spot dance. Sound 161. SCIENCE 162. The medium travels through the medium and not the particles of the medium. A wave is a disturbance that moves through a medium when the particles of the medium set neighboring particles into motion. They in turn produce similar motion in others. The particles of the medium do not move forward themselves, but the disturbance is carried forward. This is what happens during propagation of sound in a medium, hence sound can be visualized as a wave. Sound waves are characterized by the motion of particles in the medium and are called mechanical waves. Air is the most common medium through which sound travels. When a vibrating object moves forward, it pushes and compresses the air in front of it, creating a region of high pressure. This region is called a compression C, as shown in figure 12.5. This compression starts to move away from the vibrating object. When the vibrating object moves backwards, it creates a region of low pressure called rarefaction R, as shown in figure 12.5. As the object moves back and forth rapidly, a series of compressions and rarefactions is created in the air. These make the sound wave that propagates through the medium. Compression is a region of high pressure and rarefaction is a region of low pressure. Pressure is related to the number of particles of a medium in a given volume. More density of the particles in the medium gives more pressure and vice versa. Thus, propagation of sound can be visualized as propagation of density variations or pressure variations in the medium. Question 1. How does a sound produced by a vibrating object in a medium reach your ear? 1.2.2.1 Sound needs a medium to travel. Sound is a mechanical wave and needs a material medium like air, water, steel, etc. for its propagation. It cannot travel through vacuum, which can be demonstrated by the following experiment. Take an electric bell and an airtight glass bell jar. The electric bell is suspended inside the airtight bell jar. The bell jar is connected to a vacuum pump, as shown in figure 12.6. If you press the switch, you will be able to hear the bell. Now start the vacuum pump. When the air in the jar is pumped out gradually, the sound becomes fainter, although the same current is passing through the bell. After some time, when less air is left inside the bell jar, you will hear a very feeble sound. What will happen if the air is removed completely? Will you still be able to hear the sound of the bell figure? 12.5. A vibrating object creating a series of compressions C and rarefactions R in the medium. Q figure 12.6. Bell jar experiment showing sound cannot travel in vacuum. Sound 163 waves. In these waves, the individual particles of the medium move in a direction parallel to the direction of propagation of the disturbance. The particles do not move from one place to another, but they simply oscillate back and forth about their position of rest. This is exactly how a sound wave propagates, hence sound waves are longitudinal waves. There is also another type of wave, called a transverse wave. In a transverse wave, particles do not oscillate along the direction of wave propagation, but oscillate up and down about their mean position as the wave travels. Thus, a transverse wave is the one in which the individual particles of the medium move about their mean positions in a direction perpendicular to the direction of wave propagation. When we drop a pebble in a pond, the waves you see on the water surface is an example of transverse wave. Light is a transverse wave, but for light, the oscillations are not of the medium particles or their pressure or density. It is not a mechanical wave. You will come to know more about transverse waves in higher classes. 1.2.2.3 Characteristics of a sound wave. We can describe a sound wave by its middle frequency, middle amplitude, and middle speed. A sound wave in graphic form is shown in figure 12.8c, which represents how density and pressure change when the sound wave moves in the medium. The density as well as the pressure of the medium at a given time varies with distance, above and below the average value of density and pressure. Figure 12.8a and figure 12.8b represent the density and pressure variations, respectively, as a sound wave propagates in the medium. Compressions are the regions where particles are crowded together and represented by the upper portion of the curve in figure 12.8c. The peak represents the region of maximum compression. Thus, compressions are regions where density is Questions 1. Explain how sound is produced by your school bell. 2. Why are sound waves called mechanical waves? 3. Suppose you and your friend are on the moon. Will you be able to hear any sound produced by your friend? 1.2.2.2 Sound waves are longitudinal waves. Activity 12.4 Middle. Take a slinky. Ask your friend to hold one end. You hold the other end. Now stretch the slinky as shown in figure 12.7a. Then give it a sharp push towards your friend. Middle. What do you notice if you move your hand pushing and pulling the slinky alternatively? What will you observe? Middle. If you mark a dot on a slinky, you will observe that the dot on a slinky will move back and forth parallel to the direction of the propagation of the disturbance. Figure 12.7, longitudinal wave in a slinky. The regions where the coils become closer are called compressions C, and the regions where the coils are further apart are called rarefactions R. As we already know, sound propagates in the medium as a series of compressions and rarefactions. Now, we can compare the propagation of disturbance in a slinky with the sound propagation in the medium. These waves are called longitudinal QAB. SCIENCE 164 Photoelectric effect, which was later explained by Albert Einstein. The C unit of frequency was named as Hertz in his honor. Frequency tells us how frequently an event occurs. Suppose you are beating a drum. How many times you are beating the drum in unit time is called the frequency of your beating the drum. We know that when sound is propagated through a medium, the density of the medium oscillates between a maximum value and a minimum value. The change in density from the maximum value to the minimum value, then again to the maximum value, makes one complete oscillation. The number of such oscillations per unit time is the frequency of the sound wave. If we can count the number of the compressions or rarefactions that cross us per unit time, we will get the frequency of the sound wave. It is usually represented by Greek letter, nu. Its C unit is Hertz symbol, Hertz. The time taken by two consecutive compressions or rarefactions to cross a fixed point is called the time period of the wave. In well as pressure is high. Rarefactions are the regions of low pressure where particles are spread apart and are represented by the valley, that is, the lower portion of the curve in figure 12.8c. A peak is called the crest and a valley is called the trough of a wave. The distance between two consecutive compressions C or two consecutive rarefactions R is called the wavelength, as shown in figure 12.8c. The wavelength is usually represented by Greek letter lambda. Its C unit is meter m. Heinrich Rudolf Hertz was born on the 22nd of February 1857 in Hamburg, Germany and educated at the University of Berlin. He confirmed J.C. Maxwell's electromagnetic theory by his experiments. He laid the foundation for future development of radio, telephone, telegraph and even television. He also discovered the figure 12.8, sound propagates as density or pressure variations as shown in A and B. C represents graphically the density and pressure variations. H.R. Hertz. Sound 165 other words, we can say that the time taken for one complete oscillation is called the time period of the sound wave. It is represented by the symbol T. Its C unit is second S. Frequency and time period are related as follows. 1 T. A violin and a flute may both be played at the same time in an orchestra. Both sounds travel through the same medium, that is, air, and arrive at our ear at the same time. Both sounds travel at the same speed irrespective of the source. But the sounds we receive are different. This is due to the different characteristics associated with the sound. Pitch is one of the characteristics. How the brain interprets the frequency of an emitted sound is called its pitch. The faster the vibration of the source, the higher is the frequency and the higher is the pitch, as shown in figure 12.9. Thus, a high-pitched sound corresponds to more number of compressions and rarefactions passing a fixed point per unit time. Objects of different sizes and conditions vibrate at different frequencies to produce sounds of different pitch. The magnitude of the maximum disturbance in the medium on either side of the mean value is called the amplitude of the wave. It is usually represented by the letter A, as shown in figure 12.8c. For sound its unit will be that of density or pressure. The loudness or softness of a sound is determined basically by its amplitude. The amplitude of the sound wave depends upon the force with which an object is made to vibrate. If we strike a table lightly, we hear a soft sound because we produce a sound wave of less energy amplitude. If we hit the table hard, we hear a louder sound. Can you tell why a sound wave spreads out from its source? As it moves away from the source, its amplitude as well as its loudness decreases. Louder sound can travel a larger distance as it is associated with higher energy. Figure 12.10 shows the wave shapes of a loud and a soft sound of the same frequency. The quality or timbre of sound is that characteristic which enables us to distinguish one sound from another having the same pitch and loudness. The sound which is more figure 12.9, low pitch sound has low frequency and high pitch of sound has high frequency. Figure 12.10, soft sound has small amplitude and louder sound has large amplitude. SCIENCE 166 pleasant is said to be of a rich quality. A sound of single frequency is called a tone. The sound which is produced due to a mixture of several frequencies is called a note and is pleasant to listen to. Noise is unpleasant to the ear. Music is pleasant to hear and is of rich quality. Questions 1. Which wave property determines the loudness? B. Pitch. 2. Guess which sound has a higher pitch, guitar or car horn. The speed of sound is defined as the distance which a point on a wave, such as a compression or a rarefaction, travels per unit time. We know, speed, v distance time t here is the wavelength of the sound wave. It is the distance traveled by the sound wave in one time period t of the wave. Thus, v or v, that is, speed wavelength times frequency. The speed of sound remains almost the same for all frequencies in a given medium under the same physical conditions. Example 12.1. A sound wave has a frequency of 2 kHz and wavelength 35 cm. How long will it take to travel 1.5 km? Solution, given. Frequency, 2 kHz 2000 Hz wavelength, 35 cm 0.35 meters. We know that speed, v of the wave wavelength times frequency v 0.35 meters times 2000 Hz 700 meters as the time taken by the wave to travel a distance. D of 1.5 kilometers is thus sound will take 2.1 seconds to travel a distance of 1.5 kilometers. Questions 1. What are wavelength, frequency, time period and amplitude of a sound wave? 2. How are the wavelength and frequency of a sound wave related to its speed? 3. Calculate the wavelength of a sound wave whose frequency is 220 Hz and speed is 440 meters s in a given medium. 4. A person is listening to a tone of 500 Hz sitting at a distance of 450 meters from the source of the sound. What is the time interval between successive compressions from the source? The amount of sound energy passing each second through unit area is called the intensity of sound. We sometimes use the terms loudness and intensity interchangeably, but they are not the same. Loudness is a measure of the response of the ear to the sound. Even when two sounds are of equal intensity, we may hear one as louder than the other simply because our ear detects it better. Question 1. Distinguish between loudness and intensity of sound. 1.2.2.4 Speed of sounds in different media. Sound propagates through a medium at a finite speed. The sound of a thunder is heard a little later than the flash of light is seen. QQQ. Sound 167. So, we can make out that sound travels with a speed which is much less than the speed of light. The speed of sound depends on the properties of the medium through which it travels. You will learn about this dependence in higher classes. The speed of sound in a medium depends on temperature of the medium. The speed of sound decreases when we go from solid to gaseous state. In any medium, as we increase the temperature, the speed of sound increases. For example, the speed of sound in air is 331 meters s1 at 0 superscript OC and 344 meters s1 at 22 superscript OC. The speeds of sound at a particular temperature in various media are listed in Table 12.1. You need not memorize the values. Sonic boom. When the speed of any object exceeds the speed of sound, it is said to be traveling at supersonic speed. Bullets, jet aircrafts etc. often travel at supersonic speeds. When a sound-producing source moves with a speed higher than that of sound, it produces shock waves in air. These shock waves carry a large amount of energy. The air pressure variation associated with this type of shock waves produces a very sharp and loud sound called the sonic boom. The shock waves produced by a supersonic aircraft have enough energy to shatter window glass and even damage buildings. 12.3 Reflection of sound. Sound bounces off a solid or a liquid like a rubber ball bounces off a wall. Like light, sound gets reflected at the surface of a solid or liquid and follows the same laws of reflection as you have studied in earlier classes. The directions in which the sound is incident and is reflected make equal angles with the normal to the reflecting surface at the point of incidence, and the three are in the same plane. An obstacle of large size which may be polished or rough is needed for the reflection of sound waves. Activity 12.5 Middle. Take two identical pipes, as shown in figure 12.11. You can make the pipes using chart paper. The length of the pipes should be sufficiently long as shown. Middle. Arrange them on a table near a wall. Middle. Keep a clock near the open end of one of the pipes and try to hear the sound of the clock through the other pipe. Middle. Adjust the position of the pipes so that you can best hear the sound of the clock. Middle. Now, measure the angles of incidence and reflection and see the relationship between the angles. Middle. Lift the pipe on the right vertically to a small height and observe what happens. In place of a clock, a mobile phone on vibrating mode may also be used. Table 12.1, Speed of sound in different media at 25 superscript OC state substance speed in MS solids aluminium 6420 nickel 6040 steel 5960 iron 5950 brass 4700 glass flint 3980 liquids water C1531 water distilled 1498 ethanol 1207 methanol 1103 gases hydrogen 1284 helium 965 air 346 oxygen 316 sulfur dioxide 213 Question 1. In which of the three media, air, water or iron, does sound travel the fastest at a particular temperature? Q. SCIENCE 168.12.3.1 Echo. If we shout or clap near a suitable reflecting object such as a tall building or a mountain, we will hear the same sound again a little later. This sound which we hear is called an echo. The sensation of sound persists in our brain for about 0.1 seconds. To hear a distinct echo, the time interval between the original sound and the reflected one must be at least 0.1 seconds. If we take the speed of sound to be 344 meters s at a given temperature, say at 22 superscript OC in air, the sound must go to the obstacle and reach back the ear of the listener on reflection after 0.1 seconds. Hence, the total distance covered by the sound from the point of generation to the reflecting surface and back should be at least 344 meters s times 0.1 seconds, 34.4 meters. Thus, for hearing distinct echoes, the minimum distance of the obstacle from the source of sound must be half of this distance, that is, 17.2 meters. This distance will change with the temperature of air. Echoes may be heard more than once due to successive or multiple reflections. The rolling of thunder is due to the successive reflections of the sound from a number of reflecting surfaces, such as the clouds and the land. 12.3.2 Reverberation. A sound created in a big hall will persist by repeated reflection from the walls until it is reduced to a value where it is no longer audible. The repeated reflection that results in this persistence of sound is called reverberation. In an auditorium or big hall, excessive reverberation is highly undesirable. To reduce reverberation, the roof and walls of the auditorium are generally covered with sound-absorbent materials like compressed fiberboard, rough plaster or draperies. The seat materials are also selected on the basis of their sound-absorbing properties. Example 12.2 A person clapped his hands near a cliff and heard the echo after 2 seconds. What is the distance of the cliff from the person if the speed of the sound, v, is taken as 346 meters s1? Solution, given. Speed of sound, v 346 meters s1. Time taken for hearing the echo, t 2 seconds. Distance traveled by the sound, v times t 346 meters s1 times 2 seconds 692 meters. In 2 seconds sound has to travel twice the distance between the cliff and the person. Hence, the distance between the cliff and the person 692 meters to 346 meters. Question 1. An echo is heard in 3 seconds. What is the distance of the reflecting surface from the source, given that the speed of sound is 342 meters s1? 12.3.3 Uses of multiple reflection of sound. 1. Megaphones or loud hailers, horns, musical instruments such as trumpets and shahani, are all designed to send sound in a particular direction without spreading it in all directions, as shown in Fig 12.12. Figure 12.11, Reflection of Sound Cue. Sound 169 soundboard may be placed behind the stage so that the sound, after reflecting from the soundboard, spreads evenly across the width of the hall. Fig 12.15. Fig 12.12, a megaphone and a horn. In these instruments, a tube followed by a conical opening reflects sound successively to guide most of the sound waves from the source in the forward direction towards the audience. 2. Stethoscope is a medical instrument used for listening to sounds produced within the body, mainly in the heart or lungs. In stethoscopes, the sound of the patient's heartbeat reaches the doctor's ears by multiple reflection of sound, as shown in Fig.12.13. Megaphone horn Fig.12.13, stethoscope 3. Generally, the ceilings of concert halls, conference halls and cinema halls are curved so that sound after reflection reaches all corners of the hall, as shown in Fig 12.14. Sometimes a curved Figure 12.14, curved ceiling of a conference hall. Figure 12.15, soundboard used in a big hall. Question 1. Why are the ceilings of concert halls curved? 12.4 Range of hearing. The audible range of sound for human beings extends from about 20 Hz to 20,000 Hz. 1 Hz 1 cycle s. Children under the age of Q. SCIENCE 175 and some animals, such as dogs, can hear up to 25 kHz 1 kHz 1000 Hz. As people grow older, their ears become less sensitive to higher frequencies. Sounds of frequencies below 20 Hz are called infrasonic sound or infrasound. If we could hear infrasound, we would hear the vibrations of a pendulum just as we hear the vibrations of the wings of a bee. Rhinoceroses communicate using infrasound of frequency as low as 5 Hz. Whales and elephants produce sound in the infrasound range. It is observed that some animals get disturbed before earthquakes. Earthquakes produce low-frequency infrasound before the main shock waves begin, which possibly alert the animals. Frequencies higher than 20 kHz are called ultrasonic sound or ultrasound. Ultrasound is produced by animals such as dolphins, bats and porpoises. Moths of certain families have very sensitive hearing equipment. These moths can hear the high-frequency squeaks of the bat and know when a bat is flying nearby, and are able to escape capture. Rats also play games by producing ultrasound. Hearing aid. People with hearing loss may need a hearing aid. A hearing aid is an electronic, battery-operated device. The hearing aid receives sound through a microphone. The microphone converts the sound waves to electrical signals. These electrical signals are amplified by an amplifier. The amplified electrical signals are given to a speaker of the hearing aid. The speaker converts the amplified electrical signal to sound and sends to the ear for clear hearing. Questions 1. What is the audible range of the average human ear? 2. What is the range of frequencies associated with infrasound? B. Ultrasound 12.5 Applications of ultrasound. Ultrasounds are high-frequency waves. Ultrasounds are able to travel along well-defined paths even in the presence of obstacles. Ultrasounds are used extensively in industries and for medical purposes. Middle dot ultrasound is generally used to clean parts located in hard-to-reach places, for example, spiral tube, odd-shaped parts, electronic components, etc. Objects to be cleaned are placed in a cleaning solution and ultrasonic waves are sent into the solution. Due to the high frequency, the particles of dust, grease and dirt get detached and drop out. The objects thus get thoroughly cleaned. Middle dot ultrasounds can be used to detect cracks and flaws in metal blocks. Metallic components are generally used in construction of big structures like buildings, bridges, machines and also scientific equipment. The cracks or holes inside the metal blocks, which are invisible from outside, reduces the strength